Hello and welcome again to this course on how to use deep learning for object detection using Tensorflow 2. So this course is comprised of 7 different sections, and in each section we will cover a bunch of topics. So let's go through them and see what we have. So in the first section of the course, we're going to start by talking about object detection as a concept in computer vision. So for this, we're going to start by defining what object detection is, and then we will talk about why do we use deep learning for object detection and not the classical methods in computer vision. And finally, we're going to talk about, we're going to look at these models from a high-level overview. So we're going to look at Faster RCNN, SSD, and YOLO from version 1 to version 5. So we're going to look at these models from a high level and try to understand them and how they function. In the next section of the course, we're going to talk about how do we choose the right object detection model architecture. So as I mentioned before, we have several different approaches like Faster RCNN, SSD, and YOLO. So in this specific section of the course, we're going to talk about speed and accuracy trade-offs in object detection. We're also going to talk about the accuracy versus time. So usually you have to, when you choose your model, you have to take these two into consideration. Then we're going to move to how the image resolution affects your object detection model. After that, we're going to look at how to choose the right model for your object detection task. And then we go to the next section where we will be basically installing all the necessary software for our work. So for the software setup, we're gonna see how to install Tensorflow with GPU support. If you have an NVIDIA GPU if you have an NVIDIA GPU on your machine, then you can install Tensorflow with GPU support. Then we're going to look at how to install Tensorflow 2 Object Detection API. In the fourth section of the course, we're going to talk about data for object detection. So object detection requires specific organization of data. So in this section, we're going to talk about the data set that we will use and where to get it from. Then we're going to talk about how to annotate the data set to prepare it for your object detection training. We're going to then finish this section by talking about how to generate TF records, which are the norm when reading data for object detection using Tensorflow 2. In the fifth section of the course, we're going to speak about how to train an object detection model using Tensorflow 2 Object Detection API. So for this, we're going to talk about the steps needed to build an object detector. Then we're going to talk about how to prepare your config file. After that, we're going to talk about how to run the training and testing on your local machine. Then we're going to talk about training and evaluating a Faster RCNN model on your local machine. And then we're going to do the same thing for SSD. So we're going to see how to train and evaluate an SSD model on your local machine. In the next section of the course, which is the sixth section, we're going to talk about how to train object detection API models using Google Cloud AI Platform. So in this section, we're going to see how to move our training and evaluation to Google Cloud AI Platform. So for that, we're going to start by creating a Google Cloud account and downloading Google Cloud Platform SDK. Then we're going to create a Google bucket and upload our data to it. Then we're going to train and evaluate a Faster RCNN model on Google AI Platform. We're going to analyze the results using TensorBoard, but on the cloud. Then we're going to talk about the possible things to do to improve our model performance. And then we're going to talk about how to export the frozen model from checkpoints. And finally, we're going to look at how to train and evaluate an SSD model on Google AI platform. In the seventh and last section of the course, we're going to talk about how to use YOLO version 3 for object detection. So we're going to look at how to train and evaluate this model on our dataset. So first, we're going to talk about the new setup for training YOLO v3 model, since the TensorFlow object detection API does not have the YOLO model, so we're going to use a different code base. So after this, we're going to prepare the dataset for YOLO v3 model training, because the dataset needs to be changed in order to consider the current or the code base that we're going to use for training YOLO v3. After that, we're going to train our YOLO v3 based object detection model. We're going to analyze the results of the training. Then we're going to evaluate our YOLO v3 trained model using new images. We're going to compute the mean, average, precision, and other metrics to be able to understand whether our model is good or not. We're going to finally save our model as a saved model format for production. And last but not least, we're going to talk about the steps needed to run the training on Google AI platform. So with this would be the last section of the course, and I hope to see you in class. Hello. In this video, we will be talking about object detection in computer vision, and we will be defining what object detection is. So let's first start by a well-known task that is in computer vision field, which is image classification. So in image classification, what we have is an image such as this one here, and we have a cat in this image, and the goal is to tell whether there is a cat in the image or not. So when you develop an algorithm for image classification, your input would be the image, and your output would be some sort of a confidence score, such as this one here. So the confidence score is usually between 0 and 1, which represents a probability of having a certain object, in our case a cat, in this image or not. So what we usually do is that we use some sort of a threshold, for example 0.5, and if our algorithm gives us a score that is equal or bigger than 0.5, then we say that we are confident that a cat exists in this image. If the score is lower than 0.5, then we say we are less confident and most likely there's no cat in the image. So this is about image classification. In object detection, what we do is actually classification plus localization. So what we would get is something like this. In an object detection task for computer vision, what we want to do is to first tell whether there is a cat in the image or not, and if there is, we want to be able to tell where that cat exists inside that image. So at the end, what we would get is some sort of an output like this, where we have a confidence of whether there is a cat or not in the image, and then we would have some coordinates. So for example, we would get an X and Y coordinates of this point here, and then we would get the width and the height of our bounding box. So this is called a bounding box. So as you can see, in object detection, what we have is basically image classification plus localization. And that's it for the definition of object detection, and I'll see you in the next video. Object detection can also be used for detecting multiple objects in a single image. For example, if we look at this image here, we can see that we can detect dogs, bicycles, trucks, and we can even detect more things if we wanted to, such as trees or motorcycles. And when we do this, the output would look something like this, where we have an output that contains confidence scores and then we have coordinates of the bounding boxes. So here we have 3 detections based on the detections inside the image. So the first detection is for the dog, the second one for the bicycle, and the third one for the truck. And each time we have a confidence score, and then we have coordinates of the bounding boxes. Usually this is X and Y of the top left corner of the bounding box, and then we have width and height. Sometimes X and Y could be the coordinates of the center of the bounding box, but this is a small detail and you don't need to worry about it for now. So as you can see, we can generalize object detection to detect multiple objects in one image, and this is very useful in many new industries such as the autonomous driving, where the car needs to detect signs. It also needs to detect people and other cars. So this object detection task is widely used in the industry. So deep learning tackles these issues by doing several things. So the first thing that is very distinctive for deep learning is that when we use neural networks for object detection, that's what we mean by deep learning for object detection. So we are using deep neural networks. In this case, the neural network starts learning very distinguishing features, which improves accuracy. And the second thing is that the computation is shared when we are doing the detection part, which improves the speed. And finally, the neural network starts learning enough features, distributions, to be able to generalize well on new unseen images. So when you look at state of the art in research and you look at how neural networks are performing compared to the old traditional methods where we didn't use deep learning, you can see that there was a huge jump in accuracy and also in generalization. So all of these points here are very positive for deep learning compared to traditional image processing techniques. And this is why, if you look at the research now in the field of object detection, basically no one is using traditional image processing techniques anymore. Everyone is using deep learning, so it just changes from one neural network to the other. They just change the architecture, the way they frame the problem, but at the end of the day, they are mostly all of them using object detection with neural networks. When we use deep learning for object detection, or when we use neural networks, there are basically 2 different types of neural networks for object detection. The first type is the one-stage object detectors, where we have YOLO family, and I say family here because there are many variations of the YOLO algorithm. There are currently 5 different implementations or 5 different ways that the YOLO algorithm is implemented. There's also the SSD family, and there is a new way of doing object detection, which is based on transformers. So transformers are a special type of layers in neural networks that was mostly used in NLP, so natural language processing. And recently researchers have started to try to implement these transformers in computer vision tasks, such as the object detection task here. And the second type of object detection neural networks are the ones called 2 stages object detectors. And here I have mentioned the RCNN. When I say RCNN, there is a whole family of neural networks here. There is the first RCNN, there is the fast RCNN, faster RCNN, and others as well. So The difference between these two is that the way they frame the problem is different. So in the one-stage object detectors, what we try to do is to directly infer the confidence, which means the classification, and also the bounding box coordinates in one stage. So the neural network takes the input, where for the input it takes the image, and it tries to predict the classes that exist in that image and the bounding boxes that exist in that image in one single way. So this is different than this second type, which is the two stages. For the two stages, what we actually do is that we first try to detect some sort of regions in our image that might contain an object. So at a first stage, we just try to see whether we have some object that we want to detect in the image. And there's a second stage that actually takes those possible areas that could contain an object, and then it classifies them into specific objects. So for the first stage, it will tell us whether it's an object or it's a background. And in the second stage, it takes all of those objects and it classifies them into, for example, dog, bicycle, truck, so on and so forth. And also in this second stage, we refine the bounding boxes and using a certain technique that is described in all of these papers. I will not go deep for these architectures here. We will go through some of the architectures in some videos in the future. In this video, I will be showing you the structure or the architecture of the neural network called Faster RCNN. We'll only do a high overview of the network and see how this mechanism actually works. So on the article for Faster RCNN, they have this picture here, or this image that shows the different steps that the Faster RCNN neural network takes in order to make predictions at the end for classes and also for bounding boxes surrounding objects in those images. So if we look at the image here, what we can see is that we start with an input image, such as this one shown here. And what we do is that we pass it through convolutional layers here. Usually these are layers from a pre-trained neural network that was used for classification mostly. So for example, we would use convolutional layers from VGG network or Inception network. And what we get at the end or as an output is feature maps. So these feature maps will then go through a neural network, a small neural network called Region Proposal Network, or RPN for short. And the goal of this RPN neural network is to propose regions that this network thinks that objects will exist in it. So it might think that this surface here or this area here will contain some objects, although it will not tell us which object it is. It's just going to tell us that, for example, these three regions here, they have objects that are different than background. So they could be like dog, bicycle, cat, whatever, but they're just different than background. So this is the goal of the RPN neural network. And after that, what we have is another neural network. So all of these networks here work together. So when we finish this part here, we have finished the first stage. So as you remember, the Faster RCNN neural network is a 2 stages based object detector. So when we finish this phase here, we have finished the first stage. And what happens next is that we pass the output of the RPN neural network and the feature maps to another neural network that is that has the main task of region or ROI pooling. ROI pooling is a region of interest. So what happens is that in this neural network, we get at the end classes and bounding boxes surrounding objects in the image. So just to recapitulate here, we have an image, we pass it through a set of convolutional layers. Usually they come from a pre-trained neural network such as VGG or Inception or MobileNet or others. We get some feature maps here. We pass the feature maps to the RPN neural network. The RPN neural network gives us some proposals where it thinks that some objects might exist in these areas, and then we pass those proposals and the feature maps to another neural network. This neural network is the one responsible for giving us classes and bounding boxes at the end. And just to go a little deeper, we will look at these steps one by one. So here in the Faster RCNN neural network, we start by an image. So this image goes through convolutional layers. Usually we call it a backbone. So as I said, this could be VGG 16, Inception V1, V2, V3, MobileNet, ResNet. All of these are used as backbone. But just to emphasize here, we actually use only the convolutional layers. And sometimes even the convolutional layers, we don't use all of them. We use some of them. We don't use fully connected layers in this part here. So for the VGG neural network, we're only gonna take first part of it where there are only convolutional layers. So at the output of this backbone, we get feature maps. And then what we do is that we assign some anchor boxes to the image. So this is something that could be confusing in the beginning on why we use anchor boxes. But I hope that by the end of this video, you'll understand why we use anchor boxes in Faster RCNN. So anchor boxes are a set of boxes, coordinates that we predefine in the beginning. We assign them to some cells in the original image, and then we try to use them as input for the region proposal network in order to actually use regression and make those bounding boxes converge to our ground truth bounding boxes. So I'll show you later an image that shows how anchor boxes usually are in the original image, but only at the end, after I finish showing you how this diagram works. So we start with the image, we pass it through the backbone, we get the feature maps. These anchor boxes are actually assigned to the image. So we assign them, we choose these anchor boxes. Then we pass those anchor boxes and the feature maps to our RPN neural network. And at the output of the RPN neural network, we pass it to the ROI pooling network, and we pass the feature maps to the ROI pooling network. And then we have here the RCNN or region convolutional neural network that actually takes the output of the ROI pooling and gives us a class corresponding to each object. And also there is a regressor here which gives us the bounding box at the output. So here we are saying refined bounding box. We are saying this because the goal of the anchor boxes is to actually start from a set of anchor boxes like this one here. So as I told you, imagine this is an image 600 by 600. So in this position here, almost 320. So in this position here, we assign some anchor boxes here. So as you can see, we have different sizes and different aspect ratios. And this we will do for each pixel, or we do it for example, for 1 pixel, then we use a stride of 2, and we do after 2 pixels we assign these anchor boxes, so on and so forth. So at the end, you can imagine that for each cell here, we will have a set of anchor boxes. And the goal at the end is to make these anchor boxes converge to our ground truth bounding boxes. This is what we call it a regressor. And this is what we say refined bounding boxes. We are refining our bounding boxes in order to make them fit or converge to our ground truth bounding boxes. So just to recapitulate again, we have an image, we have anchor boxes, and here I have used the 2 different colors. The blue means that we are actually passing through some layers, and the color orange here, or brownish, is representing things that are inputs, things that we set ourselves, or things that are outputs. So inputs, outputs, or things that we set ourselves. So here the image is an input, feature maps is the output, and here the anchor boxes are things that we set ourselves. And you can think of them as just a set or a list of some coordinates that represent all of these different bounding boxes here. So this is on a high level how the Faster RCNN works, and I hope that now it's more clear on how this mechanism works. And later, when I show you the one-stage neural networks for object detection, you'll see how they are different from this. So here it is a little bit complicated structure here, or architecture, and maybe the Faster RCNN is one of the most complicated architectures for object detection. But with the new research and with the new approaches, they are actually researchers are trying to make this much simpler. And the one-stage object detectors, for example, have this purpose of making things straightforward, because one of the things that, or one of the disadvantages of Faster RCNN is that it's slow. It's usually very accurate, but it's also slow, because we have these 2 different neural networks that are working together. So this one proposes regions, and then the other one gives us the classes and refines the bounding boxes. So this makes it a slow neural network, and on the other hand, it's very accurate. And I am saying this also from experience. I have tested this, and I have tested other neural networks that are one-stage based neural networks, and I have realized that Faster RCNN sometimes works much better than in fact, sometimes it works and the other neural networks won't work. That's how good the Faster RCNN is, but the disadvantage is that it's slow. We will look into this in more detail a little bit later. Let's look now at a one-stage based object detector called SSD, or single shot multi-box detector. So in their paper, they have this image here that shows the architecture of the neural network. And what we can see is that the SSD basically works as follows. It starts by an image and an input. It passes it through a convolutional neural network or a backbone, just like Faster RCNN. We get some feature maps here, and we can notice that after this we have multiple convolutional layers where we are making the volumes outputs here. So the feature maps, we are making them smaller and smaller and smaller. And as you can see, each time we are basically trying to make detections. So we pass the image through the backbone, we get some feature maps, we try to make some detections using this first feature map. We take the feature map, we pass it through another convolutional layer, and then we try to make detections on the output feature maps. Then we do that again, where we pass it through some set of convolutional layers, we get new feature maps, and we make detections in those feature maps. We do this several times, as you can see here. And at the end, we have a set of detections, a big number of detections here. And then what we do is that we filter those detections using a non-maximum suppression function here that I will explain later. So this neural network is much more straightforward, I would say, in terms of detections compared to Faster RCNN. So it is a one-stage object detector because it's doing detection in one step or in one stage. So we pass the image and goes through a series of convolutional layers. Then we get detections. We filter those detections. We get the final outputs. Unlike Faster RCNN, where we have to propose regions first, and then we try to make detections after that. So let's look at a step-by-step architecture of how the SSD works. So again, we start with an image. We pass this image through convolutional layers called the backbone. So again, this could be VGG, this could be Inception, MobileNet, or whatever. We get some feature maps at the output. Now, here comes the difference, as I have mentioned before. We actually assign or generate some anchor boxes based on those feature maps. So before, if you remember, we had that image and we had a set of anchor boxes to each cell or each pixel in that image, or depending on how we define it, we can define it, for example, in the first pixel, then in the 9th pixel, then the 18th pixel. That's actually a choice of ours. So here, the backbone will give us a set of feature maps. We generate the anchor boxes, and then we try to use those anchor boxes in a manner where we do some regression and classification so that we get classes and bounding boxes. This is very similar to the end neural network of Faster RCNN. But here what happens again is that we're going to pass those feature maps to other convolutional layers. And here you should notice that these convolutional layers are different than these ones. The first ones are usually coming from a pre-trained neural network. Mostly it's used for classification. That's why I said VGG, Inception. So we take the convolutional layers from those pre-trained networks and we put them here. But these convolutional layers are actually new convolutional layers that have parameters that will learn to extract good features for detection. So we get the feature maps, we generate new anchor boxes, and then we use classification and regression in order to get classes and bounding boxes. And we do this several times. In fact, we do this 6 times. Each time we are making the feature maps smaller in height and width. And the goal of this is that in different layers here, each time we are going smaller, this means that we are detecting bigger objects the deeper we go into the network. So if we think about the last layer here, the feature maps, when we generate anchor boxes and we try to detect bounding boxes and classes, usually at the last layer here, we are only detecting the bigger objects inside the image. And at the end, what we do is that we get all those detections coming from each feature map or from each step here, and then we pass them through a function called NaN maximum suppression, and what we get is a set of outputs that represent bounding boxes in our image and also classes corresponding to those bounding boxes. So here, as I said, we have 6 different layers here, and let's look at the non-maximum suppression operation and how it works. So in the non-maximum suppression, why do we need it in the first place? In fact, when we do object detection, we usually get this kind of bounding boxes at the end. So as you can see here, there are maybe 4 different or 3 different bounding boxes here, but they are all corresponding to the same thing, to the same object here. What we actually want is to have only one bounding box here, because all of them, they represent the same object, which is the face of this person here. So in order to do this, what we do is that we use an operation called IOU, or intersection over union. So what we do is that we take these boxes 2 by 2, and each time we take 2, what we do is that we look at the intersection of those boxes, and then we look at the union of those boxes. So you can imagine how we compute this based on the areas of the boxes, and then we compute this ratio here, so intersection over union. And what we usually do is that if the intersection over union is bigger than 0.5, for example, we say that they correspond to the same object if that is the same class. Because if you remember, at the end, the output will be a set of bounding boxes that have, of course, the coordinates and also a corresponding class. So here, we are doing this operation here and doing intersection over union because the predicted class is the same for all of these 3 bounding boxes. So only when we have a set of bounding boxes that correspond to the same class, then we do this non-maximum suppression, where we compute the intersection over union, and then we keep the bounding box with the highest confidence. So just to recap here, what we do is that first, when we do detections, we get a set of bounding boxes. So they have the coordinates and they have the confidence scores for each bounding box. Then what we do is that we look at all of the classes. If they correspond, if they are the same class, that means that they are looking at the same object here. So what we do then is that we take 2 by 2. For example, we take the first 2 bounding boxes, we compute the intersection over union. If the intersection over union is bigger than 0.5, then we say they correspond to the same class, to the same object, sorry, because we already know that they correspond to the same class, because at the output of the neural network, we have the class corresponding to each bounding box. But when we compute the IOU and the score is bigger than 0.5, then this means that they correspond to the same object in the image. So here the object is this face here, so they correspond to the same object. So if the intersection over union is bigger than 0.5, we keep the bounding box with the highest confidence here. So we do this for the first 2, so that means we are only left with 1, and then we do this for the last one and the one that we had in the operation previously. So at the end, we will get 1 bounding box here that corresponds to this object here with the corresponding confidence. So I hope that this is clear, and see you in the next video. So now let's take a look, or a closer look, of how YOLO algorithm basically works. So YOLO stands for you only look once. So if you take a look at the article, the first article published for YOLO network, they show this architecture here that represents how the network is constructed. So basically we see a bunch of convolutions. It looks very similar to a classification neural network, and it's much simpler than Faster RCNN, for example. And here, the main things that you need to take from this network here is that the anchor boxes, because YOLO also uses anchor boxes just like Faster RCNN and SSD. So YOLO algorithm is actually similar to Faster RCNN in terms of how the anchor boxes are or where they are constructed. So in Faster RCNN, we have the anchor boxes basically constructed or defined, let's say defined is a better word, so are defined based on the input image. So based on the input image, we split the image into multiple cells and then we define our anchor boxes there. So in that sense, YOLO algorithm is similar to Faster RCNN. But in fact, in terms of the architecture, YOLO algorithm is much more similar to SSD because it also has a bunch of convolutions. It's a one-stage object detector, so there's no small neural network that does proposing regions like Faster RCNN, but it's very, very similar to SSD since we have a bunch of convolutions and then we try to predict our bounding boxes at the end. But it's different than SSD in terms of if you took a look at SSD network, then you realize that in SSD we assign a bunch of anchor boxes in each level of the feature map. So for example, we input the image, we get some feature map here, we assign anchor boxes here, then that feature map goes through another convolutional layer, then the output we assign new anchor boxes, so on and so forth until the end. So we get so many anchor boxes in different levels of the network. But in YOLO, we actually define the anchor boxes in the input here. So the YOLO algorithm, actually, there are 5 variations or let's say 5 versions of it as of now. So now we are in November 2020. So far there are 5 different versions of YOLO. Four of them. So the first 4, they all have an article that came out to basically give a description of how the algorithm works. But for the 5th one, there's only the code. So there's no article that came from the researchers that were working on it, at least as of now. So we start with the YOLO basic architecture here. This is the version 1. So this is what they show us. It has 24 convolutional layers followed by 2 fully connected layers. And if we go to the next versions of YOLO, so if we look at version 2, sorry, which is called YOLO 9000, basically what started to happen is just some incremental improvements. So basically the researchers take what they had before and they make some changes and some experiments, and then they get some better results and they publish a paper about that, and they share the code with the deep learning community. So for the YOLO 9000, for example, one of the main differences from the YOLO version 1 is that anchor boxes were defined using k-means clustering. So in the beginning, in the first version of YOLO, we actually just assigned them mostly randomly. So we just choose some anchor boxes. But in the second version, or in YOLO 9000, we actually look at the ground truths of our data set. And based on that, we define a certain set of anchor boxes and with a certain amount of, or certain values for the size and the scale. So when we go further, when we look at YOLO version 3, which is actually the algorithm that we will use to train an object detector later. So for YOLO v3, the main contribution or the main difference, let's say, has been changing the feature extractor. So for any object detection algorithm so far, they all use a feature extractor in the beginning. So the first convolutional layers, they come from a feature extractor. In the case of YOLO v3, they changed it to a new, larger architecture or a neural network called Darknet 53. It's called 50. It says 53 here because it has 53 convolutional layers. So this was the one of the main differences compared to what came before YOLO v3. And if we move further, then, for example, for YOLO v4, the researchers started to think, why not run a bunch of experiments and try to get the results from all of these experiments, and based on those experiments, we choose the best options. So for the YOLO algorithm, you can, or the YOLO neural network architecture, you can basically divide it into 3 parts, where you have the backbone, you have the neck, and then you have the predictions. Of course, you have the input image in the beginning, but we're not going to consider it here, just the input image. So what they started to do is basically run a set of experiments where they change things. For example, they changed the backbone, they changed some of the things in the neck. So the neck is one small part of the network that comes before the output and after the backbone. So they experimented with some new layers that came out in the literature. So they changed these layers with those new layers. And also they made some changes in the dense prediction part here, so the final part of the network. So they ran so many experiments, and at the end they actually got some, the best results, they got them by having these parameters here. So for example, for the backbone, they found that the CSP Darknet 53 gave them the best results. For the neck, they used this SPP and PAN. We're not going to go through them here, but they're just a type of layers in the neural network or in the deep learning field. The head, they use the same as in YOLO v3. So with these, with this set of choices, let's call them like that, with these choices, we actually, or the researchers got the best results. And also they made some experiments based on on some things like bag of freebies and bag of specials. So for example, bag of freebies are the things that you can change and you can do during the training, and they won't affect the inference. So once you finish the training, you don't use them anymore in your testing or your inference. For example, there would be data augmentation. So one of the things that they added was mosaic data augmentation, which is a new technique. They basically take 4 images, they split each image into 4 parts, and then they take one part from the first image, they take a second part from the second image, third part from third image, fourth part from the fourth image, and they construct a new image with other objects. So this was one of the added things here. Bag of specials, they made some experiments at the backbone stage. So as you can see, these are just a bunch of choices here, and they were all part of a set of experiments where they tried so many things, and at the end they reported the best things that worked, that gave the best results. So as you can see, there wasn't really let's say a major change in terms of the logic of how YOLO works. It's just basically a trial and error set of experiments. So they tried many things and they found that these are the best that worked. And if we go to the final version, which is YOLO v5, which I mentioned, where currently, as of November 2020, there is no official article coming from the researchers, but some of the researchers published a new version of YOLO, called it YOLO v4. They published YOLO v5, sorry. So they only published the code. So the code is available on GitHub. And in fact, YOLO v5 can be summarized in one line. YOLO v5 is basically just YOLO v4, but with native PyTorch implementation. So what do we mean by this? Basically, before YOLO v5, so YOLO v4, v3, v2, and v1, they were all basically starting from some weights that were used, that were basically gotten from the darknet framework. But at the fifth version here, what some researchers did was to basically do the whole architecture in PyTorch, and everything was done in PyTorch. And they realized that by doing this, they actually got some much better results. So to me, this is not a let's say a major improvement. Of course, in terms of results, it was better, but in terms of the logic, the neural network, things like that, they didn't make any differences. So that's why for YOLO v5 and YOLO v4, we're not going to be using them in this course. We're just going to focus on YOLO v3, because that, to me, maybe it was the last stage where there was some major changes. But of course, I also wanted to use actually YOLO v4 in this course. I wanted to show you how to train YOLO version 4. But what I realized is that there aren't that many good implementations in TensorFlow 2. And if I either do this myself or I take the one of the pre-existing codes, I realized that it's gonna take time, and since there weren't that many differences from the neural network architecture standpoint, that's why I just stayed with YOLO v3, and this is what we were gonna use to train an object detection model at a later stage. So with this, that will be the end of this video, and see you in the next time. Hello, and welcome to this video where we will be talking about choosing the right neural network for your object detection task. So when you are about to use object detection, specifically deep learning for your object detection task, you have few things to consider. So one of the main things is, what is more important for you? Is it speed or accuracy, or is it both? Because usually you have to compromise between the two. You can't always have great speed and great accuracy at the same time. So based on this choice, you will have to go with one of the well-known object detection neural networks. Another thing that you should consider is, how will you deploy your model? Is it on the cloud? By the cloud, I mean, is it on Google Cloud Platform, for example? Is it on AWS? Is it on Azure? Is it on somewhere else? Or is it on Edge? And on Edge, I mean, do you want to integrate your model with a mobile app? So the app will be or will have a deep learning model integrated with it. And also, there are other types of edge. When we speak about edge, it's also the types of software that's embedded on a mini laptop, for example, and then you would integrate your deep learning model within your software. This could be in C++, for example, on as a Windows application or something similar. So based on these choices, you have to choose the right neural network for your object detection task. One of the main resources that is used by machine learning practitioners is a paper from Google Research called Speed Accuracy Trade-offs for Modern Convolutional Object Detectors. In this paper, they make a comparison between many different neural networks for object detection, and they change so many things. For example, the image size, width and height, They also changed the different backbones. If you remember, backbones are the first convolutional layers that the image will go through in Faster RCNN, in SSD, and also in YOLO, and many other different algorithms for object detection. So this paper here, I will be referencing it so many times throughout this section and maybe throughout the course, and we will be taking different parts from it so that we can make good decisions when we are about to choose a certain neural network for our object detection task. So I will put a link for this paper with this lecture, and you should use this if you are an ML practitioner or deep learning practitioner who's working a lot on object detection in computer vision. So one of the things that we always need to consider when choosing our object detection neural network is the accuracy versus time. So accuracy represents how precise the neural network is when making predictions, and time is the time that the neural network takes when it's making inference or when it's making prediction. So this is a graph from the paper that I have referenced before, where they have made so many experiments with 3 different types of neural networks, which are Faster RCNN, RFCN, and SSD. And for us, we'll only consider Faster RCNN and SSD in this course because SSD is very fast and Faster RCNN is very accurate. RFCN is somewhere in the middle, so we will not be considering it in this course. So as we can see in this graph here, so this shape here, circle, represents Faster RCNN based neural networks. This shape here, which is a square that is a little bit rounded, represents SSD neural networks. And the colors, they represent the different backbones that are used in this with these neural networks. And what we can see is that on the x-axis, let me just make this smaller. So on the x-axis here, we have the GPU time. So this is the inference time. When we pass the image to the neural network, this is how much time it takes to make the prediction. And this is in milliseconds. So at most here, it takes 1 second, 1000 milliseconds. And here we are around 100 milliseconds, for example. And what we can notice immediately is that Faster RCNN based neural networks, they tend to be the most accurate. As you can see, all of these circles, they represent Faster RCNN based neural networks. And they are the most accurate ones between the rest of the neural networks. And if we look here at the bottom where we have smaller accuracy or mean average precision, this MAP is mean average precision, which represents how precise the neural network when making predictions. So here at the bottom left, we can see mostly RFCN and also SSD based neural networks. And here what these represent are the neural networks that are the fastest, but of course we have to compromise on accuracy here. So whenever you make a decision about using SSD or Faster RCNN, you can come back to this graph here and you can make so much conclusions just by looking at it. For example, we can see that with Inception V2 and using SSD, we get somewhat a possible good precision here, and also we're not compromising too much when it comes to the time of predictions. And also, of course, there is another thing here that is not shown explicitly in this graph, which is the resolution of the images. So when we see these 2 points here, or these 2 shapes here, they both represent SSD, with Inception v2, but we see that they represent two different things. And basically the change here is based on the image resolution. So in this paper, they had low resolution images and high resolution images. So for example, we see here, this one here compared to this one, this is faster because the image resolution that we are using here is lower. I believe it's 300 by 300 or something close. And that's why we see, for example, this arrow pointing to this one here. It says SSD with Inception v2, low resolution. And the same thing here with MobileNet, low resolution and used with SSD. So just using this graph, you can get a much better idea about the choices for your backbone, for example, and for your specific neural network, Faster RCNN, SSD, or whatever. So this is just one of the graphs that is shown in that referenced paper, and we will look at other graphs in that paper as well so that we can make better decisions. So in the previous video, we've seen how the choice of the neural network, so Faster RCNN or SSD, and its backbone affects how precise the model will be and how fast it will be at inference time. So now let's take a closer look at the backbone and how the accuracy of the backbone is linked to the mean average precision of the full model. So when we say feature extractor accuracy, we mean that these models here, so MobileNet, VGG16, Inception v2, ResNet 101, and the others, these are well-known neural networks that are used in the classification tasks. And we have defined what classification task is in the beginning of the course. And basically what we are trying to see in this graph here is whether the accuracy of the backbone affects the mean average precision of the full model. So as we can see here, when we look at this, so the color red represents Faster RCNN, green represents RFCN, and orange represents SSD. We will not consider the RFCN neural network. We will only consider Faster RCNN and SSD. So here we can see, for example, that with SSD, when we choose VGG16 as a backbone, or Inception v2, or Inception ResNet v2, this shows that although the feature extractor is increasing in accuracy, so Inception ResNet v2 is much more accurate than Inception v2, and Inception v2 is much more accurate than VGG16, but overall the mean average precision of SSD is not changing that much. We are gaining only a few points of mean average precision here. So for example, if I am making a choice here and I want to use SSD, then I would definitely go with Inception v2 or maybe ResNet 101. I would definitely avoid using Inception ResNet v2 because I am not really gaining in mean average precision. And when we look at Faster RCNN, for example, we see that with MobileNet and with VGG16, the accuracy, or let's just look at VGG16 here, because it's basically the one that was used in the original paper for Faster RCNN. So here we see that with VGG16 as a backbone, we get somewhat 23% mean average precision. But if we choose ResNet 101, for example, and it is a more accurate model, we actually gain a lot in terms of mean average precision. And if we go further and we choose, for example, Inception ResNet v2, which has a very high accuracy in terms of classification, we see that we didn't really gain that much in terms of mean average precision. So if I were to use Faster RCNN and I want an accurate model, then Of course, I can go with the Inception ResNet v2 to gain just few percentages here, but overall, I would just go with ResNet 101 because it shows that we're not gaining that much in mean average precision when choosing Inception ResNet v2, which is a more complicated neural network than this one. So this is another thing that you should consider when making the choices for a specific neural network and its backbone. So you can look at this graph here and you can make so many conclusions just by looking at this. So you might have, for example, thought before looking at this that the more accurate the backbone is, the better your overall object detector will be. But actually, it's not the case, or it's not always the case. And as we can see, SSD with Inception v2 shows us that even with a lower accuracy for classification with Inception v2, we actually have better overall mean average precision for our object detection model. Another thing that you should consider when choosing your object detection model for your specific task is how the model performs with respect to the object size. The object size here, we mean that the object that you want to detect in your image. So in that same reference paper, they have made these experiments here, and they have given us these graphs that tell us a lot about how the neural network will perform when the object size is either small, medium, or large. So here, the blue color here represent the overall mean average precision, and the green one represents the mean average precision of the network when the object that it's trying to detect is large. So you can think of it as a car, for example, on the road. If it's closer to the camera, it will look large. And if it's far from the camera, it will look small. So this is how you think about large and small objects in the image. The orange represents medium-sized, the mean average precision for medium-sized objects, and this pink color represents the mean average precision when we have small objects, so objects that are far from the camera. So here, when we look at this, we can make so many conclusions again. For example, we see that overall, when the objects are large, then Faster RCNN works best. It has the best mean average precision. And when the objects are medium, so here the orange colors here, we see again that Faster RCNN is still the most accurate one for this size of the objects. And also, when we look at the small objects, so the pink color here, again, we see that Faster RCNN is doing very well. And here, this is Faster RCNN with ResNet 101 as a backbone, and this is Faster RCNN with Inception ResNet v2 as a backbone. So this is also something that you should consider when choosing your neural network, depending on the sizes of the objects that you want to detect. So generally speaking, when we look at the different data sets that exist, the public data sets, we see the same objects in small size and in large size. But depending on your application, maybe you have a fixed camera on that's looking at something specific, and you always know that the thing that you want to detect is small. So in this case, you would go, for example, with Faster RCNN if the time is not a constraint. So if you have enough time and you're not looking at real-time object detection, then you would go with Faster RCNN because it's the most obvious choice here. So apart from this, we can see that, for example, with SSD here, with large objects, it's still doing very good compared to Faster RCNN. And since SSD actually takes less time at the inference than, for example, Faster RCNN, this means that if you are looking for a model that needs to make predictions fast, then maybe you would choose to lose some points in terms of mean average precision, but you will gain some points in terms of speed here. So this is another thing that you should consider, and this graph is very helpful in making those decisions. When choosing your object detection model, so the architecture for your object detection task, you also need to consider how the resolution of the images affects your object detection model. So by the resolution, we mean the width and the height of the image. And in the paper that was referenced, we see this graph here where they have made some experiments and they have shown us the results here. And as we can see, the blue color represents images or models that was trained on images with resolution 300 by 300. And the green color represents models that were trained on images with size 600 by 600. And again, the circle represents Faster RCNN, the square represents RFCN, and the rounded square represents SSD here. So from here, we can see some immediate things. For example, if we choose, or if we have large images, so 600 by 600 in our input, we see that overall Faster RCNN performs better. So the accuracy or the mean average precision is much better when using Faster RCNN. And here we see that on the lower end, when we choose, for example, SSD here, and with 300 by 300 images, we see that we can get some good mean average precisions and very good speed here in terms of prediction. So this is something that you should also consider. And I actually have faced this myself when I was working in the industry. So at some point we were resizing our images in order to fit them to the neural network that had 600 by 600 as inputs, for example. But I realized that if we can somehow look or just choose a region in our image and just crop that region 600 by 600, then we would get much better results, because then the object will not look very small, because it will look small if we resize a large image and we make it only 600 by 600. So we made some decisions based on what we know about how the model performs in terms of the image resolution that was used when it was trained. So this is something that you should consider. Always remember that when you choose a specific image size or image resolution for your model, this means that whenever you have to pass new images through the model, you actually have to resize them to that specific resolution. And if you have small objects in your image and your image is large, then what happens is that when you resize it and you make it smaller, the object will look very small. And when the object looks very small, then it might be harder for the neural network to detect. So in this specific case, you need to figure this out. For us, for example, as I have mentioned, what we did was we used some a priori information that we had from some sensors, and we were able to tell at least where the model exists with some relative precision. Of course, it wasn't a good precision, otherwise we wouldn't have used object detection with deep learning in the first place, but we had some sort of an information that tells us that in this specific region, for example, the object exists. So what we did was just crop our image 600 by 600 and then pass this crop here through the network instead of resizing all of our large image. And these are very important points to consider when choosing your object detection architecture. So far, we have looked at SSD and Faster RCNN neural networks, but we will be covering YOLO neural network in this course as well. But in that reference paper, they don't cover the YOLO deep learning model. And for that, what I have done is that I looked at the papers for YOLO algorithm, and I have taken the parts where they made comparisons with SSD and Faster RCNN. So first, let's just look at YOLO v4. So for now, actually, there is a new version of YOLO, which is YOLO v5. This is as of October 2020, but the new architecture or the new YOLO v5 is actually just the code that was released, and there's no official article that was released yet. And it is better than YOLO v4 in terms of accuracy, but for now I will only be mentioning YOLO v4 because this is the paper where we have the experiments that they made and the comparisons with other deep neural networks, and this is what we need for now. And as we can see here, for YOLO v4, they used as backbone CSP darknet 53, which is a type of classification deep learning model, just like Inception v2, for example, or ResNet. And with this model here, they have an average precision of 41.2%. And with YOLO v4, when we change the image resolution here, so here 416 is the size of the image, so 416 by 416, this is 512 by 512, and this is 608 by 608. And we can see that the average precision is high here, so it's 43%. And if we look at the previous version of YOLO, so YOLO v3, we see that, of course, they used darknet 53 as a backbone. They didn't use CSP. This was an addition in YOLO v4. And the image resolutions that were used are 320, 416, and 608. And just here, when we look at the average precision, we see this huge jump in accuracy. So from 28.2% to 41%. Or if we look, let's look here because this is the one that has the same image size. So YOLO v3 with 416 as image size. Here, 31% to 41.2%. So more than 10% increase in overall average precision, which is a huge jump, and which means that the model is much more accurate. And still, in terms of speed here, so this is frame per second, which is how we measure speed of inference in videos. So in videos, we have many frames. So how many frames per second does the model or can the model basically predict? So you can think of it, how many images per second will it process at the same time. So with YOLO v3, we had 45 frames per second, but with or 35 frames per second for the same image size. And here we actually get to 38 frames per second. So we have also increased in terms of speed. So just between two versions of YOLO, so YOLO v3, YOLO v4, we actually increased in terms of speed and accuracy. But now what we need to know, or what we would like to know, is how does this compare to the previously mentioned neural networks such as Faster RCNN and SSD. So let's start with SSD. So SSD is as I have mentioned before, it's usually faster than Faster RCNN. So here, when we look at SSD, since they did not use the same image resolution, we can't compare directly. Let's say we don't have the same image resolutions here, so we're just gonna take the 300 by 300 image resolution for SSD, and we will compare it to 416 by 416 for YOLO. So here, for SSD, we actually had 43 frames per second in terms of speed of prediction. So compared to YOLO v4, it's faster. But in terms of accuracy here, we see that it's much, much lower than YOLO v4. So almost 16% different. And this means that what would you rather have? Would you rather have a little bit more speed here, so around or 5 more frames per second, or would you like to have more precision with only small or smaller speed compared to SSD? So this is another thing that you have to make a decision about. And of course, usually when we speak about speed, usually we speak about YOLO, although it has a little bit slower speed compared to SSD, but the accuracy that it has, the average precision that it has is much, much better. So we just usually go with YOLO here. And also, beyond 30 frames per second, we are at the real time. So this addition of 6 frames or 5 frames per second here does not give us that much benefits compared to the drop of precision here. And finally, let's look at Faster RCNN with ResNet 50 here. And what we can see is that overall, YOLO is better than Faster RCNN in terms of precision, and in terms of frames per second, Faster RCNN is very, very slow. But of course, this is not a thorough comparison. I should mention this now. As you can see here, for example, we're only showing results from SSD with VGG16. So when we change, for example, the backbone to Inception v2, then we will probably gain more in precision. So maybe we'll get closer to this value here for YOLO v4. And the same thing goes for Faster RCNN. As you can see, we're using ResNet 50 here. And this means that we are not doing a thorough comparison, but still overall, YOLO v4 is performing much, much better in terms of speed and accuracy. So if we're doing some sort of compromise, I think YOLO v4 is at the best spot here. So if you want the best in terms of speed and accuracy, then you should probably go with YOLO. And we will go, or I will show you a diagram later on how to make the decisions based on the choices that you have. So do you want real time or do you want more precision? I will be showing you some sort of a guideline on how to do this in videos in the future. In order to help you make the decision when it comes to object detection, I have created a diagram that you can follow whenever you have a task that needs to be solved using object detection and deep learning. So depending on your industry and your resources, so for example, if you're an engineer in the industry with a focus on production instead of research, so you don't have a lot of time, you don't have many resources to do so much research in deep learning, then what I would suggest is the following. You can just start with YOLO v4 or v5. This is the safe choice. And just try this on your data set and see what it gives you. And if the results are good, then great, then your job has finished. And when I say good results here, what I mean is the loss function going down during training? Is the training stable? Is the accuracy going high? All of these things. If these things are good, then you basically have, you can just continue with YOLO v4 or YOLO v5 and you're done. But what if the results are bad? And this could come in the industry, especially when you have some tasks or some types of object detection that was not tested in the research community. For example, if you work in manufacturing, you might be using object detection to detect some specific mechanical pieces that don't really exist in public data sets. So maybe when you try YOLO v4 or v5, it won't work and the training will not be stable. In that case, you should ask yourself the following question. Is speed more important to you than accuracy? So are you looking to have a model that makes inference as fast as possible, even though you compromise on accuracy? If the answer is yes, then just use Faster RCNN with a small number of region proposals. This could be a solution for you. So Faster RCNN is known to be very accurate, and when we decrease the number of region proposals, we actually get a model that is fast in terms of prediction. So this is just one variable here, which is the region proposals. This is what I am suggesting for you to change. But remember the previous slides where I have mentioned the backbone, for example. So choosing a certain backbone architecture could affect the speed of your prediction as well. So you can play with that parameter as well. And for that, you can go back to the slide where I have mentioned this, and you can make the right decision based on that. And what if you actually want accuracy instead of speed? What if in your specific task, you don't need real-time object detection, but you want something as precise as possible, something that doesn't make mistakes a lot? In that case, you can just go with a Faster RCNN with a large number of region proposals. So if you increase the number of region proposals, the accuracy will go higher and the speed will go lower. So this is the compromise that you have to make here. And again, going back to what I have said before, as you remember, there are many things that you can choose from, so that you either prefer speed or accuracy. And we have seen in the previous slides things that you can change, for example, the image resolution and other things as well, the backbone again. All of these affect your speed and accuracy in terms of the neural network that you choose. So this is just a small diagram that you can use as a reference. And this is in the case where you are focused on production instead of research. So you just want to use what's available in the research community, and you don't want to do research by yourself. You don't have maybe resources or you don't have the time. So in that case, so if you're an engineer in the industry, or maybe you're a research engineer, or you're a scientist working closely with the industry, then you probably have enough resources, time, hardware, infrastructure, GPUs, TPUs for training, and all of these. So in that case, of course, because you're in the industry, you're still focused on production, so you want things as fast as possible, you want results as fast as possible, but still you manage and you have time to do some research. In this case, then, maybe you can start the same way as before, just use YOLO v4 or YOLO v5. And if you get good results, if your loss is going down, your precision is going high, then great, you can just stop here. If your problem is solved and you're able to detect the objects in the images that you have, then you can just stop here. But if the results are bad, so if the loss function is not going down, maybe the training is not stable, in this case, you can ask yourself again the question, is speed more important than accuracy for you? If the answer is no, so if the accuracy is more important than speed, in that case, you can use Faster RCNN with a large number of region proposals, as we have mentioned before. And on the other hand, if speed is more important than accuracy, then what you can do, which is, this is a suggestion made by me after looking at how the research is doing in terms of object detection, and also after trying these neural networks in an industrial context. What I would suggest is to build SSD from scratch and try adding the modifications made in the YOLO v4 paper. So I am saying this because if you look at the papers for SSD and YOLO v4, for example, the first time SSD came out, it had better accuracy and it was faster than YOLO. And since then, to the best of my knowledge, there haven't been any new modifications to the SSD neural network. So that's why we haven't seen the same thing as in YOLO. For example, in YOLO, we speak about YOLO version 1, 2, 3, until 4 and 5. But with SSD, we mainly speak about the original version that was trained with VGG16. And with YOLO v4, actually what happened, how did they get that good accuracy and still keep that speed of prediction? What they have made is just a series of modifications in terms of, for example, data augmentation. They added some data augmentation techniques. They also made some changes in some specific layers. It wasn't a big change. They just introduced some new techniques that were that has been in the research just recently, and they added those modifications into the original implementation of YOLO. And basically what they have done is a bunch of experiments, trying many different things, and that's how they were able to get very high accuracy and also have very good speed in terms of prediction for YOLO. If someone can do the same thing for SSD, then I believe that you can reach high accuracies and maybe even higher than YOLO v4 or YOLO v5. But of course, this will take time, the experiments that you have to make and the resources that you need to have. All of these can be constraints to you. So at the end, if the results are good here, then great, then you have finished. But if even at this phase here, the results are bad, in that case, you can go back again to Faster RCNN and use a small number of region proposals, and also maybe play with the backbone and the image resolution. So this is just a small diagram here that I hope could be helpful for you when making the decisions about which neural network to use in your object detection task. And see you in the next video. So the main tool that we will be using to train our deep learning models for object detection is the Tensorflow library, and it's a library from Google for deep learning. And now they have the Tensorflow version 2, which will be installed by default when you install Tensorflow. So for us, we will be training the models on our local machine at first. And for that, if you have a GPU enabled machine, if you have actually an NVIDIA GPU, then maybe you can use that GPU during the training, which accelerates the training in a great manner compared to if you do the training on your CPU. So in order to install TensorFlow for GPU, you had to tensorflow.org/install/GPU, and you will get to this web page here where there are all the necessary information for you to install TensorFlow GPU. And we will not be specifying the version 1.15 because we will be installing the newest versions and not the old versions. So the first thing that you need to do is actually to verify whether your GPU can be used for training. So for this, you can go to or use this link here, and let's try to see here. And here on this page, you can check the machine that you have, whether it's enabled or not in terms of training using the GPU. So for me, for example, let's say, okay, I don't have a Tesla, but if you have a Tesla machine, which is very a good machine for training deep learning models, then you can check here. Let's see Quadro products here. If you have a Quadro product, you can check here. This is the list, and you can go check all of these. If your GPU, if your NVIDIA GPU exists here, then you can use it for training deep learning models. Again, the same thing here. You can check this. For me, I actually have a GeForce RTX 1050i, and at some point, in fact, it didn't exist on this list, but it still had the GPU enabled for deep learning. I checked that online. For now, I don't know if it was added to the list or not. Let me just check quickly here. So let me just do a quick search. So 1050. So there's only this one mentioned here. It's the same thing as the first time I checked this list. So here there's only GeForce GTX 1050, but in fact, mine is GTX 1050 Ti, and it still has GPU enabled. So if you have an NVIDIA GPU and you can't find it in any of these lists, then you can do a quick Google search to see if you can use it for training deep learning models, because sometimes it won't be in this list, but you will find that some people have used it and they can confirm to you that you can use it for deep learning. So this is the first thing you should do. If you don't have an NVIDIA GPU, then in this case, you can't really train deep learning models on your GPU. You can still train them on your CPU. It's just that it will be slower, in fact, much slower than when you use a GPU. So here, let me go back here. Once you check whether you have an NVIDIA GPU that you can use for training or not, you can come to the software requirements here. And as you can see, you have to, or you need to have some things installed, some software installed on your machine in order to be able to use TensorFlow for GPU. So here, the first thing that you should install is the NVIDIA GPU drivers. And as it's shown here, it says CUDA 10.1 requires 418.x or higher drivers. So here, if you go to this link here, and I have actually opened it already in here, and you can enter your configuration for your specific GPU. For me, it's 1050 Ti, GeForce 10 series, and here I actually have a Linux 64-bit. So for me, in fact, I didn't install the drivers using this download here. In fact, what I have done is that I went to Activities, and if you type drivers, you can go to Additional Drivers, and here is going to open a window, and in Additional Drivers, it should list the drivers for NVIDIA GPUs that are available. So for me, at first, it was not installed. I had, in fact, this choice here that was already chosen. For me, I chose the 450, which is proprietary, and it's tested. So I chose this, and once I clicked apply changes, it installed it on my machine. So I went this way for Ubuntu. If you have Ubuntu, I recommend that you do the same thing as I did. Don't do it by downloading the drivers and installing them from manually, let's say. But here you can just go to the additional drivers, choose the right or the last driver that is from NVIDIA, and it's proprietary and tested. If you see on the list some choices where they have open source drivers and they have proprietary drivers, then I recommend that you choose the proprietary ones. For me, I don't have open source drivers, but at some point I remember I had those choices as well. So if you have both of them, then choose proprietary drivers, which is recommended. So when you apply the changes, it's going to be installed and you will have the drivers on your machine. Now, if you have a Windows machine, in that case, you can enter your configuration here, and for the operating system, you can go to your Windows version. Let's say you have Windows 10 64-bit, and let's say you have the same configurations as these ones here. You can click search, and here you get to this page where you can basically download the driver, and once you download the driver, you can install it like you install regular software on Windows. So for me, I won't be going through this, but I want to show you at least how to download the driver for your Windows machine. And once you get to this page here, you can just click on download, and it's going to give you access to that download link. So you're going to download an executable, and then you run it and just go next, and install. So for me, I will not install it. If you face problems with this, please let me know. But for me, I will just stay with my current configuration for Linux, for Ubuntu, and I'll be closing this. So going back here, in this step here, you can see that you should also install CUDA Toolkit and kubectl here, which comes basically, it ships with CUDA Toolkit, so you don't need to install it separately. And you also need to have QDNN SDK 7.6. This last step here is optional, so we will not consider it for now. And there is actually a much easier way to install all of these in one go. So that's what we will be doing in the next video. We will not be installing these things separately. We will actually create a virtual environment and install all of them at the same time with a few commands. So let's do that in the next video. So as I said, for installing the rest of the software that's needed to run the object detection API and to run other scripts as well, we will create a virtual environment using Anaconda, and we will install these dependencies inside of that virtual environment. So for Anaconda, actually, we will install the Conda Python package using pip. So Conda is, as it's mentioned here, is a cross-platform language agnostic binary package manager, and it is the package manager used by Anaconda. So you can actually install Anaconda, which comes with a GUI that you can use, and you can install things using that graphical user interface. But for our purpose, for the deep learning part that we will do, Conda will suffice. So we're just gonna install the package here using pip. So for this, let's copy this, and for me, it's already installed. So if I run this, it's gonna tell me that requirement already satisfied. For you, it's gonna ask you if it can install some packages. You answer with yes, and it's gonna install all of those packages. So let me clear this. So now I have Conda installed. And just to mention something, if you are on Windows, you can go to the website, so docs.conda, for example. You can maybe I'll link this to this lecture. So installing on Windows. There's also a guide here on how to install on Windows. For Windows, you will need to download a certain installer. So you can either go with Minikanda. So Minikanda is basically a small terminal where you can run all your commands, the same commands that we will be running throughout this course. So you can either download this, or you can download Anaconda installer, which has a graphical user interface, and you can install things actually by choosing them from a menu, so on and so forth. So depending on your choice, for the purposes of this course, I will be only using the terminal to run all Conda commands. So Minikanda should be enough. So for you, you can just come here and choose, for example, for Python 3. And I do recommend you choose the ones for Python 3. Avoid using the ones for Python 2. And here, based on your machine, if you have 64-bit or 32 bits, you choose the right installer and then you can download it. So let me just stop this here and let me just close this and come back here. Okay. So that's the way you can do to install it if you have a Windows machine. So for Ubuntu, we installed it using the pip install Conda command, and now we have it and we can interact with Conda using the virtual or using the terminal. So now we need to create a new virtual environment, and then we will install the rest of the software. The ones here, we will install them at the same time. So for this, let me just go back to the guide that I showed you, the one that my friend created. And I do recommend you come here as well. You look at his tutorial. It's an additional tutorial. We will not be using the same example that he used here. He used the famous example from a Raccoon dataset. We will actually use something very different. But for the installation process, it's very clear here. So we're gonna use the same commands as he had, or something similar. So let's first create our environment by using this command here. So let me just copy it, come here, paste it, and I want to change this. I want to use the 3.8 Python version, and here I want to change this to TF2, and I'm gonna state here that it's a GPU that I will be installing TF2 GPU version. This will make it easier for me and for you as well. When you look at your virtual environments, you can immediately know which environment contains the installation for TensorFlow enabled GPU. And if you, for example, decide at some point that you want to use TensorFlow for CPU, then you can create another environment and you can give it a meaningful name, for example, TF2 underscore CPU, which you know that you're gonna install TensorFlow for CPU in that environment. So let me create this environment here, and let me click on or choose yes here to install all of these. It could take some time to install everything. No, actually it was very quick. So now that we have this, we will activate our environment using this command shown here. So let's do conda activate tf2 underscore GPU. So now we have activated our virtual environment, and you can always verify if you activated it or not by looking whether the name of your environment is used at the start of the command line here. So now let me clear this, and now we will install the rest of the dependencies. And for that, what we will do is to install or to use this command here. So if you come to the guide again, you can see that you can either install TensorFlow GPU with a specific version here, but if you use this command, this means that you have already installed these pieces of software here by your own or on your own. But if you haven't installed them, which I do recommend if you just want something quick and you want something even isolated from your system, because if you install these things by each time going to the website and downloading some installers and running them, what's going to happen is that they're going to be installed on your system. So on specifically, they won't be isolated, and this is something that I try to avoid. So for me, I will choose the second type here, where I will be installing, creating a virtual environment or installing inside my virtual environment, which comes with a CUDA toolkit installed, and it has everything necessary to run TensorFlow for GPU. So now, in order to install all the necessary software that comes with TensorFlow for training on the GPU, we're going to use this command here, so conda install. In fact, I won't specify the version here. I think it already comes with version 2.2 on Anaconda, so let's take this and okay, let's paste it here. So conda install that. It's gonna verify everything. So now it asks us to allow it to install all of these packages here, and you can see that we have TensorFlow and TensorFlow GPU here, version 2.2. And let's click yes, or choose yes and click enter, and let's wait for it to install all those packages. It might take some time here. Some packages are of big size, for example TensorFlow. So just be patient, and once this installation is finished, I'll be back. So after a few minutes, and once all the packages have been installed, now we can see that it has finished here, and we can test our installation here. So let me just clear the terminal, and then I'm gonna run a Python console here and import TensorFlow. Let's just see what we get here. And what I would like to verify is, one, whether TensorFlow is installed correctly, and it is. And the second thing I want to verify is whether we are actually using, or we will be using TensorFlow for GPU. So in order to do that, there is a command from TensorFlow. So let me just Google it here. So TensorFlow lists devices. And let me just get here, and here, I'm just gonna copy this. So Control C, Control V, and then I want to list the devices. Control C, Control V. So here, now we have all the available devices for training, and if everything is installed correctly so that TensorFlow can use GPU, you can verify this in the devices available here. So if you see GPU such as this one here, so as you can see, XLA GPU, GPU 0, this means that the version of TensorFlow that is installed on your virtual environment will actually use the GPU on your machine. If you only see devices listed as CPU, this means that you haven't configured correctly your GPU, maybe you didn't install the drivers correctly, or that you just don't have a GPU that you can use for training. Maybe you have a different GPU than NVIDIA GPUs. So for us, we see that everything is installed correctly on our virtual environment, and since we can see that we have GPU listed as a device here, this means that we can use it for training, and we will be using it for training. And now we will install Object Detection API for TensorFlow 2. So this is a tool created by the TensorFlow team, so from Google, and it helps us to train our deep learning models easily, specifically SSD and Faster RCNN, which they are mentioned in this course. So for that, we will just follow the guide shown here. So one of the main things to realize that there are two different types of installations. You can either build a Docker image by using these commands here, or you can create a Python package installation basically. So what you would have is almost like a module for object detection installed on your system or inside your virtual environment. So for us, we will take the second approach here. And for that, we will start first of all by cloning the repository. So let me go here. Okay, we don't need this anymore. So Control D. Okay, let me clear this. And in fact, maybe I will create it in I'm gonna put it here. So for this, I'm gonna call this, or I'm gonna open it in a new terminal, and I'm gonna clone it here. So let's run this. Okay, I actually don't have Git installed here, so usually I use it from within a virtual environment, but here I don't have it, so I'm just going to install it. And let me get my password here. Should be installed quickly, hopefully. And once this is installed, we're gonna clone it, and it's going to be in the same folder where we have the labeling tool that we used before. So I'm gonna create it, or I'm gonna add it to this folder here. So let's just wait for this to finish downloading. Okay, it's almost there. Okay, so let me clear this, paste it again. Oh no, sorry. I want to clone this, so let's clone it here. And now we should have it inside this folder here. So, okay, it's gonna take a bit of time here because it is more or less a big API. So once the download is finished, I'll be back to show you the rest of the steps. So now that we have the repository cloned and is downloaded to this folder called models, what I'll be doing is moving this folder to a new folder that I created called Tensorflow 2 Object Detection API. So I'm gonna put it inside, and now I have the necessary files inside this folder here, which is inside the Tensorflow 2 Object Detection API folder. So now what we're gonna do is continue with the rest of the steps here, and we will be doing this from our virtual environment that we created using Conda. So here, if you remember, TF2 GPU is our Conda environment, and let me just cd into my folder. CD TensorFlow models. And in fact here, I need to be inside the research folder. So I'm gonna cd to research as well. Let me clear this. And let's finish the installation process by running these commands here. So protoc, it's only these last two. So let me take this and paste it here. So basically here we're gonna copy the setup.py file from TF2 to the current directory, which is research. So let's run this command, and finally we will run this last command here. But in fact, I faced problems while trying to use this command here because of this tag that was added. So this tag, I actually did not use it when I was using the TensorFlow Object Detection API for TensorFlow 1. But for TensorFlow 2, they added it, but in fact, it caused some problems during the installation. So I decided to not use it, and I know that it doesn't really affect the part that we will be doing, which is training the models for object detection. So if you run just this command, python -am pip install dot or pip install setup.py, it's going to install the object detection API. So let's run this. So this could take some time for the installation process, and I'm going to be back once it's finished. So now that the installation has finished, let's run a simple test that's shown here by running this command. So let me copy this and paste it, and let's see if the test is okay or not. So if the test is not okay, we're going to see that gives us an error at the end, but if everything is okay, then we should get no errors here. And once this test is passed successfully, then we can actually get to the point where we can train our deep learning models using TensorFlow 2 Object Detection API. So let's wait a little bit. So now it has finished the test here and everything seems to be okay. And now our object detection API is ready to be used so that we can train deep learning models for detecting objects on images. In order for us to train deep learning models for object detection, we first need to prepare our dataset as the first step in our training pipeline. So for SSD and Faster RCNN deep learning models, we will be using what is called TensorFlow 2 Object Detection API. So this is a tool provided by Google from the TensorFlow team, which allows us to train multiple deep learning models, and it allows us to configure things very easily, and we don't have to go at the low level of TensorFlow to understand how we train a deep learning model for object detection. So there was a first version called TensorFlow Object Detection API, but there is a new version for TensorFlow 2. So if you don't know, in fact, the TensorFlow 2 is very different than TensorFlow 1, where they have used Keras API to develop all the models or most of the models. And with the new API, they redefined these new models, and now they have a version that's specifically made for TensorFlow 2. So let's take a look at how our data preparation will be like. So first, we will have a data set comprised of images, and I will show you where to get this data set. And what are we going to do is that we're gonna annotate this data set, and when we annotate it, we actually get different or multiple XML files that represent annotations. So each image in our dataset will have one XML file corresponding to it that has the annotations corresponding to that image. If you don't know what annotation is, you will learn this very soon. But for now, just think of them as information that we add besides our images when we are training our deep learning model, so that it can learn how to detect the position or the localization of objects in an image. So once we do the annotation using a tool that I will show you later, we're gonna get a set of XML files that correspond to the images that we had in the beginning. After that, what we're gonna do is transform those XML files into one CSV file. So this one CSV file will comprise of all the annotations that exist in all the XML files. So at this step here, we will have the images as we had from the beginning, but now instead of having multiple XML files, we will have one CSV file that contains all the necessary information for the annotation part. And once we reach this step here, we will use a tool to transform this data into this CF records format, which is a format that is known in TensorFlow that helps accelerate the learning, because the format that this file will have is a binary format, which is very efficient in terms of reading and writing, and that's gonna help the training speed to be much better. So for each step, we will introduce a certain tool that will help us to do that, and in the next videos I will be showing you how to get those tools, how to install them, and we will go through these steps one by one. In this new lecture of the course, we will look at how to download the dataset that we will be using to train an object detection model. So for this, I have chosen a dataset that is very fitting to our current time, the pandemic time, where we have many people wearing masks. So the dataset will contain images that have people either wearing masks, like these two and this one here, and other people who are not wearing masks, such as this one here. And the goal of our object detection model will be to be able to identify people's faces or heads on images and tell us whether they are wearing masks or not. So for this, I am downloading a dataset that exists on the RoboFlow website. I will be sharing the link with you that is linked to this lecture, and you can just go to the link and download the dataset. I believe you have to subscribe to the website and to enter your email address. So apart from this, you shouldn't have any problems. And downloading the dataset should be for free. So in this dataset, they have 149 images, and in each image you have people who are wearing masks and other people who aren't wearing masks. So for me, I am downloading the raw dataset here. This one is a dataset of padded images. So let's take a look. Maybe we can see some images here. So they are loading. As you can see, this dataset, the padded dataset, actually has some padding, so some black will look here in the size of the image, and we will not be using this for our object detection model. We will be actually using the raw dataset here. So when you click the raw dataset here, you will get to this, or you will go to this part of the web page, and here we will download a specific version of the dataset. So as you can see here, there's the Coco JSON, Create ML JSON. There are all these types of the dataset, and for us, we will be downloading the TensorFlow Object Detection CSV dataset. And we will be downloading this because we will be using TensorFlow Object Detection API. So we will need a dataset that is appropriate for that tool. And in fact, you can even download this TensorFlow TF record, which is the final form of the dataset that the models will read during the training. But for our purposes, for learning purposes, we will be downloading this dataset here, and I will show you why in a bit. So if you click this here, it's gonna tell you to choose, okay, the format. We have already chosen this. Download zip to computer or show download code. We will just click on download zip to computer, click continue, and here, if you're not logged in, it's gonna ask you to log in, so you can sign in, and just after this, you will be able to download the dataset. So for me, I will not be doing this. I already have dataset downloaded. So let me just check here. So here, if you download the dataset, it will be zipped, and when you unzip it, you will get a folder such as this one. And when you go inside this folder, you will have all of these folders and these two text files here. So if we open the training folder, for example, what you're going to notice is that they have a bunch of images. Let's open one, for example. And here you can see that it's an image of people wearing masks, such as all of these ones. And some people are not wearing masks, such as these three ladies here. And apart from the images, you should have a file here, a CSV file that contains the annotations. So if we open this file to take a look at it, let's open it in LibreOffice. If you have Excel, you can open it on Excel. And when you open the file, you'll see that what you have is a table that contains the annotations of the data set. So what you would have here, for example, is this image here. This file name corresponds to the image name in the data set, so in this folder. And then what you have is the width and height of the image. Then you will have the class. So for this specific image, you can see that there are 5 different annotations. What this means is that we have 5 different people in this specific image, and all of them are wearing masks. And here what we have are the coordinates of those people's faces or people's heads that are wearing masks. And in fact, what we have here is the pre-annotated data set. So usually when you are trying to build a deep learning model, you in fact don't have all these annotations. This is something that you need to do yourself, and I will be showing you how to do this. For now, we will keep this annotations file in here, and we will be using it a bit later, but I will be showing you the steps to do in order to get this annotations.csv file when you don't have it. Because usually when you want to build an object detection model, you just start with a bunch of images such as this one here, and what you would need to do is to annotate them by yourself, or you hire someone to do that for you. And what the annotation process is basically to go through the images and choose or annotate it by selecting the head or the object that you want to annotate. So in our case, it would be the head. So we would be putting a rectangle here and assigning a class to that rectangle. So for this specific image, this lady here is wearing a mask. So we will be adding the class mask to our annotation. All of this will be much clearer when we do this by ourselves in a future video. But this is what I wanted to show you. So here for this specific data set, we already have the annotations, which is going to help us a lot. And for me, what I would like to show you is how to annotate the data set, show you some examples, and later we will actually use these annotations. We will not annotate all the images because it will take a long time, and it's really not a learning experience. So for me, I want to show you the tools to annotate the data set, but then we will come back to our data set and our annotations, and we will use them as they are in here. And one other note about the data set. So as you can see, it's split to 3 folders. There's a training folder, there's a validation folder, and there is a testing folder. So usually in deep learning projects or machine learning projects in general, what you have is a certain split of the data set where you have a folder that contains data that will be used during training. And what you would have also is either one other folder or 2 folders. So here we have 2. So we can use this validation folder to validate our model during the training as well. And once the training is done, we can test our model on this test dataset in here. So apart from this, this is exactly what we will be using for our training, and see you in the next video where I'll be showing you more about the annotation process. As I have mentioned before, even though we have our dataset annotated, we actually will do some annotations ourselves just to see how the whole annotation process works. So for that, we'll be using this tool called label image, and what it basically allows us is to do what is shown in this image here, where we can go through the parts or the objects that we want to detect. We can assign a bounding box around the object, and what we do after that is assign a class to that object. So as you can see here, we are annotating these 3 persons here, and we're choosing the class person for each one of them. And to download or to have access to this tool, what you would need is to follow these steps here mentioned. So there are steps for Ubuntu, Linux, for Python 2 and Python 3. There's also there are also steps for Mac OS, and finally for Windows. So for my case, I am using Ubuntu, so for that I'll be using this specific guide here, but I will be changing some things. I will tell you later why I changed some of these things, specifically this second line here. So the first thing that you need to do is to clone the code. So we're just gonna download a zip of the code, and here I'm just gonna put it in. I have already done this before, but we will do it again together. So here I already have, as you can see, a folder called label image, but for us, let's download it to this folder here, and let's go here and unzip the folder. So extract here, let me delete this, and for this I'm just gonna change this to copy, so label image copy, just so that I can distinguish it from my original folder here. And here what I will be doing is let me open a new terminal window, and here I'm gonna cd to this, so just to avoid copying the whole or cding to each folder one by one here, I just drag this this file here and then change the folder. So let me clear this. So what I have now is the same thing as I have in this folder here, and let's go back to the guide and see what we should do next. So for us, we are using Ubuntu Linux Python 3, which is the recommended way. And here the first thing you need to do is installing these PyQt5 DevTools. So let me copy this, and here let's paste it. In fact, you don't need to cd to this folder in order to run this command, but I'm just doing this so that I know that I am in the right folder later when I'm trying, well, when I will reach this fourth or fifth steps here. And for this, let me just run this. Let me enter my password, and as you can see, I already have this installed. So it's already the newest version. Okay, I have already this installed on my system, so no need to install it again. And when we come to the second step here, when I ran this command here, I actually faced a problem, and when I went to the issues here, I actually found someone who faced the same problem as me. So I have this same problem here. So installation issue when trying to run the command that I just shown you, and I have the exact same errors here. So for that, I think the problem is coming from the versions that are mentioned in the requirements.txt file here. So as you can see, there are specific versions of PyQt5 and LXML. So for me, what I have done to solve this problem, which is what I have mentioned here in this issue, this is actually my account. So in order to fix it, I just installed PyQt5 and LXML using pip and without specifying the specific version. And to do this, actually, I don't want to install these things on my system. So what I usually do is create a virtual environment and install everything necessary to run this Python script inside that virtual environment. So for this, I am using virtual env. So it's a tool that allows you to create virtual environments very easily. As you can see, when I type virtual env, it shows me all the different commands that I can use. For you, maybe it won't be installed. So if it's not installed, it will give you a command on how to install it. And you can just run that command. So it should be something like sudo apt install virtual env or something similar, but it's gonna actually give you that command if you don't have virtual env installed on your system. So let me clear this first. And to create a new virtual environment, what we need to do is to run virtual env, and we need to give a name to our virtual environment. And you should know that when you create a virtual environment using virtual env, that environment will be in some sort of a folder that contains all the necessary things to allow you to run those scripts in the virtual environment, and that folder would be actually created inside this folder here. So let me just first do an ls here. As you can see, we don't have any virtual environment. I haven't created anything. Let me run the command here. So virtual env, I'm gonna call it venv. And when I run this, now I should have a new folder called venv, as you can see is shown here. So inside this venv, I have all the necessary things for my virtual environment to be run. And in order for me to activate my environment, I need to run source and basically run a script that exists in venv bin, and it's called activate. So when I do this, as you can see now, I have this name of my virtual environment at the start of my command line here. So let me just clear this, and now let's start installing the necessary things to run our virtual or our script here. So let's go back and just see, okay, we need to install things that are in the requirements, and I have, as I said before, I faced some problems, and in order to solve them, I actually installed PyQt5 and pip and LXML using pip. So let me go back here just so that I can enter to the requirements.txt and just take these names of the packages. So let me Control-C this, and I'm gonna run pip install PyQt5 and also LXML. And let's run this and see what we get. So here is collecting everything, and it's should install all the necessary packages. And I'll be back when, oh, okay, it's already installed in fact. So it installed PyQt5 and also installed the LXML. Let me just verify here. Install XML. Yeah, the requirement is already satisfied. So now that we have these two Python packages installed, let's go back to the steps here and look at the next command. So here we need to run this command. And in order to run this command, in fact, you now need to be inside the folder that contains those files. So here we are inside our folder that contains all the necessary things here, and here we're gonna run make qt5. So the command was run successfully, and now we can actually run python label image.py. So here, just to mention a quick thing here, as you can see, they ran Python 3. I am only using Python because I only have Python 3 installed on my system. So when I run Python, let me run it alone. You can see that I have 3.8 installed. If I had two versions of Python installed on my system, if I had Python 2 and Python 3, then in that case I would need to use 3 here in order to tell my system that I want to use Python 3 for doing this command. But for me, I only have Python 3, so just using Python label image.py should be enough. And when we run this command, we get access to our labeling tool here. And as you can see, it's exactly as we've seen in that image on the GitHub repository. And here you can do so many things, like for example, you can open one image here, or you can open a directory here, and we'll look more into this in the next video. So again, in this interface here, you can see all of these buttons here that we will be using. So this one for opening an image, opening directory, going back and forth between images, and this is for creating a rectangle, duplicating it, deleting it, so on and so forth. So let's just start by opening a directory, and for this I'm gonna go to the dataset that I downloaded. So it's this one, mask wearing v4 row TensorFlow, and for me I have changed the name here. Before, these underscores, actually instead of them we had some dots, and I removed them. This is to me much more clear when trying to read the folder. And here, if we go and we choose this folder, if you click open, you get a list of all of your images here. And with this, you can actually go and annotate the dataset by choosing, for example, create a rectangle. And when you have a rectangle here, you can enter the name of your class. So for us, maybe we'll write mask. And as you can see, there are already some predefined classes in here. And these are coming from the folder that, let me just check here, or the file called maybe classes, maybe data. Yeah, predefined classes. So this folder actually contains these predefined classes. You can remove them from here and keep it empty in order to avoid having them whenever you're trying to annotate a new object here. So this is just an example, but for us, we will not be annotating all the data set as I have mentioned before. So what I'm going to do here is that I will go to my data, I believe it was here. So I'm going to go to the data set again. I'm going to go to this folder, training folder. I will just take a few images and put them in a separate folder. I'm just going to copy them. I will not remove them. So after I do this, okay, maybe it's stuck because of this one. Let me just stop it for now. So Control C, or just stop it from here. Okay, I hope that's not freezed. Okay. So now let's go back, enter. What I will be doing is taking maybe just 5 images. Let me check if they don't contain many people here. Okay, this is just for to show you how you can annotate the data. So we're not gonna take this image. As you can see, there's a lot of people in this image. What you would usually do is go back, go through each person here and annotate it and tell whether this person is wearing a mask or not. So we're not gonna use this image for the testing purposes. We'll use this, maybe this as well, this and this. Okay, let's just take these ones here. So I'm just gonna copy them, going back here. I'm gonna create a new folder. I'll call it, for example, dummy. Go inside, paste these images here. I'm gonna go back to my terminal here, clear it, run the app again. I will open a directory. For this, I'm gonna go back to the data set here, mask, and go to the dummy folder. So here I only have 4 images, and we will go through them and annotate them quickly here. So in order to annotate the image, what you need to do, okay, I think actually I haven't removed these yet, so let me stop this and remove these classes before we move on to the annotation part. So here, let me go back to data tools, here label image copy, and inside data predefined classes. I'm gonna remove this, save it, go back here, run the command again, open the directory, choosing that dummy directory, and okay, we have the 4 images. So for annotating, I'm gonna click on create rectangle here, or rect box, and I will just basically click, then drag here my mouse in order to get the whole head. And now, since this specific person is wearing a mask, I'm gonna call this mask. And for the baby, I won't be annotating it because we don't see the whole face of the baby here. So we're just gonna annotate this person here. The other people, we can't see them clearly, so we're not gonna annotate that as well. And here you can just click on save, and it's gonna show you that's gonna save it to the same folder. And let's click save here, and let's just see what we actually get. As you can see here, we actually get an XML file that has the same name as the image. The only difference is the extension. So if I open this, I'm not sure if I have a good way to open this. Okay, I'm just gonna open it in Chrome. And what you see here is that in that XML file, we have the file name, we have the path to the file name, we have, okay, we don't have a name for the database, that's okay. Then we have the width and height and the depth, which represents the dimensions of the image. So the depth is the number of channels, RGB, red, green, blue. And then what we have is the bounding box coordinates and the name of the class that corresponds to that object. So as you remember, we chose mask, and here we have the coordinates of the pixels that represent the bounding box. So if we go back to our tool, so the two xmin, ymin values represent the value of this pixel here, and xmax, ymax represent the values of this pixel here. And let's go back. So this is how you get an annotation for specific image. And let me just go back and go to the next image. So you click here, next image. Let's annotate this again. And there are actually some shortcuts that you can use from your keyboard instead of every time going to clicking on this button here. For example, for creating a rect box, you can just click on W. So if I click on W, I get the same thing, and now I can annotate this. So this is wearing a mask, and this person is wearing a mask. And now, since this person is not wearing a mask, I'm gonna write no mask. And the same thing for this person. So click W again. This, no mask. Okay. So now I have the four annotations. And let's say I made a mistake for this face or this face. I can just go here, click it. I can remove it. For example, it's going to be removed from my annotations, and I can annotate it again. So here, let me just click here, and it's no mask. So okay. So now that I have this this image finished with the annotation part, I can also save it using Control S. So I don't have to go to this button here each time. So I'm just clicking Control S and I will get the same thing. So I'm gonna save it. And if I go to my folder, I see again that for this image I have a corresponding annotation file, an XML file. And if I open it, here is the same thing. We have an image, the path to that image, the size of that image. And here, as you can see, we have 4 different annotations. So there are 2 of them with mask and 2 of them with no mask. And each time we have the coordinates of the points representing the bounding box. And again, X-min, Y-min represents the values of this pixel or this pixel, and the X-max, Y-max represent the coordinates of this pixel or this pixel or this one. So this is how you annotate the data set, and you can go to the rest of the images and do the same thing. So here, let's do this. And as you can see, the 2 classes will be saved here so that you don't have to write them every time. You only do it once and it's saved. And here, let me annotate the rest of them. Control S to save it. Save. Go to the next image. W. Annotate this again. So this person is wearing a mask. The same thing for this person here. And this one. And this one here again. And we have these 2 people here that their faces are more clear than the rest of the faces. For example, this one and this one are behind. We can't see them very well, so we're not going to annotate them. So Control S again, save, go back, and we now have the whole data set. Let's say for this dummy data set, we have it annotated, and we have an XML file corresponding to each image. So now that we have this, we actually need to transform our data set in such a way that is appropriate for the tool that we will be using for training an object detection model. In fact, we can't use these XML files as an input to our pipeline. We need to transform them into what is called TF records. So it's a specific format that TensorFlow accepts when training an object detection model using Object Detection API. And we will look at how to do this in the next videos. So previously we had annotated our dataset or our images, and we got those XML files, and now we will transform those XML files into one CSV file that contains or combines all the annotations from all the XML files. So for this, we will be using a script from an open source repository. So I will be linking this this link here to the lecture. And what I have done is that I took this file or this script here and I have pasted it. And now what I will be using is this specific function here, XML, sorry, generate CSV file. So what I have done actually is that I made some minor changes. So here, as you can see, there's the main function XML to CSV, and then they basically run it on the training set and the validation set. And what they do is just they create these functions with the different paths to training and validation, and then they run these two functions one after the other. So for me, what I have done is that I created one function that can take the path to the images and the path to the output CSV file. So this will be generated, and at the end of the function, once the function is executed, we will have a new CSV file that combines all the annotations from the XML files. So I will be maybe linking only this XML to CSV Python file or Python script, and just to let you know that I have actually taken it from this repository here. So if you want to go to the source and check it, then you can go to this link in here. So let's go back to the script. So basically what we are doing is that we are going through all the XML files in our path, and after that we are constructing a tree. So a tree is just a representation of the elements in XML file. So if we go to okay, it's not here. Let me try to find one XML file. So this one, for example. And if I open it, what you're going to see is that XML files are basically represented in some sort of a hierarchy. So you have this annotation here, which represents basically the biggest element. This is very similar to HTML files if you have worked with HTML. And so you have annotation inside the annotation, you have folder, you have file name, you have path, and then you have source. Then inside the source you have database, then you have size. Inside the size you have width, height, depth. So you can imagine some sort of a tree that represents these data in a manner that's easily accessible by programs and while coding them in Python. So this is the only thing we're doing. So we're creating a tree, we're getting the root of that tree, and then we're going through the root and trying to find specific elements in that tree. So there's object, there's file name, there is size, and what we are doing is creating this tuple here that contains all of these elements, and then we are appending them to a list, and then this is where we write the CSV file. Basically what we do is first we create a row that contains the titles of each column here. So we have file name, width, height, class, xmin, so on and so forth. And then what we do is that we take that XML list and we basically create a data frame, and in that data frame we choose the column name and we choose our list, and we get a data frame here. And in the CSV file, what we basically do is that we first use that previous function which takes the path to the images and gives us a data frame. And then what we do is that we transform this data frame to CSV, and we give it a path where the CSV file will be written. So at the end, if we just use this function generate CSV file, so it's going to take the path to the images, path to CSV file, and it's just going to write our final CSV file to this path here that I have defined. So now if I go back just to verify things before I run this script, so let me go back to this part here where I have the data set, and it's here. I'm not sure if I changed the path again, so let me just maybe take one image. Take one image here, and now what I would like to do is to take this part of the path here, so until here. So I'm gonna copy it just to make sure that I am using the right path, and then let me just take this again and paste it. Okay, so it's basically the same thing, and what I have created here is the dummy.csv. You can call it whatever you like, maybe annotations.csv is more representative of the file. So now that we have this, let me just clear this. Now that we have this, we need to run our script basically. Let me just save this. So in order for us to run the script, again, this script will have some dependencies, as you can see here, glob, OS, pandas. I'm not sure if they are installed on my system, but you can either install it or install the dependencies on your system, or you can create a virtual environment that you can use to install all these dependencies, or you can actually just use the virtual environment that we have created before for the annotation tool here, label image. So I don't need the annotation tool anymore, so I'm gonna close it. Let me clear this. I'm gonna cd to my XML to CSV file, so it's in media. Okay, let me check this. I'm gonna do media, data, tools, and I think I'm calling XML to CSV. So let me clear this. Let's ls this just to verify. So we have the virtual environment and we have XML to CSV file. So I'm just gonna write Python XML to CSV. So the goal here is that we go from these 4 XML files and we generate a new CSV file, and it should be written inside this folder. So for this, let me go back here. Let me run it. If we get this kind of errors where we don't have the dependencies, we can just install them again using the same manner. So pip install pandas. So it's going to be installed quickly here. And usually that's how I do things. Sometimes if I run a script and I don't know if I have all the dependencies or not, I just run it a few times, and each time is going to tell me if something is missing. So now basically the only thing that was missing is the pandas Python package. So let's go back here and verify. So as you can see, we have our new annotations file written here. It's only one file. And if we open it, let me open it in LibreOffice, and let me go here. Okay. And as you can see, our final CSV file has the same format as the first annotation file that I have shown you, that came with the dataset when we downloaded it. So here, as you can see, we have 1, 2, 3, 4, so 4 different images, because these ones represent the same image. This one represents one image, this one again, and these ones are all corresponding to the same image. The only thing that's changing is the annotations inside that image. So this image here has 6 annotations, so 6 bounding boxes. This one only has 1. This one has 4, and this one has 1. So as you can see, now we basically combined all the images or all the XML files, sorry, into one CSV file that has all the necessary information for the annotation part. So let's just go back and verify something here. So the dummy dataset is here. Let's open maybe the big training set annotations file. So let's go here, open it, and as you can see, it's the same format. We have file name, width, height, class, and okay, let's go here. No, I don't need this anymore. So annotation.csv. So file name, width, height, class, width, height, class, xmin to ymax. So as you can see, this is how you get to this specific phase of preparing your dataset. So as you remember, I have shown you before, when we downloaded the dataset, we had these files already included in the dataset, but now you know how they got this CSV file here. So we started with the dummy dataset just to go quickly and to see how they went from images to images plus CSV file. And now that we have this, we can actually go back to the step here. We will be using the original dataset from now on. So these three folders, we will be using them from now on. And we will be using these CSV files instead of that dummy CSV file. So the whole point of this dummy folder here is just to show you how they basically came to that specific step where they had images and a CSV file that contains annotations. Another important thing that we need when we are creating our dataset or when we are trying to create the final TF records is what is called label map. So a label map is basically a file that looks like this, where we define different items. Each item will represent one class or one type of objects in our images. So as you remember, in our annotations, we labeled the faces with either mask or no mask. So we basically have two classes in our dataset. What this means is that we need to create a file, a label map that assigns IDs into each name that we have given to our classes. So for us, we gave the first class the name mask and the second class the name no mask, which means that we need to have two different IDs, one ID for mask and one ID for no mask. So here, let me just copy this from this open source repository here. You can look at the URL here. I just basically typed label map and I went to the first repository that I saw, and I took this part here. And what I'll be doing is that I'll be pasting this into a new file here. I'm gonna paste it here. So the ID one, I'm gonna give it to mask, and ID 2, I'm gonna give it no mask. So just before we save this, let's go to our dataset and verify in our annotations. Well, let's just go here. So in our annotations, as you can see, we have class mask and class no mask. And in fact, I have made a mistake here. So as you can see, when they labeled their images, the original dataset that we downloaded, they actually wrote no dash mask instead of underscore. So for me, I have to change this as well. So this should not be an underscore, this should be a dash. And now I have the label map, corresponding to the dataset that we have. And the label map is the same for all of our folders here. So we have the test train and validation, they all have the same name when it comes to the classes, so mask or no mask. So now that we have this, let me just save this. So Control S, I'm gonna save it inside this folder. I'm gonna call it label, sorry, let me remove this. So label map.pbtxt. So I am using this extension here because that's the convention that's used by TensorFlow Object Detection API. So I'll be keeping it the same. So this file extension will be used for our label map. So let me save this. Let's go here, and as you can see, it's right here, the file. And now what I will be doing is that I'll be using a new tool or a new Python script that goes from the label map, the CSV files, the images, and all combines them into one TF records that we will use later for training. So the tool that we will be using to transform our data set into TF records format is basically a script called generate TF records. And this script, I took it from this repository. In fact, this repository belongs to a friend of mine called Abdurrahman Gabir. And we basically studied together at some point, and we also worked together at some point. So he created this very useful script that we can use in order to generate the TF records. So TF records, again, is a format that TensorFlow Object Detection API basically accepts, and it's easy to train our models using this format here. So what I have done is that I took this script here and I have pasted it to a new script on my local machine, and now it's actually very easy to use this TF records or this generate TF records file in order to transform our data set. And again, in order to run this script, as you can see, it has many dependencies, including TensorFlow and PIL and others. So for this to work, we actually need to have some tools installed in a virtual environment. And since these are the tools that we will be using for training the object detection models, we will create a separate environment or virtual environment to run this specific tool, and also later to run the training and the evaluation. In fact, instead of creating a new virtual environment, we will just use the virtual environment that we created before when we installed TensorFlow GPU and also Object Detection API. So for that, I just opened my script here, and I opened the terminal window inside VS Code, and I'll be doing I'll be activating the virtual environment here, and I'll be running the script from here just so that I can see all the arguments that are mentioned here. So for that, I'm gonna run conda activate. So our environment is called TF2 GPU, and now as you can see, it's activated. Let me clear this, and what we should do now is run our script here, because I am already inside the folder that contains that script. And this script takes 4 different arguments here. So the first argument is the path to images. So I'm gonna do path to images. And for that, what I will be doing is just dragging and dropping the folder's paths here. So let's start with the train folder here. So I'm just gonna drop it here, train, and now I need the path to to annotation. So the second argument here is the path to the CSV file. So for that, let me go here, open this, look for the annotations, and now I have the path to my CSV. And again, just to reiterate, we are no longer using the dummy folder here where we created the annotations. This was for demonstration purposes, just to show you how you annotate your dataset and you get to the point where you have the annotation.csv file. But now we actually are using the real data that we downloaded and that's already annotated for us. So that's why we're using the path to this folder and also the path to this CSV file. And the fourth argument is path to label map. So as you remember, we have we have our label map that we created in here. So I'm just gonna drag this and drop it here. And finally, we need the path to save the TF records. So this path is for saving the TF records, and for that I want to save them in the same folder here. So inside this folder, just so that I can keep things in order. So now we should have all the arguments necessary to run the script. And let me just run this and see what we get. Okay, we actually have a problem here. Let me check. Yeah, in fact, the problem is that for the final arguments here, so path to save TF records, it actually needs to point to a specific file that we want to create that has the extension record here. So for that, I'm just gonna do train.record so that it's saved, and let's see what we get now. So now it's generating the TF record. It should successfully have created the TF record file, and now we can see it here. So this file here actually contains all the images and the annotations, and it has put them in a binary format that is easily to read by the model during the training. So what we're gonna do next is to do the same thing for test folder and validation folder, so that we get 3 different TF records that we can use for training or testing or validation. So I'll be doing this quickly now. So let's clear this. Let's just create or just go through the arguments again. So for this, I'm gonna go to validation. So this is for to save the TF records. The label map should stay the same. The annotations, let's check this. So validation, path to annotation should be that. And finally, we have the path to images. This also should be validation. So let me just check the name of the folder again so that I don't make a mistake. In fact, it should be valid. Sorry about this. It should be valid. And okay, the name of the CSV file is the same. So valid. And here again, valid. The label map should stay the same, and the rest here it should be valid. So let me run this, and it should have created it. So let's check. Okay, we have it here. And finally, we will do the same thing for our test folder here. So everything that's valid should change to test here. So the test folder for the TF records, the label map again should stay the same. Annotations, this one should be test. And finally, the path to the image here should go or should point to test. And let's run this again. Let's check our folder, and now we have the TF record for the testing folder as well. So now we have all the data put in the right formats that we need for training and also for testing and validation. And the only thing that is left now is to configure our training, choosing our model, and then running the training. So we will look at this in a future video. And now we will look at the steps needed to build an object detector using TensorFlow 2 Object Detection API. So in order for us to train and evaluate a object detection model for whatever task that we want to do, we have to follow these steps. So first we need to choose a neural network architecture. So this could be SSD, Faster RCNN, or others. Then we need to download a pre-trained neural network corresponding to our choice in step 1. So if we choose SSD, then we will go and download a pre-trained neural network, so pre-trained SSD network from a specific place that I will show you. After that, we will download, or we will look for the configuration file corresponding to our pre-trained neural network in step 2. So if we choose SSD, we download the pre-trained model and also a configuration file. And after that, we will configure our training using the configuration file. So this configuration file will have multiple parameters that we need in order to create our training job, you can call it. For example, we need to specify the path to training data. We need to specify the number of classes that we have in our dataset, and many other parameters as well. So in the configuration file, we will be doing this. And finally, we will run the training and evaluation using the scripts that are part of the TensorFlow 2 Object Detection API. And for this also, I'll be showing you which scripts to run and also which parameters to pass to the scripts so that we can run the training and evaluation. And now let's talk about transfer learning, because we will be using it for our object detection task. So what do we mean by transfer learning? So usually what we have is a neural network such as this one. This is the SSD neural network, and it has these layers, and the process is to give it some images at the beginning, and we want to predict the classes or the objects that are in that image. So we want to know what kind of objects are those, and also where they exist in the image or where they are localized inside the image. And if you have a large data set, when I say large, it's in the order of hundreds of thousands and ideally millions of images. In that case, you can start from the neural network architecture and you go from scratch and you train it from zero, let's call it like that, which means that you only define the layers. They will be initialized randomly, and then during the training they will learn to extract the necessary information so that they can make predictions, good predictions at the end. But for most of the cases in the industrial context, we don't really have that type of large data sets. We usually have very small data sets, such as the one that we have, so it's less than 200 images. So even actually if you have maybe a data set in the orders of tens of thousands of images, it is still relatively small compared to the very large data sets that are used or that are publicly known in the deep learning field that researchers use to train these kind of neural networks. So for our case, what we will be doing is that we will start from a pre-trained neural network, hence the reason why we will be downloading a pre-trained neural network, as I shown you before, or as I have mentioned before in the steps for training an object detection model. And when we do this, we actually have two different options in the TensorFlow 2 Object Detection API. So the first option is to only start from the pre-trained part, the pre-trained network of the classification part. So these will be initialized randomly, but this part here will be initialized from using the weights that were used when this neural network was trained for some classification task. And the second option is to actually start by using pre-trained neural network for all the layers. So all the layers will be initialized using some weights that were basically learned when the neural network was trained on a large data set. So these are two different options, and for our case we will start from we will choose the option where all the layers have been initialized, and that's because we have a small data set. In fact, if you have a data set in the orders of tens of thousands of images, in that case, maybe it's better if you only use the pre-trained part of the classification layers and keep these initialized randomly, and then you train everything using your data set. But for our case, since we have a very small data set, we will keep the pre-trained layers, we will keep all of them, and we will start from them as our initial state. So remember this, because at the point where we will fill our configuration file, we will have this choice to either start from the classification layers as pre-trained or all the layers as pre-trained. So usually they're called detection layers as pre-trained. So we will be looking at this option in the configuration file when we are preparing our file for training. And just remember this. Remember these two options, and remember why we will be doing option 2 instead of option 1. In this video, I'll be showing you how to structure your folders and prepare your data for the training. So for this, there are several steps, and the first step would be to create a bunch of folders where things will be stored in them, training artifacts and other things as well. So what I usually like to do is to create some sort of a folder like this one here. So I called it object detection, and inside of that folder I will be adding several experiments. Let's call them like this. And an experiment basically represents a certain setup that I use for training. So for example, one experiment could be by using Faster RCNN neural network. Another experiment could be using SSD based neural network. So I like to structure my folders like this, and I start by creating an experiment. So here we have experiment 1, and when you go inside that folder, you will have two folders there. The first one is called data, and the second one is called training process. And what these folders represent is, so for the training process, it's an empty folder where all the training artifacts will be saved. So by training artifacts, I mean two things. The first thing are the trained models. So during the training, at certain timestamps, a model or a checkpoint will be saved to this folder. And the second thing is what's called events. So these events basically are files that store what's happening during the training. So it's storing values of accuracy, of loss functions, and so on and so forth. And we will be using those events files in order to see what's happening during the training. And to do this, we'll be using a tool called TensorBoard. That comes later. So going back, so this folder is for saving the training artifacts. And this folder here will contain all the necessary data and files in order to run the training. So the way I like to structure it is as follows. One folder, I call it train. And inside this folder, I'll be storing the training data, so the TF records that are used for trainings. So let's just do this right now quickly. So if we go to train and we look for our TF records here, so we have this one. So let me copy it and let me go here and paste it. So this is for the training. And just something that I want to mention here, since we don't have a lot of data, I believe that maybe it's better to use as much data as we can for training and use the rest for testing. So for that, what I have decided to do is to basically take the validation data and use it for training as well. And we will use the evaluation data for testing. And this is again a decision that I made based on the number of images that we have. I don't think it's a good idea to split them into 3 different parts when we don't really have that much data anyway. So let me copy this and I'll paste it here as well. And let me just change the names. So I'm going to call this, for example, train 2, and this one will be train 1. And these will be both files will be used for the training. And the second folder that we have is the testing folder. So this folder will contain the data for testing. So for this, I'm gonna go back here and go to the test folder. So again, sometimes I say evaluation, sometimes I say testing, but they mean the same thing. So here, testing, I'm gonna copy this and come here. I will paste it here. And this will be all the images and annotations stored in this .record file will be used for testing. And the last folder that I have here is the folder that will contain my pre-trained model. So the pre-trained model is the model that I'll be downloading that will be useful as a starting point for our training. And for this, to get this pre-trained model, I'll be attaching this link to this video here. And this link basically points to the model zoo. So object or TensorFlow 2 detection model zoo. So this table here contains checkpoints or pre-trained models for many different architectures, as you can see. And for example, if you take SSD or Faster RCNN, there are many different backbones. For each backbone, you have a different checkpoint. So for us, for this specific video, I'll be choosing Faster RCNN with ResNet 50 v1 as my architecture, as my starting point. So for that, I'm just gonna click here and it should give me the link to download, and I should just save it. For me, I have already downloaded it here, so it's in my downloaded it's in my downloads files. Sorry. So here I'm just gonna go to my folder here. I'm gonna open this in a new window. I'm gonna take this, I'm gonna copy it, I'll paste it here, and then I will extract it here. So let me just extract it here, extract here. And once it's finished extracting, I will delete this zipped folder or zipped file here. So the last thing that we will add to our data folder is the label map. So the label map is what we created before. So just to see it again, it just contains this map. Basically, it maps an ID to the name of the class that we have. So 1 will point to mask and 2 will point to no mask. Oh, let me close this. And now what we need is one last piece of data that we will use for training, which is what I have mentioned before. It's called the config file. So for the config file, you can just go to the cloned repository or the downloaded repository for object detection, if you remember. So it was when you downloaded it, you should have had this folder called models. So inside models, research, and then object detection. Let's go to object detection. And here inside configs, TF2, you will have a list of all the config files that are available, and that these config files correspond to this model zoo here. So if you come here and you go to the training, sorry, not the training process, the data pre-trained model, here you should look for a config file that has the same name as this one. So for this, I'm just going to copy the name here. So Control C, and I'll come here and I will just look for it. So Control F, Control V, and this is the config file that I need for the training. So I'm going to copy this and I will put it here. And now I have everything necessary to run my training. The next step will be about changing the parameters inside this config file, and we will be doing this in the next video. And now let's make the necessary changes to our config file in order to allow the training to be run and to define all the necessary parameters that training and the evaluation will need. So for that, I'm going to open my config file using some text editor. And here, as you can see, the config file is divided into multiple sections. So there is the section about the model configuration. So here we see some parameters regarding the model. For example, the number of classes, the input size here. So the size of the images at the training time and testing time. We also have some other parameters for the model here. We also have here another section about the training config. So for the training config, we have the batch size, we have the number of steps, we have the path to the pre-trained model, the one that we downloaded. So those checkpoints, we need to point to them here. And also we have a train input reader here. So this is the part where we will define the paths to our TF records. So our data set basically, and also the path to the label map will be defined here. We have an eval config section here where we can define some configuration for the evaluation or for the testing part. So for example, we can change the batch size here or the metric set. And finally, we have an evaluation input reader or a testing input reader. And this is the part where we will define again the path to the label map because it's needed here, and also the path to our .record files. So basically the path to the dataset or to the part of the dataset that will be used for testing. So as you can see, there are lots of parameters here to change, but there are mainly some parameters that you will have to change each time you starting from this specific setup of the config file. So we just copied this from the folder inside our object detection API. So there are some parameters that you most likely will be changing them each time. And there are other parameters that you don't really need to change them. You can have your training and evaluation without changing them, but they can improve the results in some cases. So these parameters are basically a second degree. They're not the main parameters. So these second degree parameters, we will talk about them a little later. But for now, we will speak about the main parameters that you need to change. So the first parameter will be the number of classes. So here, because this was the pre-trained neural network that we downloaded was trained on Coco 17 dataset. In that dataset, they have 90 classes. In our case, we don't have 90 classes. We only have 2. So we have the objects with mask and the objects with no mask. So only 2 different types of objects or only 2 classes. So this will be changed to 2. The other thing that we need to change is the batch size. So for the batch size during training, it's better to have a large batch size, but since we are running the training on our local machine, and specifically for my local machine, I only have a GPU that has 4 gigabytes of memory, so it won't handle this number of images at the same time. For that, I'm gonna change it to 2. And the number of steps here, so each step basically represents one batch of data. So if in the batch we have 2 images each time, this means that in each step we will pass 2 images at the same time. So here, for the testing purposes, just so that we can see the training running, I'm going to change this to only 200. I just want to show you some things. And when you are happy with the configuration that you have defined here, in that case, you can increase the size of the number of steps, and then you can run the training to get your final best object detection model. Another thing that I want to change, or I will need to change in fact, is the fine-tune checkpoints. So this path here will be the path to where our pre-trained model is on the local machine that we have. So for this, I'm gonna go to my pre-trained model path. So it should be in data, pre-trained model, then faster here, then checkpoint, and it's this one, checkpoint 0. So for that, I'm just gonna open this in a terminal just so that I can get the full path here. I'm gonna copy this and I'm gonna paste it here. So here, and it should be checkpoint CKPT-0. So this is the starting checkpoint that we will need to define. So here I have defined the path to that checkpoint. And here, as you can see, we have fine-tune checkpoint type. You have the option of choosing either classification or detection. And this is based on the slide that I have shown you before. When we have a neural network, we either keep the parameters for the classification part only, or we keep the parameters for the whole network, so all the layers. And that's what we want to do in our case. And for that, we're going to change this to detection. So we want to start from a neural network that has all the parameters initialized using the pre-trained neural network defined here. So this, we're going to start from detection. And let's go down a little further. So here, we need to define the path to our label map. So just to verify here, the label map is inside data. So for that, let me just copy it from here. It should be in here. Let me copy this and I'll paste it here. And just to avoid any mistakes, I'm just gonna copy the whole name from here. So Control C and Control V. And in fact, the path to the label map, we're gonna need it for the training part and the testing parts. That's why I'm gonna copy it and paste it here. And the other thing that we need to change are the paths to our dataset for training. So here, for the training part, I'm gonna change this. Let me just go back and check the path here. So basically, until we get to data, then we go to train. So here, I'm gonna do the same thing basically. I'm gonna paste it. So until we get to data, then train. Let me just verify data, train. Now we are at the folder that contains our training records. But since we have two different files here, what we should do is do something like the following. So when we write this notation here, so star.record, it means that I want this path here to include all the files that have an extension of .record. So that's why I'm adding this. And finally, for the evaluation part or the testing part, I'm gonna copy the same thing, except that I will change the path. So let me copy this and I'm gonna paste it here, and I will change this to test. So let me just go back and verify. So I have data, I have test, and in fact I can just write test.record, but this doesn't hurt since we have only one file that has the extension .record. It will be chosen as the file for the evaluation part. So with these parameters defined, I believe we don't need to change anything, for at least for now. So these are the main parameters that you will usually change whenever you get a new config file. And for the other parameters, most of them you most likely won't be touching, but some specific parameters you might want to change them from time to time when you are trying to get the best accuracy possible from your model, and maybe we'll look at those a little later. But for now, these are the main parameters that we need to define. And with this config file finished, let's try to run a training and the evaluation and see whether everything is working correctly or not. In order to run the training and the evaluation, we will follow the guide here shown on the GitHub repository for the object detection API. And basically what I have done is just copy these commands here and put them in a file that I can always come back to without going to the repository. And for that, we need to define a few parameters to pass to the script that will do the training. So here, as you can see, the main script that does the training is called model main tf2.py. And this model or this script will take 3 parameters. So there is the pipeline config path. So this is the path to our config file. This is also another parameter called model dir. So the model dir is the path to where everything that comes from the training will be stored. So the checkpoints and also the events that store the accuracy or the development of the loss and the accuracy of the model. And this last parameter here is just to log everything that's happening in the training to our folder that we defined in model dir. So the first thing that we need to do is define these parameters here. So we're gonna choose the path to the config path, choose the path to the model dir, and then we will run this command directly because it will take these parameters that we defined here as an input. So pipeline config path will be here, model dir will be defined as well. So for that, let me just copy this. And in fact, what I want to do is I'm going to open 2 different terminals, and I have activated my environment, my Conda environment that has TF2 GPU installed and object detection API installed. So I have 2 terminals here, and I will define the paths in both terminals. One terminal I'll be using it for training and the other one for testing. So let me just define here, there's the pipeline config path, and that should be in, let me go back here. This should be here. So this is the config file that we just defined. So I'm gonna put this here, and the same command, I will run it in my second terminal as well. And again, what we need to define here is the model dir. So I'm going to take this and I'm gonna paste it here. So the model dir will be the path to where everything will be stored. So this should be our training process here. Everything that comes from the training will be stored in here. So I'm gonna put this here as my model dir, and I'm gonna run the same command in my second terminal here. And let's look at the command here. So the command that we need to run now is this command, where we will run the script model main tf2.py, and we're gonna give it the parameters that we just defined as an input here. So for that, let me copy this. Copy. And one thing that you should do is you should make sure that you are inside models research directory in order to run this command. So for that, let's come back here and see. Okay, we're already inside models research. If you're not, then you have to come to this specific path here so that the script can be run and everything will go smoothly. So for that, let me just paste this here, and this should be for the training. So I'm gonna run this, and you should know that for the starting, it takes some time to start, and also for the logs, it only shows us the logs after each 100 steps. So I'll show you that a little bit later. So these are just some logs that come from the API and from Tensorflow. You don't need to look at them for now. They don't tell you a lot. It's just some information about preparation of training. So these are not, don't worry about them. If you see warnings, it's very okay. There's no problem with this. And okay, it's almost started, just to make sure. Okay, and for the evaluation part, what we will be doing is running the second command here. And for the second command here, we will run the same script. As you can see, model main tf2.py. We're gonna give it the pipeline config path just like before, the model dir just like before, and the other parameter that we need to define so that we tell the script that we want to run testing and not training is this parameter here. So this is called checkpoint dir. So what this represents is the directory where the checkpoints will be saved. If you give this as an input, then this script will realize that you want to do testing and not training. And what it's going to do is just wait for some checkpoints to be saved in this model dir folder, and then it will read them using this checkpoint directory in order to run the evaluation. So just to reiterate, for the script model main tf2.py, if you only give it these three parameters here, so we're not going to speak about this last parameter, it's just for logging, but we're going to speak about these two. If you give it only the pipeline config path and the model dir, then it's going to know that it's for training purposes, so it will run the training. If you give it this third path here, which represents the path to where the checkpoints have been saved, so in our case, for example, they will be saved in the same folder defined here. So the same model dir can be chosen for checkpoint dir. So if we choose, or if we add this parameter here, then this script will realize that we want to do evaluation or we want to do testing, and it won't run the training. It will just wait for checkpoints to be saved and then use them to test on the data that we defined in the eval input reader here. So it's going to use this data here in order to do the testing part. So let me just go back to the terminals. So here, in fact, if you see this then the training has started, and it's gonna take some time just to finish the first 100 steps. Once the first 100 steps are done, then you will see a log here that tells you that it was done, and it's gonna go through the second part of that 200 steps, so the second 100 step. And now if you see this this log until this point here, that means that your training has started without any problems. If it stops, then there probably is some problem, some error, and you can just read the logs in order to understand what was wrong. But for now, if you get to this phase here, that means that your training is working properly. So now let's go to the evaluation part, and let's define the final parameter that we need to use for the evaluation part or for the testing part. As you can see, I keep saying evaluation or testing. They mean the same thing, so just keep this in mind. And different researchers or different engineers might call it one or the other, so they mean the same thing, and don't worry about this because basically they both mean that we are going to use that data for inference only, and we're going to look at the accuracy only, and we're not going to train the model using that data. So let me just copy this here, and what I will do is here I'm going to change or I'm going to choose the path where my checkpoints will be saved. So again, if we go here and we go to training process, as you can see, these are the models that were just generated by the training process. So this is the folder where everything will be saved for the training. And if we go to train folder here, this is a folder that was generated by the detection API, and it saves the events. So basically the history of the training part, so the development of the loss values, and also the average precision during the training process. So here I'm going to choose the same folder, so training process, because I want to read the checkpoints from the same folder here. That's what it means. And we have two different parameters, because you can think of a way where you have maybe you have your checkpoints, you have moved them somewhere else. In that case, you can actually just point this checkpoint directory to wherever you have put your checkpoints. And you might be asking, why do we need the model directory anyway? So actually the model directory here will help, basically will help us save the evaluation events when we are doing evaluation. So the same way here, as you can see, we have the events for the training are being saved here. When we run the evaluation, we're gonna have a new folder here called eval, and the events for the evaluation part will be saved inside the eval folder. So that's why we need to define this model dir here as well. So let me just run this, and now let's run our script here. So copy, and again make sure that you are inside the folder models research, and let me paste this. I'm gonna run it, and now it's gonna take maybe some time to set everything correctly, and maybe now it will only do evaluation using the checkpoint that's already saved. So the checkpoint here is gonna use it for testing, and then it's gonna stop, or it's gonna pause basically and wait for a new checkpoint to be saved. And when a new checkpoint is saved, at that point this script will take that new checkpoint and use the same data in order to run the evaluation again. So let's just wait a little bit. And of course, it can take some time for the training and the evaluation. So be prepared for this, especially if you have a machine that is not very powerful, such as the one that I am using. So here it's still setting things up. And of course, I'll be showing you maybe, if it doesn't take a long time, I'll be showing you what happens here for the evaluation. And if it takes too long, then I may pause the video and come back to it later when things are moving a little bit quickly. So here it's still moving. Okay. There should be some logs after this that tells us that it has done the evaluation part. So let's wait a little bit here. So after a few seconds, and maybe around a minute, I had these logs here where you can see average precision, you can see detection boxes, so on and so forth. And what these represents is the logs coming from the evaluation part. So if you see this, that means that the evaluation is running correctly. And once it finishes this part, in fact, it's going to stop, or it's going to pause and wait for a new checkpoint to be saved. And this new checkpoint will be saved after the training part here. So after this script reaches, or this terminal reaches a certain step where everything will be saved again. So what's going to happen is that we're going to have a new checkpoint here called CKPT2. And once it's created, then the evaluation part here will take that new checkpoint and run the evaluation again. And as you can see, a new folder was created called eval. And inside of it, as you can see, we have events. And these events represent the development of the evaluation part. And this was created because we defined the model there the same as in the training part here. So maybe let's just wait a little bit and see. So just now, in fact, I had this new log, and this is what I was mentioning before. As you can see, the evaluation part is basically paused here, and it says waiting for new checkpoint at this path here. So once we get a new checkpoint from the training part, then the evaluation will start again using that new checkpoint. So I just wanted to mention this, and the training is still running now. So once it reaches a certain level where new checkpoints are created, then I'll be back and we'll see what happens then. So now, after 200 steps, the training has stopped, as we can see in here. And basically for each step, it took 5 seconds. That's why it was a little long. And we can see just from these two values here, we see that the loss is continuing to go down. So that's good. And the other thing that I want to show you here is that, as you remember, we were at this stage here. So waiting for new checkpoint at this path here, and sorry, it should be this one. So here, once a second checkpoint was saved, so once we finished the 100 steps, the first ones, a second checkpoint was saved. So it was here, these two, and once they were saved, a new, you can say an event, or this event has triggered the evaluation script so that it started again. So as you can see from here, waiting for new checkpoints, then it says found a new checkpoint at this path here. So once the new checkpoint was saved, the evaluation started again, and as we can see, the same thing as before. We have the detection and everything for the testing parts is shown here. And again, it's waiting for new checkpoint. So if for example, we run the training again and it goes for longer times, then this evaluation script will continue to wait for those new checkpoints, and each time a new checkpoint is generated, it's gonna use it for the testing or for the evaluation. So now, after that the training has finished, well, basically finished on the 200 steps that we defined, because it's not finished in terms of finished the whole training and the model is ready for production or for inference. No, this is just for the experimentation purposes. We chose 200 steps, so they are finished. And now what we can do is analyze the development of the loss function and see how the precision also, or the mean average precision, has developed for the evaluation part as well. So for that, what I will do is use a tool called TensorBoard. So TensorBoard, this is a tool that comes with TensorFlow, and it basically helps us analyze all the history of the training and even the graph that represents the neural network. So for doing this, what we need to do is run TensorBoard and give it a parameter called logdir, and logdir is the path to where the events are saved. So for example, for the training part, we can pass this. So TensorBoard -- logdir, and then the path to the training folder, and let's run this and see what we get. So here it gives us the results in this in the browser, and we can access that page by going here. So I'm clicking on Control and then clicking this with my mouse, sorry. And here we can see the development of the loss function here. So this is one of the loss functions. So for Faster RCNN, there are several loss functions based on the different stages. As you know, there are 2 stages in Faster RCNN. So, for example, we have the classification loss and the localization loss for the final network, or the mini network. And the region proposal network, if you remember, is the network that comes before the last one, and it comes right after the backbone part. So for this, we can see this is the development of the loss, and what we usually look for is that the loss should be going down overall. So that should be our the aim of our training. So if the loss is going down, then that's good. If it's not going down, then that's bad. And also, it should go down smoothly. So when we look at these plots here, we realize that the loss overall is going down, but it's doing so many fluctuations here, as you can see. And also there's this weird thing here, but actually this comes from the fact that I stopped the training here by myself, then I ran it again. So what happened is that it went back to basically to the initial value of the loss, and then it started converging again. That's why from here to here, so this left part here, there are actually 2 different plots. They are superimposed one over the other, and that's because I stopped the training and I ran it again. But of course, this is just for experimentation purposes. On this side here, it's more clear. We can see that, okay, the loss is developing in this sense and it's going down overall. But even with this, even if we ignore the fact that I stopped the training and started again, we realize, or we can see that the fluctuations are too much here. And one reason for this to be the case is that we are using a very small batch size. So when we are doing this, basically the gradient is moving slowly, and it's not taking good steps. It's not looking at the, sorry, not the steps. It's not looking at the at a big chunk of the data set every time it makes a step. So it's only looking at a small variation of the data, so only 2 images each time. So when it's making the move downhill, because when I say downhill, this is what the gradient is trying to do, where the gradient descent algorithm is trying to do. So we're trying to move downward in some sort of a hyperparametered function, and the thing is that when we are only looking at a very small subset of the data set every time, so 2 images every time, we're not making the right decision when trying to go downhill. But if we increase the batch size, this will probably be much smoother. And of course, I can't use high values of the batch size because of the limitations of my machine. So this is something that you should consider when you are developing your object detection model. If you don't have good machine, then the training could be something like this, and the end model will not be that good if the training is like this. So as you can see, the same basically is in all the different loss values here, or the loss functions here. I mean, overall, for example, for the localization loss, we see that it's going down, which is good. And again, this is where I stopped the training, so it went back to the initial value. The same thing here and here. But overall, we still see that the loss function is going down, so that's a good sign. But apart from this, we can't really say that this is a good training. And again, there are many reasons for this. Mainly the batch size that we are using is very small, and it should be increased. If I see, if I'm doing this in my job and I see this kind of plot here for my loss function, the first thing that I would try is the batch size, to increase it and see if it becomes smoother or not. So this was for the training part. And now, if we look at the evaluation part, so let me just stop this and go to eval. So eval, because here I'm trying to access these events here. And if I open this, then I don't get a lot of information for the average precision here, because we didn't run the training for that long. But if we go to the images part here, what we can see is a side-by-side comparison. So the left side is what the neural network that we are training is trying to predict or has predicted, and on the right is the ground truth. So as you can see, the network is still far from good, because as you can see here, it should have detected this as the mask, and it says it's no mask, and it's not even being close to the shape of the face here. So the same thing could be seen for the other images as well. So here we have, this is the ground truth on the left, so this is an image here, and this is the image where the network has predicted the bounding boxes, and again, the results are very bad. But this is something that is understood. We did not run the training for a long time, and we don't have a large batch size, and this was the first trial, so I'm not surprised that we got these results. So the goal is to have at the end a good model that's able to detect the people that are wearing masks and the people who are not wearing masks. And so far the model is still not capable of doing that. So we'll look and we'll see how to improve this in the next videos. So in this video, we will be talking about the different things that you can do in order to improve the training on your machine. So for me, as I have mentioned before, I don't have a very good machine for training large neural networks such as this one, Faster RCNN with ResNet 50. And let me just check, for example, my NVIDIA settings here. So this is my GPU. So as you can see, mine is GeForce GTX 1050 Ti, and it has 4 gigabytes of memory. And even with this, I cannot go beyond the number 2 for batch size. In fact, I can maybe choose 3, but usually it's better to choose a power of 2. So either 2, 4, 8, 16, so on and so forth, because the way that the GPUs are made, it helps a lot if you actually have a power of 2 as a batch size. It's much more efficient for parallelization, but that doesn't stop you. You can actually try 3, you can try 5, just that usually it's not recommended. So for me, since I am stuck with 2 and I cannot go beyond this, and we have seen the final training, and at least for the 200 steps, we've seen how it went. So I have decided not to do the training on my machine because I know from my experience that the final model will not perform very well. But for you, if you have a good machine, then of course the first thing that you should do, based on what we have seen in the previous videos about how the training went, you can just start by changing the batch size and making it a high value. Maybe you can start with 8. If you have a really good machine, you can even try 16 or 32 or even higher. So for me, I will leave it at 2 here, and I will not be doing the training on my local machine. In fact, what I will be showing you a bit later is how to leverage the power of Google Cloud Platform in order to run the training on some of the powerful machines on Google Cloud Platform. And that will allow us to increase the batch size and get better results. So this is my recommendation for you. If you have really good machine, then the first thing you should try is to change the batch size to a higher value here. And also, you can increase you should increase the number of steps. So let me just look for, number of steps here. You can increase it to 2000, for example, at least, to see how it went or how the training goes in these 2000 steps. For me, I will stop here as I have mentioned, but the exact same setup you can use on your machine, and you can get or you can train a deep learning model for object detection on your local machine. You just need to know that if you don't have a good machine, then the final model will not be that good. In fact, even with the settings that we have defined here, we can train a deep learning model and we can use it at the end. It's just that the results will not be good enough, especially for production. If you are working in the industry and you're trying to develop a good deep learning model for your task, then having a good enough machine for training your model is very necessary. For training SSD-based models, we can do the same thing as Faster RCNN model or any other model in the model zoo here. And for that, let's create a new experiment. So let me just create a new folder here called experiment 2, for example. And just a quick note here before I forget. In my job, what I usually do when I run multiple experiments on some local machine, I usually add a new a new text file here that just gives a summary of the different setups that I have here. For example, I would say that this is a model trained on Faster RCNN. The dataset is organized this way, and any other relevant information, because usually when you are in the industry and when you run multiple experiments, sometimes you forget what's the difference between two different experiments. And for that, one thing that you can do is just add a text file to each experiment, and you define or you describe your experiment in that text file. For me, I will not be doing this here because we probably won't be running many experiments. But for you, if you're doing this in your day job, or if you're running this, or if you're doing so many tests and experiments, then this could be a good habit for you. So now what I would like to do is maybe just get the data from here again. So for this specific example, I am copying the data into my new experiment, but I'm doing this only because the dataset is not that big. But if you have a big dataset, then a better option would be to keep it somewhere, you can say centralized, where you can access it. For example, you can add a folder here called data, and you add the data to it, and then from within the experiments you point to that folder, which is a much better approach than the one we are using here. But for our experimentation purposes, and because the dataset is not that big, we will just copy it and paste it here. So again, in the train folder we have train records. In the test folder we have a test record. And in the pre-trained model, we have this pre-trained model from Faster RCNN. But since we want to train a SSD-based model, I will be deleting this. So this folder should be empty now. And apart from that, the label map should stay the same. Nothing needs to be changed in this label map. So let's go back here, pre-trained model, and now let's make a choice about the SSD model that we want to use. So as you can see here in the model zoo, we have several SSD based models, and there is what changes is the backbone. So here we have MobileNet V2, V1, V2 with this image resolution and using FPN Lite, SSD with the ResNet 50, so on and so forth, with different image resolutions. So for me, what I will be doing specifically is download this one just to keep the same backbone, the same image resolution. We will just change the different, we'll just change the model from Faster RCNN to SSD. So just the main architecture, let's call it like that. So for this, I will be downloading this, and I'm just gonna keep it in the downloads here. So I'm gonna save it and let it start. Okay. Now let me just say keep. It should be downloaded now. And apart from this, let me go here and go to downloads, and it should be downloaded here. So while waiting for this, let me just talk again about this this part here. So as we can see, there are several models here, and this famous one, MobileNet, is made specifically for models that you want to deploy or you would want to deploy on mobile phones. So these backbones are made or are created in an efficient manner. So the architecture is very, it's tiny and effective. So when you train a deep learning model with this backbone, so MobileNet, then you can deploy it on your mobile phone, and it wouldn't take that much space, and it would be more efficient than the rest of the models here. For example, Faster RCNN would be huge. It would need a lot of memory, so it would not be a good choice if you want to deploy your model on mobile phones. So let's go back here, and I believe it was here. Okay, I actually saved it here. So I'm gonna take this from here and paste it here, and here I want to extract it, so extract here. Now that it's extracted, when we go inside we see the same thing as before. So here we have checkpoint, we have saved model. It's exactly the same, you can say the hierarchy, but now we have a Faster RCNN or SSD ResNet 50 model. So let me just delete this compressed file. And yeah, so now we have the same setup for the experiment. And maybe one thing we can do is just let me check here. So in experiment 1 we have data. What we need now are the 2 config files, and we need an empty folder for saving the training process. So let me just go back, create a new folder, training process. This is where we will be saving the files or the artifacts of the training. And what we need now is to find the corresponding config file. So the corresponding config file to the network that we downloaded. So we downloaded the pre-trained model SSD ResNet 50 V1 FPN 640 by 640. So we will look for the corresponding config file in our local repository that we downloaded. So in order to get that config file, where we need to go is to the path where we have config files. So if you downloaded your repository again, so object detection, if you go to models, research, object detection, then configs, then TF2, here we will look for the same or for the config file that corresponds to the SSD ResNet 50 V1 FPN 640 by 640. So let me just maybe do SSD, and here let's look at ResNet. So this one is ResNet V1 FPN, and maybe just do this. Oh no, sorry, data pre-trained model. In fact, let me just copy this, Control C, so that I don't make a mistake here, and just paste it here. Yeah, so this is the one that we need, so I'm gonna copy it from here. So Control C, pre-trained model, data, experiment, it should be here. So now we have the same setup as before, where we have folder that contains our data. We have a config file that contains the configurations that we need to modify, and that corresponds to the same pre-trained model that we downloaded, which is here. So we have the same hierarchy, and in the next video I'll show you how to change the configurations in the config file before you run your training. And now let's change the configurations in our config file. So let me just open this one here. And again, we have to go through the main parameters that we need to change, and the rest are mainly optional. So we're not gonna go through everything here, just the things that must be changed. For example, the number of classes. So again, we have two classes. And what else we need to set here? Let me check. So here, okay, we need the path to fine-tune the checkpoint. So this path here, it should point to where our pre-trained model is. So let me maybe just move this here. It's gonna be almost the same path as in Faster RCNN. So I'm gonna copy this and okay, here it should be experiment 2, and of course this needs to be changed. So let me just check here. It should be inside data and pre-trained model, and this is it here, and inside checkpoint in fact. So if I open this in a terminal, maybe we can actually just copy it from here. So copy and paste, and inside the checkpoint we have CKPT0 is our checkpoint. So this is the path to the checkpoint that we will use as a starting point for training. So this is a pre-trained neural network. Apart from that, we're going to change the batch size here as well. So again, since I don't have a good machine for training, I'm just going to use 2 as a batch size. And let's go down and check. Well, we also need to set the label map path here. So the label map, actually maybe we can just get it from here. Oh, it's not here. There's a pre-trained model. This is where the label map is. So it's in data. I'm gonna copy this, paste it, and should be label map.pbtxt. And the same thing for the evaluation config. So I'm gonna copy this and paste it here. So this is the label map path for the evaluation config. And the last important or the last necessary thing to change are the paths here. So the path for the training data and the path for evaluation data. So it should be inside the folder data. So here train, let's check maybe this. It should be in data, then train. So maybe we can keep this on top here just so that we can see this. So this train, and inside train, everything that has an extension of dot record will be taken into consideration. So again, when we use this notation here, what we are saying is that take everything inside that folder that has the extension dot record. So then we can go down here and copy this, copy or remove this. So Control V, data, and this should be eval, and again the same thing as the training part. So let me just go back here. Oh, sorry, this should be actually test and not eval. So this is test. We can either write test.record since we have only one file, but I'm going to keep it like this. It's okay. So now that we have finished these main parameters, these are the necessary ones that you have to change. And of course, we're going to change maybe a few things depending on your machine and depending on your setup. So maybe the number of steps, where's that? It should be here. Yeah, number of steps. So since we don't have a lot of data, maybe 2,000 steps should be enough. So this this number 2,000 should be enough if you have if you're going to train on your machine or on the cloud. It doesn't matter. And since we are again experimenting, I'm just gonna set this to maybe 200. And now what we need to do is to basically run the training. Let me just check a few things. Okay, the label map should be the same. Pre-trained model. We have the SSD model here. We have our config file. We've changed it. Training process is empty. So this should be okay. So now that we have finished setting up the main parameters in our config file, the next thing we're going to do is run the training with this setup and see if everything is working correctly or not. In order to run the training, we're going to be doing the same thing as before. So the first thing I have done is activating my Conda environment here. So as you can see, I have TF2 GPU in the beginning, which means that I am using my Conda environment here. And the other thing that we need to do is define some local environments here, or local variables that we're going to use to run these commands here. So the first thing is, I'm just going to copy this. And okay, it didn't copy. Why is it not copying? Okay, I'm just going to write it. Yes, I think there was a problem there. So this is the path to the config file. So for this, I'm gonna go to here and I'm just gonna drag and drop this. So this is the path to my config file. And the other thing is the model dir. So model dir will be equal to this path here. So this is where the training artifacts will be saved. And let me just clear this, and we're gonna run the same command as before. And as it says here, we need to be inside models research, which we are. So here, I'm just gonna copy this and paste it here. And let's see if the training runs correctly or not. So now it's successfully opened dynamic library libcudart.so.10.1. So here I actually forgot to mention one thing that we need to change, which is fine-tune checkpoint type. So this was classification and I changed it to detection, just like before, just like in Faster RCNN. So after I changed this, I ran the training again, and as you can see, the training is running correctly, and I noticed that it was faster than Faster RCNN, because now with SSD, the network is much simpler than Faster RCNN, which makes the training faster, and also the prediction part or the inference time should be faster as well. So now that we have everything set up, we now know that we know what we need to change, we know what we need to set up in order to run the training locally, both for Faster RCNN and SSD. And as you can see, it has finished since we have set up only 200 steps, but now we have all the necessary ingredients in order to run the training on our local machine. So again, I will not be doing the training to get the final best model on my local machine. I don't have a good GPU on my machine, and for that reason, I will be using Google Cloud Platform, specifically AI Platform Service from Google Cloud Platform. I will be using that to train my deep learning models, and I will be showing you how to do this in the next section of the course. What I would like to show you now is some of the parameters that can affect your training and that could improve your results if you know how to handle them. So the point here is to show you some very specific parameters. We're not going to go through all the parameters here. And for that, let me just maybe go back to the Faster RCNN config file. And okay, let me just remove this here. And let's start from the beginning, and let's look at firstly the grid anchor generator. So the grid anchor generator is the parameter that is responsible for generating anchor boxes. As I have mentioned before, the anchor boxes are boxes that we start by defining in the beginning, and then throughout the training, what the neural network is trying to do is to make these anchor boxes converge to our ground truth boxes. So since we have our own data set and we have annotated it and we know the different types of objects that we want to detect, this knowledge can help us maybe choose better scales and aspect ratios. So for scales and aspect ratios, these are parts of the grid anchor generator. So all of these are parameters that you can change. And maybe let's start with these two first here, because they're easier to understand. So the height stride and the width stride basically represent the centers of the anchor boxes that we are generating. So as you remember, I told you that if you have an image and you have this, inside this image you have many pixels, so you can choose to define an anchor box in the first pixel of the image, and the next anchor box you can choose to define it in the next cell, or on the second next cell, or in the 16th next cell as it's here. So this means that if we use these two parameters, height stride 16, width stride 16, this means that I would start with the first pixel of the image and I would define some anchor boxes in that pixel. Then I would go 16 pixels to the right and define another set of anchor boxes, and then 16 pixels more. So this is 32 pixels from the start. So I defined a new set of anchor boxes, and then this is from the height perspective, from the width perspective, sorry. And from the height perspective, we would go from the first pixel to the 16th pixel in the down direction. Then from that to another 16 pixel, define another set of anchor boxes, so on and so forth. So if, for example, imagine you have an image, which is just, of course, an imaginary setting, but imagine you have an image of 16 by 16 pixels, then in this case, if you use these two parameters, you're gonna define a set of anchor boxes in the first pixel, then in the last pixel in the first row, and then in the last pixel of the first column, and then the last pixel of the image. So you would have 4 different centers or 4 different positions where you're gonna set a bunch of anchor boxes in those positions. So this is for these two parameters, height stride and width stride. The other parameters that are important are the scales and aspect ratios. So for the scales, what they represent is basically you can think of it as a multiplier. So you multiply this value here with a certain base size. So the base size is a size that is chosen before, which is a size of, let's say, the first anchor box that you ever define. And then what happens is that we're gonna multiply these values with the size of that anchor box, and then we will have a new anchor boxes. So if I am not mistaken, while looking at the documentation, the base, width and height of the base anchor box is 256 by 256. So it's as if our first anchor box ever is a box that has the size 256 by 256. And then what we are saying here in the scales is that we want to have 4 different boxes. So the first box will be a 1/4 the size of the base anchor box. So if we have 256 by 256, if we divide it by 4, that becomes 64 by 64 anchor box. So this is one anchor box. Another anchor box will be half the size of the base anchor box. So again, 256 by 256. If you divide that by 2, it becomes 128 by 128. So that would be your second anchor box. This one will be the exact same thing as the base anchor box. So 256 by 256. And this fourth one here will be twice the size, so 512 by 512. So these are the values that you would multiply by the base anchor box so that you would get new anchor boxes. So as I have said, from my reading from the documentation, the base anchor box should have a size 256 by 256. So our scales, the ones that we're going to use, are these 4 here. So we're going to have 4 different sizes or 4 different scales of the anchor box. So 1/4 of the anchor box, 1/2 the same size, and twice the size. And last, we have the aspect ratios. So the aspect ratios are basically defined as the width by the height. So the width of the anchor box divided by the height of the anchor box. So what this means is that you would have for example, here we have 4 different anchor boxes, right? So we're gonna take, for example, the first anchor box, and then we would set 3 different anchor boxes based on this size here. So what we would have is that, okay, let's take a concrete example with concrete values. So as we said, the base anchor box would be 256 by 256. The 1/4 of it would be 64 by 64. So what we're gonna do is, with these aspect ratios, we're gonna create one anchor box that has the width of that anchor box 1/2 the size of the height of the anchor box. So it would be, for example, 64 by 128. So this would be one possible anchor box here. And then we would keep the same size. So the width over the height will be the same. So that means we're gonna keep 64 by 64 as a type of an anchor box. So this would be a squared anchor box. And then in this case here, we would have the width twice the value of the height. So for example, we would have the width 64 and the height would be 32. So as you can see, when you define these scales and these aspect ratios, then you are defining the set of possible anchor boxes that you're going to use during the training. So if we go back to our example where we are training a model to detect faces of people that have masks and faces of people that have no mask. In this case, maybe one possible change that we can do is maybe remove the aspect ratios that are 0.5 and this is 2.0. Maybe we can just keep 1.0, and the reason for this is that maybe the face is almost always a square, so it's closer to 1, and you almost never find a face that has the width 1/2 the size of the height, or the width double the size of the height. So these two values here wouldn't make much sense in our case. So maybe one good thing would be to remove both of them, and this means that we would have less anchor boxes. So this would be faster training, and also at inference time this would be also better. So I am trying to give you a guideline on how to choose these specific scales and aspect ratios. And with our example, I hope that you understand what these values are and how they would affect your deep learning model and how you would choose them based on your specific use case. And another important parameter in the config file is the data augmentation part. So let me just look for this. So augmentation. So both the examples for Faster RCNN and SSD. So let me look for augmentation here again. As we can see, both of them define these or this parameter called data augmentation options. So here we have it defined here. So data augmentation options, we only have this. And if we go to SSD, we see that we have these two. So data augmentation options, we define this, then another one, data augmentation options, where we define this. So data augmentation, as you may know, is a powerful tool that basically helps us generate new data from our collected data set. So if we take this example here, what we do is basically take the images that we have collected as an input, and then we just randomly flip them horizontally. So you have one image, you flip it horizontally, then you have another image. So just like that, you can have double size of your data set. And again, there is here another parameter called random crop image, where basically we remove crops from the image. And this would also help the learning part, because we basically cover some parts of the image and we tell the network to predict the right values or the right output for these images. So this would help the image generalize well. So what I would like to show you here is the possibility to add more data augmentation options. So for example, if you go to preprocess.proto, so this is in the let me just look for it. It should be inside our data or our object detection API. So if you go to models, research, object detection, protos, if you search for preprocessor.proto, so this is what I am having here opened. So all of these options are data augmentation options that you can use in your training. So if we go here, for example, and let me just copy this, and we're gonna look for it inside preprocessor.proto. So as you can see, it's defined here. And again, if we take, let's say, random crop image, if we come back here, maybe, yeah, you can see here, it's here, random crop image. So all of these are possible data augmentation techniques that you can use in your training. And in order to do that, as you can see here, we have this parameter, data augmentation options. We open our brackets, then we add the name of the data augmentation technique inside of it. And if this data augmentation technique needs some parameters, we would define them inside these brackets here. For random horizontal flipping, we don't need any parameters because we're just flipping the image. But for example, random crop image, then maybe we would need min object covered, we would need some aspect ratio, some min area, max area, things like that. So these parameters would be defined inside. So if you want to add a new data augmentation option, what you need to do is to go to this preprocessor proto, where you can look up the different options that you have here. And when you want to know which parameters you need to pass, unfortunately there is no documentation per se to see this. So what you need to do is to look it up in the code. So for example, if we take this and if we go to this page here where we have preprocessor builder tests. So actually maybe we can even find this here. Let me just look it up. It should be in our it should be downloaded here as well. So builders and preprocessor builder tests. If we take this, maybe we can open it here as well. And let me just move it here. Yeah, so if you go to preprocessor builder test, here you can look at the different parameters that you need to pass for that data augmentation option that you chose. So here, let's again go and maybe look up random adjust saturation. So Control C, I'm gonna come here, Control F, Control V. And as you can see here, you have these two parameters to define for random adjust saturation. So saturation is an image processing technique. You can look it up to see what it does. And basically it changes the saturation. So you basically, if I'm not mistaken, you multiply the pixel values by these two parameters or by a certain parameter to get a different saturation. And here, since it's randomly adjusting the saturation, you can choose the min delta and the max delta so that during the training we randomly generate a number between these two and we use that number in order to adjust saturation. So if you want to use this, let's say in your data augmentation, what you would do is again data augmentation options, and you would open the brackets, you would close them, and inside you would write the type of data augmentation that you want to use, close the bracket again, and then here you would take those parameters, so min delta and max delta. Let's just copy them. Let's suppose that we're going to use these two values here. So you would add them here. So just like this, now you have a new data augmentation option that you can use during training. And again, you can add as many as you like here, as long as they are already defined in the preprocessor proto here. So with this, now you know how to look up these options and you know how to find the right parameters corresponding to those options. And with this, I think now you have, you should have a good knowledge about how to use these very important settings in your configuration file. So there is the data augmentation part, and then there is the anchor boxes part. And I hope that this is clear, and see you in the next video. Hello and welcome to this new section of the course where we will be exploring how to leverage the power of cloud computing, specifically using Google Cloud Platform in order to train our deep learning model. And we will be using the service called AI Platform for this specific task. So if you go to Wikipedia, the definition that you will find there is that cloud computing is the on-demand availability of computer system resources, especially data storage and computing power, without direct active management by the user. So what they mean by this is that you have access to these machines, and these machines have available resources that you can use for storage and also for computing power. For me, when I think of cloud computing, I think of it as remote Linux machines that have almost the same thing as as you have on your laptop, except that the configuration might be much better. So if you don't have good GPUs on your machine, for example, then on these remote machines on the cloud, you will have better resources, you will have access to more storage if you need to, so on and so forth. And one important aspect also is that these remote Linux machines actually contain some software that does specific things that you can just use it directly. You don't have to install it on your local machine. You don't have to worry about whether your machine can handle the demands and the resources that this software will need. So cloud computing is made for this specific task, which is to allow you to get access to these powerful machines with a high availability of storage and computing power. And for this specific section, what we will be using is Google AI Platform. So AI Platform is one of the services available on Google Cloud Platform. So this AI Platform is a service for artificial intelligence tasks. So almost anything related to AI you would need in your projects, you will find in this AI Platform service. Moreover, it has different approaches to training machine learning models. So there is the direct approach where, for example, they have support for Tensorflow, and you can just use your code, you upload your code, and the AI Platform service would read your code, and then it would do the training as you would do on your local machine. And also there is the way that we are doing in this course, which is through containers, where we build a container that has inside all the code and the dependencies of that code that you need in order to do your training. And then we can just use this container on AI Platform in order to run our training. Another great thing about this service is that it supports most, if not all, machine learning frameworks. So if you think of TensorFlow, PyTorch, MXNet, scikit-learn, all of these libraries you can use in your AI Platform service. And the best way to do this, in my opinion, is to use containers, because when you use containers, you are isolating your code from the system, and you're also compacting the dependencies that your code needs in just one image, a Docker image. So that makes it very easy to use any new libraries and frameworks. And even if you would like to experiment with different versions of the same framework, for example, as you know, or as you have heard maybe, the TensorFlow 1.x is different than TensorFlow 2.x. So you might want to maybe experiment on these versions, the versions that come with 1.x and the versions that come with 2.x, and maybe you want to run the same training and see the differences. Maybe you want to test new, let's say a developer version of some framework. You can do all of this using containers, and since AI Platform supports containers, you can use those frameworks and libraries to do whatever you like using Google Cloud Platform. In this video, we will be looking at how we can create a new Google Cloud Platform account. And for that, the first thing we need to do is to have a Gmail account. So for me, I already have a Gmail account that I created specifically for this course, just to show you how to start from zero. So once I have my Gmail account created, then I went to just Google and I looked for Google Cloud Platform. Then I chose cloud.google.com. And once I'm at this page, I chose this one here. Okay, let me just change the language to English. And you can just click on Get Started for free. So with Google Cloud Platform, what you will have is a okay, let me just check. Here you need to check your country and just check that you have read the conditions and everything. And what you're gonna get is $300 of free credit. So here, what this means is that you can test so many services on Google Cloud Platform for basically for free, because this is $300 offered by Google as a cloud credit. So this is going to help you try so many things without really using your own money. So for that, let's just click on continue here. And okay, you need to fill some basic information here. Now here you actually need to use your credit card, but don't worry about this because you will not need to, you will not be paying with your credit card. They just need this information in order to know that you are a real person, you're not a bot, and that you actually have a Visa card or whatever credit card that you can pay with later if you choose to maybe continue after you have that $300 finished. So for here, I'm just gonna enter my credentials, and once I'm gonna enter my credentials, I'm gonna click on start my free trial here. And after that, I'll show you what's gonna get, where we're gonna get once we finish this phase here. So here, actually, you will get to a specific step here where you need to validate some information. And for that, I had to take a picture of my credit card while hiding most of the numbers, just leaving the first 4 digits, just so that they can verify it. And as it's mentioned here, it might take some time to verify all of my my credit card and all the necessary information. And for me, I will stop here and I will continue using my my account that I had created long before. But for you, once you create this, you can start your free trial, and then you will access the same things that I will be accessing once I create or once I start using my other account. So here, now I am in the Google Cloud Platform, but using my old account, the one that I always use to create projects on Google Cloud account and on Google Cloud Platform, sorry, and to use all of their services. So as you can see here, I'm already in a dashboard, and it has already selected a project for me, which is a project that I'm using for testing purposes and for other things. And for you, once you come here, you're probably gonna find one project that's already created for you, and you can either choose that or you can create a new project. So you can click on new project, and here you can give a name for your project and you can create it here. And okay, let me just so let's call it test project course, and let me just click create. And here it should take maybe a few seconds. And now if you come here again, you're gonna see the new project here. If you click it, then you're gonna have the new dashboard that corresponds to your chosen project. So for me, I'm gonna continue using my old project here that I created specifically for object detection, for testing, and for everything linked to this course. So I'm just gonna keep using this one here. For you, you can start with that old one. So Once you get to this page, you have everything necessary so that you can start using Google Cloud Platform, and I'll see you in the next video. Another important thing that we need to have in order to be able to run the training on Google Cloud Platform is what's called Google Cloud SDK. So this is a software development kit that you can download, and you can have access to Google Cloud by the mean of your terminal. So here, if I write, for example, gcloud, you will see a set of options here. Okay, so as you can see here, it's giving me a list of options, things that I can use for or on Google Cloud Platform using my terminal. For you, if you try this command, you're probably gonna have an error. It's gonna say that you don't have that command installed on your machine. So for that, if you go and you search for Google Cloud SDK, it's gonna take you to the page. So here it just shows Cloud SDK, and if I come here, okay, it says get started. I'm just gonna click on get started here, and once you come here, you actually have the different options to install the latest SDK depending on your operating system. So for me, I have Linux, so I downloaded it using these commands here. So just downloading this, you can also alternatively just download an archive using this command, and you can extract it, and then you just run the script here. Just follow these commands here. It's very simple. If you have Windows, then you can also follow these steps here, and there is a GUI for installing everything necessary. So for me, I have already installed this. I am on Debian or Ubuntu, sorry. So for Ubuntu, I followed these steps exactly. I just copied and pasted these commands on my terminal, and I ran them. And at the end, I had Google Cloud SDK installed in my machine. So here, once you have it installed, let me just clear this. Let's clear it. So here, if I do, for example, gcloud init, so this one is gonna just show me some information about my my email, and the project that I'm setting. So the project that I created, or the project that I'm currently using. So for this, you can just verify that everything is set up correctly. And here, for example, it says pick configuration to use. Either reinitialize this configuration with new settings or create a new configuration. For us, we're not going to do any of the two because we already have everything set up. I'm just going to click Control-C. And once you have your correct Gmail account linked to your gcloud or Google Cloud SDK, here you can check so many things. So if we do, for example, gcloud, let me think, it shows gcloud, I think projects list. Here, for example, it's going to tell me all the projects that are created on my Google Cloud account. So if I come here, for example, you can see these 4, and they are the same here. So I have 4 projects here, and if you want to set one of the projects instead of another one, what you can do is Google Cloud config set, and I think here you just copy this. So let me choose this project, for example. So copy, paste. Okay, I actually think it should be set project. So here it has set a new project, and if I do again gcloud init. Let's see what we have here. As you can see, I have that project set for to be used, sorry. So for me, of course, I don't want to use this project. I want to continue using my other projects. So let me just do list my projects again. And here I want to set this project object detection using TF2. Now I just updated my project here. So let me check. Cloud init, and here, okay, I can see that it was set correctly. Control C, clear. So now I have, once you can use these commands, that means you have your Google Cloud SDK correctly installed on your machine, and you can continue with the rest of the course. Something that will be different now that we want to train our deep learning models on Google Cloud Platform is that our data needs to be on the cloud as well. So far we had data on our local machine, but now it needs to be on some storage facility in Google Cloud Platform. And for this, we're going to use a service called, you can just choose here Google Storage, or let me maybe write bucket. So if I write bucket here, I can just create a bucket. I have the first option here. So creating a bucket means that you're gonna create almost like a drive where you can store your data just like your local drive, except that now it's on the cloud. So I'm just going to click here. So I actually just changed the language on my computer just to stay always on English. So here, when creating a new bucket, you need to give it a name. So you can say, for example, you can either create each bucket, you can consider it as an experiment, or you can create a bucket and inside of it you create mini experiments. That depends on how you prefer things. So for me, I'm going to create one bucket and maybe set several experiments inside of it. So here, let's say, for example, TF2, let's say object detection API bucket, and I always like to end my bucket names with the name bucket so that I can distinguish it from the rest of the names of whatever things I create on Google Cloud. So here I'm going to click on continue, and of course you're free to choose whatever name you like. So I'm going to click on continue here. I'm just going to choose one region. So we're going to have the lowest latency within a single region. And here for the location, you can choose whatever you like. For me, I am in Europe, so I'm going to choose maybe Europe West 1. And I'm going to click on continue. Here, as you can see, you have 4 different options: standard, nearline, cold line, archive. I'm going to choose standard because it's the best one for short-term storage and frequently accessed data, because the data we're going to put here, the training process is going to access it frequently in order to read the images and pass them through the neural network. So I'm going to choose standard. So I'll click continue. Here I'm going to choose uniform. So this is the type of access control that you want to give to your Google bucket. For me, I'm going to choose uniform because it ensures access to all objects in the bucket by using only bucket level permissions. Here you actually have to specify access to individual objects, and I don't want to do that for testing purposes. And I usually just go with this second example because I want to ensure a uniform access to all of my objects. So I'm going to click on continue. And here you can either choose a customer managed key or Google managed key. I'm going to choose Google Managed Key because I don't want to add any more configuration. And here I'm just going to click on Create. So now our bucket has been created, and you can think of it now as just as your local drive, where you have basically like a C drive or a D drive, and inside of it you can create whatever you like. So for us, for example, we can create a folder, we call it experiment 1, for example. So if we do this, we're going to have a folder just like we had in our, let me check, so data. So just like we had here, experiment 1, and inside of it we had these data folder, training process, and also the configuration file. We can do the same thing and just upload them here. And in fact, let's just do this right now. So if you click on upload folder, let's just go to experiment 1 and let's go to data just to verify. Okay, here we have this, we have the pre-trained model. So yeah, so let's just upload this folder here, data. So I'm gonna upload it. It could take some time since we have some data here. And while waiting for this, let's create a new folder. We're gonna call it training process. So let me click on create. So as you can see, I'm trying to keep the same basically structure that I had on my local disk inside my Google bucket. And this makes it easy to understand things, and it makes it easy to understand and to keep things the same way, so that whenever you do testing on your local machine and you go to the cloud, you know exactly what things are, and you don't get confused by different setups that you choose for your local machine and Google Cloud Platform. So now that we have this, okay, now almost all of our data has been uploaded. Now I think all of them have been uploaded successfully. So let's close this. So as you can see now we have, let's go to training process. Here it's an empty folder. This folder will contain everything necessary, or everything that's generated from the training process. So there's the model, and there is the events, and everything that we had on our local machine. Gonna have it here. For the data folder, what we have is the label map. We have the test and train folders where we have our record files or TF record files. And we have a pre-trained model. For this experiment, we have Faster RCNN with ResNet 50. So it's exactly the same things that we had on our local machine. Let me go back here. So the one thing that is missing is the configuration file, which is the file that contains everything necessary for the training. So if we go here, again, as you remember, we need to define paths to our files, paths to our .records, and so on and so forth. So on our local machine, we defined these paths here depending on the structure and the different drives that we have, or the different disks that we have on our local machine. But on the cloud, we actually need to change this, because now when we run the training on Google Cloud Platform, the training will need to access these folders here. So everything needs to point to this bucket here, and inside this bucket we need to point to all of these folders. So for that, I'll be showing you how to change things in your configuration file so that it's basically configured for training on the cloud. So we're going to do this in the next video. So in order to configure things in our configuration file to accommodate training on Google Cloud Platform, let's first try to remember this. Now we have a bucket here, so we have this name of the bucket, and inside of that bucket we have a folder called experiment 1, and inside that folder experiment 1, we have all of these new, all of these data and the folder where the training artifacts will be saved. So if we go back to our configuration file that we used for training locally, what we had was something like this. So we had basically until this point here, okay, let me maybe look for the Faster RCNN. Okay, I don't have that one, but for SSD, for example, we see that we have this folder here, and then we have, okay, the experiment name, and then data, and the file, and the same thing goes for the rest of the paths that we defined. So for the label map, for the training records, for the testing records, it's the same thing, starting from the name of the experiment, and what comes before is basically the path to wherever these folders are found on our local machine. So if we think of it the same way, but just different in terms of now we have the data on our Google storage, the only thing that's going to change is that now our paths are going to start with GS, which is stands for Google Storage, and then we have a colon, then // Here we need to add the name of the bucket and also the name of the folder that we are using, which is experiment 1, but the rest will be the same thing as before. So for the checkpoints, they are found inside data, pre-trained model. So if we come here, so if we go to data, pre-trained model, we're going to find this folder here. Inside that folder, if we go to checkpoint, we're going to have CKPT0 in here. So if we go here, it's exactly the same thing starting from data. The only thing that's going to change is where that, or the name of that bucket, and then the folder that contains the rest of these things. So for that, let's go back here and let's take the name of our bucket. So copy, come here. I'm gonna change this to this, and what's gonna be left here is the name of the folder that we have here. So this is experiment 1. So if we come here and we change this to experiment 1, now we have exactly the same thing as we had before on our local machine, except that this path now points to Google Storage and to the bucket that we created. So if we take this part here, we can just copy and paste it basically everywhere. So for the label map path, again, it's inside the Google Storage. Then here we need to give the name of our bucket and then the name of the folder experiment 1. Then label map will be found inside data. And for the training records, if we come here, we change this. So GS colon / name of the bucket experiment 1. And the same thing goes for the other label map, or for the label map for evaluation. And here again for evaluation we have basically the same path, except that now we're pointing at the test folder. So with these things changed, now we have all of our paths pointing to the right place on Google Storage. And of course, now that we're gonna do the training on Google Cloud Platform, specifically AI platform, because we actually have the ability to run the training in 2 different setups, but for us, we're going to choose AI platform because it's much simpler. And now we have the possibility or the ability to change the batch size. So instead of using 2, now I am using 8. So 8 is a larger batch size, which is going to make the training much better. And for the number of steps, I increased it to 2000 here. And Here, most of the things will stay the same. We're not going to change them. Again, I have shown you before what you can do with scales and aspect ratios and what they basically represent. So you can change this. For now, I'm just going to keep them the same because we're just testing now and we're experimenting. The only new thing that I have added is this parameter here called second stage balance fraction, which by default it's 0.25, which basically represents the amount of positive examples that are taken while training. And for me, I just increased it to 0.5. This means that I want to take things, I want to take the examples that represent a negative examples, so background and positive examples, in a more equilibrium manner, you can say. So this is the only thing that I changed. You can ignore this if you don't want to use it, but for me, I have actually tested with 0.25 and with 0.5, and I did realize, or I did notice some improvement in the results. So you can add this parameter here as well if you like. If you want to just experiment, maybe you can remove it, or you just don't use it and you run the training, and after that you analyze your results. If they're not good enough, you come back here, you add it, and you give it the value 0.5. So I'm gonna save this here, and now I think everything is set up for training on the cloud. What I will be doing now is going back here and going to experiment, and here I'm gonna upload files now instead of folders because I just want to upload my config file. So let me click here, come back here, and I just changed the name of my config file. I added dash or underscore cloud at the end just to be able to distinguish it from the other config file that I use for training locally. So I'm gonna open this, and now it's inside my bucket and everything is set up for training, and I'm going to show you how to run the training in the next video. So before, when we were running the training on our local machine, we used these commands from the documentation, and as you can see here it says local. So in order to run the training locally, we just use this command where we defined the pipeline config path and the model dir. And the same thing for evaluation. Now, when you want to train on Google Cloud Platform, you actually have two different options. The first option is using what's called Google Cloud VM. So basically what you do here is that you rent a virtual machine on Google Cloud Platform. So you can have access to that machine, you can customize it, and you're gonna pay by the hour. And basically that machine is yours and you're gonna pay for it as long as you are renting it. As long as you are configuring it for your use, then it's yours and you have to pay for all of those hours even if you don't use it. Now for this, of course, you can set up things as they are mentioned here. And for me, what I prefer is using the second option here. So you can also train your object detection model on Google Cloud Platform using the service called AI Platform. So AI Platform is a service offered by Google Cloud, which makes things much easier when trying to run the training on Google Cloud Platform. So in order to run the training, what you need to basically do is to do these commands here. So the first thing is that you need to copy the setup.py file from the object detection folder into the research folder. So for me, I have actually already done this. Let me go back here. And here, as you can see, I am inside research. So if I do ls, you can see that I have setup.py file here. If you don't have it, you can just run this command. So what this command does is basically from the research folder, you're gonna run this command. So it's gonna go to this folder tf2, it's gonna take this setup.py file, it's gonna copy it to the current folder, which is research. So you can do this manually, or you can run this command as you like. For me, as I said, I already done it, so I have setup.py file inside my research folder here. So let me clear this. Clear this. And the main command, or the only command in fact that you need to use, is this one here. And in fact, I have tried this before and I realized that some things are not updated. So some things did not work for me and I ended up tweaking a few things to make it work. And for that, I ended up using this command here. And in fact, I will be attaching this file here to this lecture, so that makes it easier for you. So not many things changed really. The only things that changed are, for example, the Python version, they are mentioning 3.6, but it's not, if you run it like this, you're going to have an error. It's going to say, I think it's going to say that Python version 3.6 is not supported. So Python 3.7 is the one that is supported, at least as of now. So we are in October 2020. And apart from that, what I have changed are I added this, this line here. So scale tier to custom. I think they don't use it here. Yes, they don't use it, but it is required. When you run it, it's going to tell you that you need to set up the scale tier argument to custom. So I have done this. Another thing that I needed to change was this. So master accelerator, let's see what they used. So master accelerator, they used count 8 and type NVIDIA Tesla V100. I used count 2 and I kept the same type here. If you use count 8, you basically are going to run out of quotas and you need to make a request for new quotas, and that could take some time because you're actually making a request to the Google Cloud team and they need to study your request and take some time to answer you. But if you choose count 2, then you already have this quota and you can use the machines with discount. Of course, if you want more powerful machines, so if you want to add like 8 different types at the same time, this is gonna cost you more, that's for sure, but also you're gonna have to make a request to the Google Cloud team. So for me, when I changed this to 2, it worked perfectly, so I'm just gonna keep it here. I'm gonna keep it as it is. And the things that I think apart from this, nothing really changed. The same commands are left as they are. And the only things that we need to set up are the model dir and the pipeline config path. So if you go to your terminal, you actually need to set up these two paths here. But now they will be representing a path that exists on Google Storage and not on your local machine. So as it's mentioned here, let me just keep this always on top. So here, this path here, so gs : model dir specifies the directory on Google Cloud Storage where the training checkpoints and events will be written. So basically to our training process folder. So if we go back to our bucket here, and what we need to point to is this folder here, training process. And okay, let me just go back and check. So this should be model dir. So for us, let's start by defining, okay, model dir. So my model dir needs to be, let's go back again to our Google bucket. So model dir should be tf2 object. So let's copy this, copy, and then slash experiment 1 and training process. So this should be our model dir. So this is gonna be added to this. Let's go back again and check, or let's just look here. Okay, yeah, model dir is gonna be added to this. So it's gonna be Google Storage : / then this path here. So it should be the correct path. And now we need to also define the pipeline config. So pipeline config here, and this basically needs to point to our configuration file. And for that, what we need to have is the same thing as before. So it needs to be until this. So we're gonna have the Google bucket name, experiment 1. Inside of that, we're gonna take the name here. So maybe I'm just gonna take it from here. So Control A, Control C, and yeah, this should be the correct pipeline config. So let me clear this. And apart from this, I think we're set up to run the training. So let me just come here and copy all of this command. So copy this, and of course, again, I am inside my environment that I created using Anaconda, but I don't think it's necessary for this thing. Okay, let me just in fact verify something very quickly. Okay, Control C, clear. And in fact, I'm not sure, but I think you don't need to be inside this this environment that we have created, since now we're not gonna be using the local environment that we created. We're not gonna be using TensorFlow installed in that local environment. Everything is gonna be happening in the cloud. And in fact, let me just deactivate my environment, clear this, and I have this. Okay, let me maybe just check something first. We need to see whether our local variables that we have defined still exist once we close the environment. So let me check this. Okay, yeah. Basically, the variables that you define inside the terminal are going to exist inside that terminal, no matter whether you are inside that virtual environment or not. So let me clear this. Let's paste this again. Let's run it, and let's see what we get. So I just want to mention something here. So the first time you run this command, so the command that we took from here and from the repository of TensorFlow Object Detection API, when you run it the first time, it's going to ask you to allow it to enable this service here, so ml.googleapis.com on your project. So for that, you just need to choose here yes, and then click return, and then it's gonna enable it. It might take a few minutes, and once it enables it, everything should work properly. Now you might face this problem here where it says error, and it tells you that it's an internal error that was encountered. So to tackle this, what I would suggest you to do is just wait a little bit more and then run the same command again, because sometimes even when you enable the API, it might take a little bit of time to make the effect permanent in all of your project. So for that, sometimes when you run the command, like we did here the first time, the effect of enabling the API is still not propagated. So if you wait a little bit, like I did here, and I ran the same command again, you see that the command worked perfectly. So again, this is just a small thing that you should consider when you run the training the first time, or when you run this command here the first time. So I hope that this is clear, and if you face more problems that are different than this, then please let me know. So in fact, the training job has started successfully, as it's mentioned here. It says it's queued, so it's already it's already one of the training jobs on our Google AI platform. And just to verify that, we're going to go back here and we're going to look for AI platform on our dashboard. And let's go here. And in fact, here you can see our jobs. So as you can see, your AI platform, I have this job here that just started. So maybe let me click on this. It could take some time maybe to start things. Okay. In fact, we are inside our job here. Okay, let me just go back, maybe check all the jobs. I think my browser is a little slow, but I think the training job has been created successfully. So let's just wait a little bit. So yeah, in fact, these jobs are the ones that I have tested by myself before. And this job here, as you can see, this turning thing, it shows us that this job is still running. These ones have finished. So if I open this in a new tab, we're gonna see details about that new created job. So as you can see, this job has just been created. So October 27, 2020, exactly. So just 3 minutes ago, we ran this. It's the exact same job that we created here. So here, if we go to view logs, so I'm going to open this in a new tab again. And here we should see details about our job. So if the job starts and the training starts correctly, we're going to see all the details in here. If a problem appears, then we're going to see the problem appears here as well. So this could take some time to start a virtual machine on Google AI platform and to set everything up. So I'm going to wait a little bit and we're going to see what we have after everything has been set up correctly. So after some time, we see that we have lots of logs in here where things seem to be configuring inside some of the machines on Google Cloud Platform. And if I go way down, I can see here that it says step 100 per step time. Okay, this is per step time, and then the loss value. And this is an indicator that my training has started correctly and already 100 steps have finished. And in fact, you will see these logs after each 100 steps. So here, let me just try to maybe see if, yeah, okay. So actually, sorry. So here, after 200 steps, we see another log, and we see that the loss, in fact, has decreased, which is a good indication that the training has started correctly. So now, the only thing we need to do is to wait for the training to be finished. And one thing we can do to maybe verify things is, let's go to our Google bucket. Okay, maybe it's not here. Oh, maybe let's just search for it here. So bucket, I'm gonna look for storage here. And here I'm gonna go to the bucket that we created. So TF2 Object Detection API bucket. Experiment 1. Training process. And as you can see now, we have some checkpoints. So the model is being saved to this folder, and we also have a folder called train. Inside that train, we have events files, which are the files that basically save the development of the loss function during the training, and also some other parameters during the training. So maybe to look this up, maybe something we can do is run TensorBoard. So locally, when we were running TensorBoard, we were pointing to a local directory, and we were using our terminal. For Google Cloud Platform, what we can use is the Cloud Shell. So it's almost like a terminal, and it's running on your cloud or on your Google Cloud Platform. So here, once it's opened, we can see that we are inside our project object detection using TF2. And here, what we can do is use the same commands as before. So TensorBoard log dir. And here we need to give it the path to this folder here. So if I do Google Storage, colon // then let's take the name of the bucket, then experiment 1, then inside of that training process. And one thing we need to add here is what's called the port, so that when we open this, we open it in a specific port that we can use to visualize our TensorBoard window and everything inside of it. So if we do -- port 8080 and I ran this command, it should show me that, okay, the first thing it's going to ask me is to authorize Cloud Shell to basically make GCP API calls. So I'm going to say authorize. And now my TensorBoard window should be in this window here. But in fact, if you click it, you won't be able to access that site. The correct way to access it is by going here to this button here, which is called Web Preview. And if you click it, it's going to say Preview on port 8080. You click that. And now you have your TensorBoard window opening here, and you can see all the graphs inside this window. So immediately we can see that our training is basically much better than before. We still have these oscillations here, but still it's much smoother compared to what we had before, and the loss function is going down, so that's a good thing. And of course, the main thing that we need to look at is the total loss. So if the total loss is going down, then that's a good indication. If it's going up, then that's a bad thing, and you need to check your training. So here we can see that the training is going smoothly, and it has reached step 350. And as you remember, our training will have 2,000 steps, if I'm not mistaken. So let me check again. 2,000 steps. So after 2,000 steps, the training is gonna stop, and we're gonna have the final model saved inside our bucket here. So inside training process. So now you can see how you can do basically the same thing that you were doing on your local machine. You can do it on Google Cloud Platform. You have access to the same things, except that now you have better machine, and you have access to better configurations than what you have on your local machine. If, of course, you have a local machine that's like mine, but if you have a good local machine with good GPUs, then of course you can run the training locally and you don't need to go on Google Cloud Platform. And one final thing that we need to do is to run the evaluation. So basically you can run the evaluation at the same time as the training. So, and it's gonna do the same thing like it did on our local machine. We're gonna, the evaluation job basically, or the evaluation script is gonna look for new checkpoints, and once we have new checkpoints, it's gonna run some evaluation and it's gonna save the evaluation values like mean, average, precision into a folder, and it's gonna be in the forms of events, just like the training folder here. So for running the evaluation, we'll do this in the next video. And now we will be running the evaluation on Google AI platform, and for that we're gonna be running this command here. So it's almost the same as the previous command except this added part here, so checkpoint directory. And here this checkpoint directory we're gonna give it the same thing as the model dir, and what it's going to do is basically create a folder called eval inside our bucket. So if we go here, inside this, so the same thing that we have here. So there is a folder called train. We're gonna have a new folder called eval, and inside of it everything will be saved. And again, some of these commands are outdated, so for me, after experimenting, I will be using these commands here that are updated. And again, you first need to copy that setup.py file from TF2 to the research directory, and if you already done it in the first part when you ran the training, then you don't need to do it here. So for us, we already done that. So what we're gonna do is basically run this command here. So I'm gonna copy it from here, go back to the terminal, and I'm just gonna paste it again in here. So this will be a command to run a new job, which is object detection evaluation job. And now we see that the job has been queued. So let's go back to our dashboard and see whether we have the job. So this is the training job. It doesn't have eval in it. And I hope you notice this. So when I run the training, I name my job object detection, and then I give it a date, so the current date. But when I run the evaluation job, I call it object detection eval, then the date. And of course, the commands are the same. So this is the runtime version basically for the TensorFlow. So it's 2.1, Python version 3.7, job dir. So basically where we're gonna save our artifacts. Package path, this is something so that AI platform knows that we're gonna use object detection. The module name, the same thing. This is for AI platform to know that we're gonna use object detection. This is the region scaled here. As I mentioned, we need to add it because if you don't add it, you're gonna have an error. It's gonna, I think there's a default value here, but if you want to use these machines, so NVIDIA Tesla V100, you need to set this to custom. The master machine type and the master accelerator, I'm gonna keep them the same as in the command mentioned in the documentation. The model dir is gonna be the same. Pipeline config is gonna be the same as well. So now that we have this, let's go back and see. And now you can see, of course, we have this new job. And I'm gonna open it in a new window. Maybe I'm gonna push it after the training here. And also you can get access to the logs. And here you're gonna have the same thing. You're gonna have Google AI platform setting up everything so that it can run that training, that evaluation part. And let's wait a little bit. And again, what this is going to do is basically create a new folder. Inside this folder here, it's going to be called eval, and inside of it, it's going to save all the events for the evaluation job. So, okay, let me go back maybe again and check to see whether it started or not. So it's still setting up things in this remote machine. So I'll be back when things have started and when the evaluation has started, basically. So after a few minutes, I see that we have these logs here where we have detection boxes, precision, sorry. So we have all of these values here. When I see this, this means that the evaluation is running, the same thing that we had on our local machine. And if we go to our bucket again, we see that we now have this new folder that has been created. It's called eval. And inside of it, we have these events. And in order to see the evaluation part, we can also visualize this on TensorBoard. So let's open the Cloud Shell here. And of course, the Cloud Shell is still running our TensorBoard here. So the training part, let me just maybe stop it. Eval. Let me refresh this again. So here, because we only have one checkpoint now, we have only one data point here, and the mean average precision is still 0 because the training has not moved a lot yet. But after the training moves many steps ahead, we're gonna see new values here, new values saved. And now what you basically have are two different jobs, so two different setups where one is doing the training and the other one is doing the evaluation. Whenever the training reaches a certain level, new checkpoints will be saved here, and once those new checkpoints will be saved, the evaluation job is gonna detect that there are new files and it's gonna run the evaluation again. When it runs the evaluation, we're gonna see new data points here where we have mean average precisions based on that new checkpoint that has been saved. So with this, you now have all the necessary tools to run the training and the evaluation on Google AI platform. And I think this will wrap up everything. Of course, once the training is finished, I'm gonna show you the end result. But for now, this will be it. And of course, for the training, this could take some time. These are some previous jobs that I ran by myself. So as you can see here, this one took around 2 hours and a half. Of course, some of them, I stopped them by myself. And for the evaluation, it really depends. If you run it at the same time when you are running the training, then it could take some time. And if you choose to run it at the end, then this, I believe, could save some of the cloud credit, because the evaluation could go very fast once all the checkpoints have been saved. For me, I'm deciding now to run them at the same time. I know that at most it's gonna take maybe 2 hours and a half or 3 hours. I think for now I still have enough credits to run both the training and the evaluation at the same time. And again, once everything has finished, I'll show you the end results. So with this, I see you in the next video. So now that the training has finished and also the evaluation, let's take a look at what we have here, and let's analyze the results that we got. So just the first thing I want to see is if you go back to the jobs list here, you see that both of the training job and the evaluation jobs finished. So for the training, it took around 2 hours and a half, and also for the evaluation. Okay, let me just refresh this page to make sure that I have everything up to date. In fact, the evaluation was the last job. So this is the training job that we ran. It took around 2 hours and a half, and the evaluation job took 1 hour and a half, because it was mostly waiting for the training part. So whenever the checkpoints are saved, the evaluation job basically reads that checkpoint and makes a new evaluation. So in order to run, or in order to see the results and to analyze them, let's go back maybe here and just open a Cloud Shell. So let's wait for it. Okay, now we have it. Let me clear this. And what I want to do now is to maybe start with the train part. So again, when you use TensorBoard, you use logdir and you point to the folder that contains your events, then you will have the analysis going through those events files, and we will see what's happening, what was happening during training. So let me run this, and let me use web preview here. I'll preview on port 8080. I'm gonna close this. So here we see that this is how the development of the training went. So as we can see, overall the training or the loss functions went down. So every loss here, we see some fluctuations here, and this is normal, I would say, since we are still in fact using some a low batch size. If, for example, we use a better machine on Google Cloud Platform, and when I say better machine, I am talking about these values here. So what you give to master machine type and master accelerator. And of course, I am using these because I don't need to make a request for a quota, for example. And also, these machines are not very expensive. So if you want more machines and you want maybe more powerful ones in order to increase the batch size, then of course the price will be higher. So if we go back here and we look at the loss function, so here the total loss mainly encapsulates all of the other losses. So if you look at this, it's going to give you much better intuition about how your training went. So we see here that the training overall went well because the loss function kept going down until it went to the step 2K. Of course, here when I see this, now something that you can immediately realize is that for these last steps here, maybe the last 500 or even 800 steps, the loss function did not go down that much. So if I were to run the training again, then I probably wouldn't have used 2000 steps, because I see that the loss value here basically stayed the same. It didn't move that much. So maybe I would have stopped it at this step here. So 1200. So this is just something that I usually do. The first training you run, you see how the training went. If you see that the training and the loss function stayed the same for a long time, then if you run the training again, it's better to just stop the training before. So overall, I can say that this training was good. And now what I would like to see is the evaluation part. So for this, let me go back here and I'll stop this. And now I'm going to run the same command, except that now I'm going to point to the folder eval. And just to reiterate, these folders actually exist on, okay, maybe I don't have them here. Let me just look for them here. So storage. We have our buckets. So TF2 Object Detection API bucket, experiment 1, training process. So again, we are pointing to this folder here. When we point to train, then we are looking at the events that hold the information that were saved during the training. So the loss function values. And for the folder eval, what we have here are the events or the different parameters and the different metrics that were saved during the evaluation job. So let me go back here and run this again. And I should now have in this page the evaluation part. So when I refresh this, I can see that the mean average precision here changed from the first time. So the first checkpoint that were saved, if you remember, the first checkpoint basically is saved once the training starts immediately. The other checkpoint was saved at steps 1K. And although we chose 2K steps, but in fact, we don't see any value for mean average precision at the 2K step. I believe this is because the mean average precision did not improve. So now at the 1K step here, this is the best mean average precision that we got. And we can see that mean average precision basically it gives us information about large and medium and small objects. So inside the image, sometimes when we are detecting the masks or no masks, if they are close to the camera, then they're gonna look bigger and larger. And if they are far from the camera, they're gonna look small. So what these graphs here tell us is that in the large or on the large objects, so when the people are basically close to the camera, we have a more or less high mean average precision. So this is a value of, okay, it's 0.6, but when it's smoothed is 0.3. And here for medium objects, it's around 0.3. If it's smoothed, then 0.2. And again, for the small ones here, we see that they have the lowest value for mean average precision, which tells us that for small objects, our model is not performing very well. So for example, if you run the training again, maybe this is something that you would want to focus on. Maybe you can add new images or collect new images with objects that are far from the camera, so they look small. So this could improve the results as well. And also you can tweak the parameters in the config file for that purpose. And here, this is just the recall, but for us, let's just focus mainly on the precision here. In fact, if you are working in a team and you're trying to build an AI solution, it's better to focus on one metric. This is something that I read in the book from Andrew Ng. He says that it's better to focus on one metric when you are trying to optimize a deep learning model for some AI project. So for me, I usually try to focus on the mean average precision because it tells me how my model is performing overall. And apart from this, we can actually look at some images. So these are the images coming from the evaluation dataset. So if you remember here in our experiments in data test, so here we have a .record file which contains images and annotations for the data that the model did not see during the training, or at least it didn't use during the training, because in fact, the model did see them during the training because we ran the evaluation at the same time as the training. So at the 1K step and at the first step also, we were doing evaluation, so the model did see these images. But it did not use them for training, so this is why we use them to see how our model basically generalizes on images that were not used for training. So here, what we have here is that on the left, we have the predictions of our model, and on the right, we have the ground truth. So here, for the first image, we see that our model is performing, I would say, very well. Here, it detected all the faces with masks, so it had the correct class predicted, and also the bounding box is very good, I would say. It's the model is very sure that these people are wearing masks. And for the ground truth, we see that it's the same thing. So we didn't miss anything from the ground truth, which is a good thing. Let's look at other images, maybe this one. So again, on the right we have, sorry, on the right we have the ground truth. On the left we have the predictions. And again, we see that the model was able to detect these people wearing masks correctly. Let's maybe look at different images, maybe something that's a little difficult for the model. Okay, let's look at this one, for example. So here, again, on the left, we have the predictions, and on the right, we have the ground truth. And you can realize this if you look at the probability of predictions or the probability linked to that annotation. So in the ground truth, you see everything is 100%. So we are very confident because it's a human who annotated these images. But on the left, you see that for some predictions, for example, this one here, it says that it's wearing a mask, but it's very low probability. I believe this is, I'm not sure if it's 97 or 37, but still the model is still not sure. Here we have prediction of someone that's not wearing a mask, and the probability is a little low. Again, the same thing here. So this person is not wearing a mask and the probability is low. And we also see that, in fact, there is a person here that the model missed. So this person here is not wearing a mask. The model should have predicted this, but it didn't. So again, this shows how our model underperforms when it comes to small objects in the image. So when the objects are big, so when the people are closer to the camera, their faces or their heads are very clear. So the model finds it easy to predict whether they're wearing a mask or not. When they're a little far, then it becomes a bit more difficult for the model to make the correct prediction. But overall, I would say that the model is doing well. I almost never expect the model to be perfect, so to have 100% accuracy and to find all the objects, but I expect it to at least be able to predict the correct classes and the correct things for the objects that are clear to me as a human. So these ones are very clear, so I would expect the model to do well on these. The ones that are far a little bit, then I'm usually okay if it's not performing that well on those things. But of course, there's always room for improvement, and you can always do more things to improve your model. And again, maybe this image is also a good example on when our model underperforms. So mostly these are small objects. Most people or all people here are far from the camera. So the model is able to predict most or a lot of these people and what they're wearing, but also it misses other people like these ones here. And again, we can see this in the ground truth. So there are so many people here, but in the prediction part, we're not able to predict those very well. But again, overall, I am happy with these results. And I think that this would be it for the training and evaluation part. What I would like to do now is to take our trained model, so the model that's inside our training process. So I would like to take this model here, so checkpoint 2, and use it in some Python application to make predictions on the images. And again, as you can see here, we have checkpoint 1, checkpoint 2, and checkpoint 3. Checkpoint 1 is the one that was saved once we ran the training. So whenever you run the training using Object Detection API, it's going to save a checkpoint at the beginning. And that one usually is very bad because we're still at the start of the training. And we also have another one that was saved at the 1000th step. So this is checkpoint 2, and another one that was saved at 2000th step. I'm gonna choose the one that's called checkpoint 2 because, again, if we go back to our graphs here, we see that one model, or the model that was saved at the 1K step, is doing well, and no other model was saved because it probably did not do well compared to this model here. So we're gonna take this checkpoint 2, download it, and use it in some Python application to make predictions on our images. So I have mentioned a technique or a possible approach to tackle that problem where we had the model not performing very well on small objects in the image. So one thing that I mentioned was to maybe annotate new images where the objects are small and include them in your training. So that's a possibility. Another thing that you can try is going at the scales here for the anchor generator here. And what you can do is add maybe another scale that's even smaller than this, so maybe 0.1 here. And what this means is that we're gonna generate some anchor boxes that are very small and that they will learn to converge to those small objects in our ground truth images. And this will teach basically the neural network to recognize better the small objects. And also maybe I would remove this bigger size here because we didn't have that many images where the object was that big. And just doing this, I believe this could improve the results. And again, since I have explained this before and what they mean, I hope that you understand the intuition behind this, because what I'm trying to do here is generate anchor boxes that are very small. And when I train my model, this will basically, it's as if I am guiding my model to detect things that are that small as well. So this is another thing that you can do. And of course, you can still play with the other parameters. Maybe you can add more data augmentation so that you can generate more images during the training. So this is also a possibility. So there's a lot that you can do. Just playing with these parameters can improve things. But of course, the purpose of this course is to show you how you can approach these things when you're building a deep learning model for object detection. And we can't go through all the options and do them because I don't think even that the cloud credit that we get from Google Cloud will be sufficient for doing all these experiments. But of course, I am giving you some guidelines here, and I encourage you to try them. And if you face any problem, don't hesitate to let me know. And now, since our training has finished, what we need to do is to use our model for inference or for making predictions using our images, using new images or old images. And for this to be the case, as you remember, what we have now is, or are these checkpoints here that were saved during the training. But these, although they contain the model weights and the architecture of our neural network, the convention is not to use these for inference at production time. So when you are trying to put your model in production, so whether that be on the cloud or on your laptop as part of some sort of a desktop application or in a mobile application on Android or iOS, for that, you will not be using the checkpoints here, but you will be using what's called the frozen model. And this frozen model is basically taken or it's generated from these checkpoints. So this is what I'll be showing you in this video. So the point is, or the purpose and the aim is to take the checkpoints here and turn them into a frozen model that we can use to make predictions. So the first thing I want to do is to check which one of these checkpoints. As you can see, we have 3 different checkpoints here. I want to see which one is better so that I can only take that one, and that one I'll be using for creating my frozen model. So the first thing I'm going to do is just activate a Cloud Shell here, and I'm going to run the TensorBoard again just to look at the evaluation events, and based on that we're going to choose which checkpoint to keep. So here basically, if you ran the commands before for TensorBoard, if you use your arrow keys, for like now I am using the up arrow key, I can go to the commands that I used before and I can just run them from here without retyping them. So here, as I mentioned, I want to go to my checkpoints or to my events here in the evaluation. I want to see these. So for that, I'm gonna choose here eval, and I will run this command from here. And once I see that the command is running, and of course we have to authorize this. Now that I see that the TensorBoard is running on this address in the browser, I'm gonna go to Web Preview, Preview on port 8080, and here we're gonna, of course, get our plots again. So as I have mentioned before, if we look at the mean average precisions here, we see that we have basically 2 points where the model was saved. There is the first point at step 0, so that represents checkpoint 1, and there is the other one that was saved at step 1K, so that represents checkpoint 2. And of course we have here, as you can see, we have 3 different checkpoints. So the third checkpoint, we didn't say, although the model was saved, there was no evaluation done. The model probably did not improve that much. That's why the evaluation job did not save or did not add that point to the graphs here. So for that, what we're gonna do now, since we see that in these plots, the model that was saved at 1K is better than the model that was saved in 1K, at step 0, because at step 0, we basically had the same pre-trained model that we took from the model zoo. So of course, that model did not know what mask or what people wearing masks and people not wearing masks is. So of course, we had the mean average precision as 0. But here it started to learn, and the mean average precision started to increase. So we're going to take checkpoint 1, and for that, or checkpoint 2, sorry. So checkpoint 1 is the model that was saved at step 0. Checkpoint 2 is the model that was saved at step 1K. So here I'm going to download these 2 files here. So let me just, in fact, I think I already have them downloaded. So let me check here. New tab. Yeah, in fact, I already have them here. So maybe I'm just gonna cancel this and we're gonna use these ones that we have them saved here. I already downloaded this. So what you need to download is these 2 files, so checkpoint 2 here, one for the index, one for the data. And also you need to download this first file here called checkpoint. And with that being said, let's take the 3 files from here. So I'm going to copy them. I'm going to go back to our folders where we ran the experiments locally. And here I'm going to create a new folder. I'm going to call it inference. So inference, in deep learning terminology means that you're just going to pass images through the model to make predictions. You're not going to run the training. So this is the inference phase. And let me just maybe create a folder called data. And inside of it, I'm going to create a folder called checkpoints. And here I will save, or I will paste all of the files that were downloaded. So as you can see here, when the files were downloaded, the Google Cloud Platform basically has this naming convention where it's basically giving us the name of the folder here. So experiment 1, then training process, and then we have the names of our files here. And this is okay, you can keep them like this, but in fact there is something, or there's a problem that you're gonna face at a later stage, which is basically when we're gonna transform our checkpoints into a frozen model. The script that we're gonna use is gonna read this file here, so the checkpoint, this first file here. So let me just open it and show you what it has. So this file here, as you can see, it has basically a history of the checkpoints that were saved. So here it says, okay, model checkpoint path, it's pointing to the last model, so checkpoint 3. And here, every time there is a new checkpoint, it adds it here as, and with the corresponding name. So checkpoint 1, 2, 3. And if we go here, we see them named as such. So we have checkpoint 1, checkpoint 2, and checkpoint 3. So when we are going to run our script, it's gonna have a problem, because in this file here, basically this file tells us that in the history of the training, these are the files that were saved. But then when our script is gonna look at our folder, it's gonna see that there are other files here, because it's gonna see that they have other names. So it's not gonna recognize that this checkpoint 3 or this checkpoint 2, for example, corresponds to these 2 files. Although we have checkpoint 2 in the name here, but our script is not gonna know them, because there's all of this this part here, all of this here that was added by the Google Cloud Platform, just to help us basically distinguish between our files, and that poses a problem for us. So the easiest way to fix this is basically just to remove everything that was added by Google Cloud Platform. So we're gonna remove this. I'm gonna go here and remove this too. And finally, we're gonna remove this. So now we have the same structure that we have on our Google Cloud Platform, and we have the same names. And when we open our checkpoint here, it's gonna be the same. So when our file checkpoint has these names here, if our script goes to our folder here and it reads this checkpoint, it's immediately going to recognize that this CKPT2 corresponds to this CKPT2. So now, okay, let me just close this. We don't need it anymore. And now that we have this, we're gonna run the script that comes with Google or TensorFlow API. So let me just open a new terminal, and here I'm gonna activate my Conda environment, activate TF2 GPU, and as you can see, it's activated now. So I'm gonna clear this, and now I'm gonna CD to my folder that contains the TensorFlow Object Detection API. So this should be in here, TensorFlow, and then we're gonna go to models and research. So now we are inside the folder research, which is inside our TensorFlow 2 object detection API. And the script that we need to run is actually inside the folder object detection. So let us take a look at the scripts that are here. And the one that we are going to use is this one. This Python script here will take the checkpoints that we have here as input and is going to give us a frozen model at the output. And that frozen model, we're going to use it to make predictions, and that would be the file that you would deploy in production however you like, and you won't be using the checkpoints in production. So for that, let me clear this again. And the way to run that script is, in fact, I already have written this to help you basically take that or run that script easily. So I'll be sharing this, with this lecture. So here, in order to run the script, what we are going to give it, first of all, this is a mandatory input here or argument where we tell it which type of input we have. So we have an image tensor. So we're just going to mention this. This is by default. It always stays like this. The second argument will be pipeline config path. So this one would be the path to the config file that we have. Then we have the trained checkpoint dir. This will be, this is the path to where we saved our checkpoints. So this is why I am mentioning adding this here. So this the $, then model dir, and I'm mentioning that this is the path to where your checkpoints were saved. And finally, this is the output directory, and this is the directory that's going to contain the frozen model. So for that, let me just take a look at how we are structuring our data here. So first we have the checkpoints saved here. And what I usually like to do is to put everything that I used for inference inside this folder here, so that, or at least inside the inference folder here, so that I know what I used during the phase where I froze my model. So for that, let me go back here, and I'm just going to take the config file that we used on the cloud. So Control C, and maybe I'm going to add it. I'm going to add it here. And what I also need is, no, I think that's it actually. That's the only thing that I need, but we will be saving our frozen model into a directory, and for that I'm going to create a new directory. I'm going to call it frozen model, and this naming convention frozen is known in the deep learning community. So what it means is basically the model will not be eligible for training anymore. It's going to be made for prediction only. So when we run this script here, exporter main v2.py, it's going to optimize our model for inference, and it's going to remove any parts that are not used during inference. So now that we have this here, I'm just going to go here or I'm just going to go to my script again, and I'm just going to define these variables in here so that it's easier for me to run that final command here. So the pipeline config path, this one would be our configuration file. So I'm going to run this. The model dir will be the path to where our checkpoints are. So this, I'm going to add it here, checkpoints. And finally, the output dir will be the path where I'll be saving my frozen model. So this would be that one. And now we have everything necessary to run our script for freezing our model. So let me just copy this command here, and I'm gonna paste it here, and let's verify we have, or we should have everything here. And let's run this command and see what we get. So if everything goes smoothly, we should get some new files added into this folder here. So let's wait a little bit. This could take maybe around a minute or so. So let's wait and see what we're gonna get in here. In fact, I realized that I forgot to change something, so I wanted to share with you this error here so that if you face this error yourself, you're gonna know how to fix it. So here it says this, it did not find this checkpoint here, CKPT3, and the reason for that is that when our script model exporter, or what's called exporter main v2, when it's run, it's gonna read this file here, checkpoint. And this model here is basically pointing to the last checkpoint that was used or that was generated during training. But for us, since we're gonna use checkpoint 2, we need to change this to checkpoint 2. We don't really need to remove these checkpoint 3 parts from the file. We just need to tell our script that look at checkpoint 2 and not checkpoint 3. So now that we have this, let me clear the screen again, and we're gonna run the same command again. So I just used the arrow keys to get this command, and let's run it again and see what we get now. So here I wanted to show you this error as well. As you can see here, it says that there's some tensor that's incompatible with another tensor shape here. So if you read something like this, it might be very confusing and you may not know what the problem is. So for you, like, what's the difference exactly? What's the problem? Where is this problem coming from? You downloaded the checkpoints and you put them in your directory, and you just took that config file that you use on your local machine and you just run in this script here. And the problem is, for me at least, this config file that I am using here, I actually took it from the local training. So when I was training locally, and when I was running the training locally, I had some values a little bit different than some of the values that were used on AI platforms. So as you remember, if I go back here, so I had one configuration file that I used locally, then I created another one for training on the cloud, and then I made some changes and I uploaded this one to the cloud. But I believe I did make some changes to this config file even after I uploaded it to the cloud. So the version of the config file that was used for training our model on AI platform is different than the one that is saved on my local machine. So this is posing a problem, and in order to solve this problem, what you need to do is just download the exact configuration file that you used on your AI platform when you were doing the training. So if you download this exact one, and for me, I downloaded it and it's saved in my downloads folder here. So I'm gonna take this one. I'm gonna go back here, go to inference. I'm gonna remove this one, and I will paste my configuration file that I downloaded it just now. And of course, as you can see, again, when Google Cloud Platform downloads or gives us some files to be downloaded, it changes their naming. So here, I'm gonna change it to the original name that we had. You can keep it as it was. This does not add any problem, but just for me, I like to keep things, I like to keep the same structure everywhere so that it's easier for me to understand and to remember what I have done in the past. So now I am sure that this is the exact configuration file that I used during the training on AI platform. And let me just go back to my terminal here. Let me clear this, and I'm gonna run the command again. So now everything should work fine. There shouldn't be any problem now because we have the exact same structure that we had on AI platform. We have it now here. So everything should go smoothly. And okay, it shouldn't take that long. And it seems that everything is okay. There's no error. There's no problem popping up. And of course, in our folder here, okay, now you see that our folder is filled with some new files, and this is the frozen model. And as you can see, the freezing process, if we can call it like that, is finished. And now we have this folder here that contains some files here. So this is just another configuration file, which is basically the same configuration file that we had. It just copies it here. As you can see, we have the same values that we had in our configuration file here. And okay, let me just reload this. What else do we have? We have a folder called checkpoint, where we have the checkpoints that we used. So the ones that were here, they were copied to that folder here, or that folder, sorry, here. And finally, what was generated, or the main thing that was generated as a frozen model, is the saved model here. So as you can see, now we have these three folders, and we have, these two folders and this file here. So this file is .pb. So this is an extension, which means protobuf. This is an extension that basically is a binary file. So it's small, and it also encapsulates the architecture of our model. And in the variables here, we have the weights of our model. So this is the new convention of frozen models in TensorFlow 2. So when if you go back to TensorFlow 1, what you would get at the end is just one file, .pb. That's a large file which contains both the architecture and the weights. But now this is a different approach from the TensorFlow. This is what the TensorFlow team has chosen. So now we have a file called which has an extension .pb, and we have a folder that contains the variables, and we also have a folder that's called assets. But honestly, I still don't understand what's the purpose of this folder here. It's always empty, but there's probably some specific case where it might contain something, but still we're gonna keep it because it was generated. So all of these represent the frozen model, and this is what we are going to use to make predictions on our images locally. Now that we have our frozen model generated here, let's use it to make predictions on new images. And for that, we're going to use some helpful scripts that are in the repository from my friend again. So he made some very helpful scripts that we can use during the inference time. And these two scripts are one called detector.py and another one called objectdetects.py. And to use them, I actually copied them and pasted them in my in some files on my local machine. And what I will be doing is using these scripts. And in fact, I made some small changes to these scripts, and I will be sharing with you my version of the scripts, but they are very minor changes. And here, what basically these scripts do is, the first one, detector.py is represents a class here called detector tf2, and this class is a class that helps us do so many things. Where, for example, we're gonna load the label map. As you remember, the label map is the map that basically has IDs and then has classes. So, for example, ID1 would map to class mask, and ID2 would map to class no mask. So here it's also using some utilities from the object detection API. And what we're doing here is just loading some necessary files like the label map. We're creating, or we're clearing a session here. So when you see this command here, what we're actually doing is just that if there is some model that's already loaded in memory, then this command clears it, so that, for example, if you run the inference once, if you run it again, then first it's gonna clear the memory of your machine and then continue to load the model here, as it's shown in this command here. We're loading the model. So first we're clearing the session and then we're loading the model. We do this because if you already have a model in memory and you try to load another model, sometimes you can get a memory error where you basically either your script freezes or something is gonna prevent from running the inference. So when we clear the session, we're making sure that the memory is empty, or at least there's no model loaded in that memory, and then we load the model again. And then there is a function here that basically runs the detections. So what we do here is we create a tensor image or an input tensor. So the only thing we're doing here is just we're taking our image, which has 3 dimensions. We have width, height, and the depth. Depth represents the number of channels, usually 3. And then we're adding a new dimension. So now our image becomes something like 1, then width, height, and 3. So we're adding this value, or this new dimension here, because during the training we were using something like this, and this helps us, for example, load many images and pass them through the model that we constructed. So you can imagine that we have, for example, 2 or 3 or 4 images, and they will all be stored in the first dimension. So, for example, you can imagine a structure like this where we have 4 images and each one has the same width, height, and depth. So that's the only thing we're doing here. And then we're getting the detections by passing that input tensor to the model. And once we're getting the detections, and then we're basically decomposing the information that's in here, because the detections part contains so many things. It contains the coordinates of the bounding boxes. It contains the classes, so in our case, mask or no mask. It also contains the scores or the confidence levels. So if you remember when I showed you in TensorBoard, some of them had like 99% confidence, and some of them had maybe 77 or 74%. So that represents the score. And usually it's not in percentage. In fact, it's never in percentage. It's in a value between 0 and 1. So these would be something like 0.1 or 0.7 or 0.9, so on and so forth. So here we're just basically putting everything together and then returning detection boxes here. And of course, this extract boxes is just doing what I have mentioned. So it's just putting everything together. We're appending the different boxes one after the other, and we're returning them. And then here there is this function that displays the bounding boxes. So what it does is that it takes the image, it takes the coordinates of the bounding boxes and their confidence scores and their classes, and it's just as you can see, we're using OpenCV to draw rectangles on our images using the coordinates that we got from the detection part. And that's it. There's no, there aren't many things. There is nothing here that's complicated. Everything is just plain simple. We're just making predictions, taking those predictions, organizing them into different bounding boxes, and then we're drawing them. So that's what the detector class here is helping us do. And here, just want to mention something. I think I made some changes here when I was doing some testing. I'm just gonna verify here if there's anything that I changed that you don't know about. Yeah, I think there's nothing here. Maybe I just changed the size of the rectangles because the lines were too thin. So I added some size to that. But apart from that, there's nothing specific, or there's nothing complicated here. And then we have the detect objects Python file, and this file basically uses the class that's defined here, and we're either making detections on the video or on some folder that contains images. And for us, what we will be doing is running the detection on images that are in a folder. So for that, let's go back to our folder where we have everything shown here. So we have the checkpoints, the frozen model. Let's create a new folder. Let's call them, for example, test images. And then inside this folder here, we're gonna add some images. For that, I'm gonna look for images to add them here. And once I add them, we're gonna use them to make the predictions. So here we have these 4 images that we're gonna use to test our frozen model. So here I just have an image of my brother wearing his mask, also an image of me wearing the mask, and also I have 2 images from the dataset that we used. So we have this image where 2 people are wearing masks here, and here we have a bunch of people who are wearing masks, and also this person here is not wearing any mask. So we're gonna run our script here on these images, and let's see what we get. And I just want to mention something. Since I am recording and I'm also going to do the inference, the memory could be overloaded. So so far I'm not sure if it's gonna freeze or not. If my screen freezes, then we're gonna wait a little bit, or there's also something else that I'm going to do, which is saving the predictions. This script basically allows us to do that. As you can see here, this last parameter allows us to save our script or our output images. So at the end, we should have some output images that are basically the same images as ours, except that there will be bounding boxes here. So for that, let's go here and just look at the parameters before we run the script. So here the script, we're going to give it the model path. So the frozen model, we're going to give it the path to the label map. Here we don't need to give it this because we want to show all the classes. This basically, if you have a, let's say many classes and you don't want to show all of them when you do predictions. Let's say you have people with mask, people with no mask, and let's say a chair, and you don't want to see the predictions for the chair in your image. In that case, you just use the IDs for the classes that you want to show. So for example, 1 for people with mask, 2 for people with no mask. And if 3 corresponds to the chairs, then you don't add 3 here. For us, we want to show everything, so we're not going to pass this. This threshold here is the confidence score. So for example, you might choose to show only the objects that have a confidence that's higher than 0.8, so 80%, or you want to show, in this case, for example, we want to show all the objects that have confidence above 0.4, or you can even decrease this and put it 0 or 0.1, where you're going to show even more examples. I think 0.4 is okay. In fact, I'm even going to increase it maybe a little bit to 0.5. And apart from that, if you pass the video path argument here, that means you want to make predictions on a video. For us, we're not going to be using this, and I do encourage you to try this as well. And finally, we're going to pass the argument save output, and what this is going to do is save the predictions, so our images will contain those rectangles. So if I do output directory here, if I add a path in here, then that's where the output images will be saved. But for me, I'm not gonna add it here. I'm just gonna change it where I give the arguments. So I want to save them in a folder called outputs inside this folder called data. But let me just maybe change this, and maybe I'll get a new folder. I'll call it output, and I want to use this folder for as an output directory. So let me just clear this, and I want to get this in here, and I'm gonna take this folder, so copy, and I'll paste it in here. So this means that any generated images or any images where the predictions will be shown on them will be saved in this output directory in here. So now let's try to run our script here, and in order to just be able to see all the arguments, I'm just gonna run the script from here. So the first thing, again, we're gonna have to activate our Conda environment. So it's TF2 GPU. I'm gonna clear this, and then I'm gonna run Python detect objects.py. I'm gonna give it the path to the model. So model path will be, let's look at this. So the model path will be in the frozen saved model. So I'm gonna pass this one here, saved model. And what do I also need to pass is the path to the label map. So path to label map. And I don't have the label map in my folder here. So let me go back here. I want to add it here as well. So as I have mentioned before, I like to keep everything that I use for some specific task in one place, even if I'm copying things. Just easier to understand and remember things that way. So I'm gonna copy this from here, and I'm gonna go back here and put it here. Okay, so now I have the label map, so I'm gonna pass it here. What else do I need to pass? I need to pass the directory where my images are. So images there. This would be the folder test images. And apart from that, we only need to pass the save output argument here. So we don't pass anything to this one. We just say save output. If you add this argument in here, this means that it's gonna save the output images into our output directory. So let's run this and see what we get. And again, this might take a little bit of time, and it might freeze a little bit because we would be overloading the GPU memory. So let's hope that it goes smoothly, and let's try this now. So now, okay, we have some logs from TensorFlow. And Okay, successfully opened the dynamic libraries from CodeDNN. And now, as you can see, we have this image, the first image. It's not shown well here because of the way OpenCV shows the images, but I'm just gonna click on space just to go to the next image. And here we see another image where we have the bounding boxes and the writing here. So the class plus the confidence score, and the writing is a little bit big here because I made some changes, but I'll speak about this a little bit later when we finish this. This is another image where we have the different faces. And here, as you can see, this class says no mask, this says mask, this says mask, so that's good. Let's go. And this is this is the image of me wearing my mask, and that would be it. So it's good that it didn't freeze. Now let's go to our output directory. I'm not sure, it should have saved them here. In fact, I had a problem here where I forgot to add a / at the end of my path here. So this was causing a problem. That's why the images were not being saved here. And once I added my / here, the images were being saved when we run the script in here. So now that the images are saved, let's look at them. So I'm gonna open this first image of me wearing a mask. So as you can see, our model was able to detect my face, and it says that there is a mask. So I am wearing a mask, that's correct. And it's very confident in its prediction. So it's 1, it's basically 100%. And that's good because we never shown this image to our model during training, and it was still able to predict it well. So that's good. If we go back here, we see that it was able to detect all of the faces here. Of course, the writing is a little bit big in here, and that's because I made some changes in order to be able to see the writing in here, because my image is larger than these images. That's why if I did not increase the size of the writing here, we wouldn't have been able to see it. But here it's also able to detect these ones, so that's really good. Here it says no mask, and that's true. This kid has his mask a little bit, he's not wearing it correctly, so that's why it's predicted as no mask. Here, this is predicted as mask. This one we can't see because the writing is a little bit on the top. And this one also, we can see that it says mask, so it's a good prediction. And overall, I can say that our model is performing very well. So with this, now you can see that how we went from the training to getting our checkpoints to freezing them to get a frozen model, and then using that model to make predictions on new set of images. And now you have seen basically the whole pipeline where you do the training and also the inference part. Now that we have seen how to run the training on Google AI platform, and for the first case we use Faster RCNN ResNet 50, let's try to do the same thing with SSD. And for this, we're basically gonna do the same exact steps, except that now we're gonna use the SSD pre-trained model and the SSD config file. So for that, let's just go back to our experiment 2. And experiment 2 is the one that contains all the necessary data for training SSD model on our local machine. And what we're gonna do now is move everything to the cloud and run the training there. So I'm gonna go back to my bucket here, and let me get to the root of the bucket, and I'm gonna create a new folder. I'll call it experiment 2. Let me create this, and inside this I'm gonna upload the same data as before. So basically, let me just upload folder here. I'm gonna upload data, and again, just to reiterate, just like we discussed this for training on the local machine, you can actually put your data in some centralized place. For example, you can add it here, a folder called data, and all your experiments can access that folder here. Or since we don't have a big data set here, it's very small. For that reason, I am just adding it to my experiment folder here. Feel free to do whatever you think is best. And now that we have this data here, I'm gonna create a new folder. I'm gonna call it training process, just to keep things consistent. And what we need now, okay, while waiting for this to upload, we're gonna go back and check the config file. So let me just maybe, I'm gonna copy this and paste it here. I'm gonna change the name and just add _cloud here. And this file here, we're gonna use it to add all the necessary things to run the training on the cloud, just like we did with Faster RCNN. And let me just open this here, and I will make it closer to Faster RCNN so that we can just compare things here. So let's go through the main things that needs to be changed. So maybe let's start with the batch size. We know that we're gonna make it a larger batch size, so I'm gonna put 8 right now. Here I'm gonna put 2000 again, or maybe just 1500. I'm gonna put 1500 here, and let's go through the paths here. And since it's basically the same structure, the only thing that's gonna change, or the only two things, is the experiment. This will be experiment 2, and the name of the config, or the name of the folder here needs to be SSD. So let me maybe copy this one or this one here. I'm gonna copy it and I'll paste it here. So I first will change this, since it's the easier part. And now I have to change this to Faster RCNN, or to SSD, sorry. So this should be inside the pre-trained model here. Oh no, it should be in data, pre-trained model, and this is the name of the folder. I'm going to take it from here, Control-C, and I will paste it here. And just to check, we should have inside of it a folder called checkpoint and then CKPT0. So we are done with the path to the checkpoint, so to the pre-trained model. Now let's go down and change these ones. I will do the same thing, so I'm gonna copy this and I'm gonna paste it here. So this is gonna change, it's gonna become experiment 2, detection API bucket. And okay, let me just check something. TF2 object detection API, yeah, that's exactly the name that I'm using. And again, I'll just copy this and paste it for the evaluation part here. It's the same thing. So I'm gonna paste this here. And also this needs to change. So the path to the training data, TF2 object detection. Here, I'm gonna put this one here. And finally, I need to change the path to the .records, and this should be for test. Let me just verify here. It should be test, yeah. Okay, let's just verify one last time, because I remember that I created another bucket when I was experimenting. So just to make sure, okay, TF2 Object Detection API bucket here is the same everywhere here, TF2 Object Detection API bucket, and it's the same bucket that we have here. So this should be good. And okay, let me go back, maybe save. Okay, everything is saved. Let's check one last time if we missed anything. Let's look at the pre-trained model. Are we using it for detection? Yes, we are. So that's good. And apart from this, let's look at maybe the anchor boxes also. So we have, okay, anchor scale. We have one scale here. We have these aspect ratios. Maybe I'll add another scale here. So I'm going to use 0.2 maybe. So this means that I want 1/5 of the base anchor size, which is usually 256. So this will be 1/5 of 256. And yeah, okay. You can also play with the other parameters if you like. For now, I'm just going to keep these ones here. And let me save this. And what I will do now is upload. Okay, let's verify everything has been uploaded. Let's upload files now. Experiment 2. It should be here. So this is the cloud one. And now after this is uploaded, let's refresh the page to verify that it's been correctly uploaded. Okay, it's here now. So everything is set up to run the training. And what we need to do now is to do the same thing as we did before. So let me maybe clear this. Let's check our text file here that contains the necessary commands to run. So if you remember, we actually have model dir pointing to experiment 1. We need to change this. So for that, I'm gonna set model dir again. And here, in fact, even the bucket name, I had changed it. As I mentioned before, I actually made some experiments by myself. So let me just copy this, paste it. This should be experiment 2 and training process. And then I need to set the pipeline config file or path. Let me just check this. So echo this. Okay, it's actually pipeline config path. So let's set it again. Pipeline config path equals the name of the bucket, experiment 2, and then the name of the config file. So let me just, sorry, it should be, okay, it's actually here. Let me just close this. I opened it by mistake. Let's go here and check. Okay, it should be this. Let me copy it from here. And oh no, in fact, it should be here. Yeah, sorry, it should be this. Control A, Control C, and then paste it here. So now we have the two main variables configured here, model dir and pipeline config path. So let me clear this again, and let's go back to our script or to our text file that contains the commands, and let's verify if there's anything that needs to be changed. So here, Cloud AI Jobs Training, maybe we can change the name of the job. So maybe I'm gonna add SSD here, just so that I don't forget. So maybe this as well, so that when I see the jobs on my AI platform dashboard, I can know which ones were using SSD and which ones were using Faster RCNN very quickly. So I'm gonna add this here, and let's check. Okay, the runtime version for TensorFlow is 2.1, Python version is 3.7. The job there is this one, so where we will be saving the models checkpoint and also the events for that are saving the history of the training. Package path is .object detection. This is to let the AI platform know that we want to use object detection. This is the name of the script that will be run. So model name or module name, sorry, object detection .model name TF2. This is also for AI platform to know what it needs to use. The region, we're gonna keep the same region. Scale tier, we made it custom because the default value is not custom, and if you run it without this line here, then it's gonna use the default value, which is basic, I believe. And basic does not, you can't use basic with this type of machine here, so we need to change it to custom. And of course, for the machine type and the master accelerator, we're gonna keep these ones here because they are good enough for training. And of course, the model there again is set here, and the pipeline config path is the path that's pointing to our configuration file. So let me copy this and let's come here and paste it. Okay, maybe let's just verify one last thing before I run it. So gcloud projects list. Just want to verify okay. So this is the ones that we have. If I run gcloud init, we are using a different project. Yeah, that's what I was worried about. So because I did make some changes, I now need to set my project again. So the project should be object detection using TF2. Let's go back. Yeah, it's this one here. Object detection using TF2. So to set it, we need to write gcloud config set project, and then we need to give it the project ID. So I'm gonna take this from here, copy, and then paste. Let's run this, and now we have it set. Let's verify again. Okay, this is the project that we're using. Let me clear this again. Let's go back here, copy the command again, copy, and let's run this. So as you can see, sometimes you can forget some details, sometimes you can miss some specific things, but as you can see, you can always verify things before you run the training so that you're always sure about what you are doing. So as you can see, the training job has successfully been basically added to our list of training jobs on AI platform. And let's go back to our dashboard here and verify if we have that job here listed. So, okay, now we can see it. And as you can see, object detection SSD, we have it here. And let me just open it in a new window here. And I'm just gonna close these ones because we're not gonna use them for now. And here, okay, it has started. Let's open the logs here. And as you can see, it's basically the same approach as before. Now for the SSD model, the training should be faster because the network architecture is simpler than Faster RCNN. And while waiting for this to start, maybe we can run an evaluation job at the same time. So let's go back here and let's verify. Okay, for the evaluation job, we basically don't need to change anything. So I'm just gonna copy this command and here, just to mention something that maybe I didn't mention before. For the scale tier, we're using basic GPU. As you can see here, before we used custom. So custom, because we're using this type of machine, which is a more powerful machine. This is a basic GPU. So it's a GPU that's good enough for evaluation, since we're only gonna do evaluation each time a new checkpoint is saved. So I'm not worrying too much about the type of GPU for evaluation. So, okay, let's copy this again, paste it, and let's run this. And now we have our evaluation job added to the queue. If we go back here, let me refresh the page. We should see now 2 different jobs running. Yeah, so as you can see, we have this one for the training, this one for evaluation. Let me open this in a new tab, and let's open the logs. And okay, now we have the 2 jobs running, and as you can see, the machine, we already have a machine allocated for the training job, and things has started. So since everything seems to work correctly, I'm gonna leave them now for some time while the training and evaluation are running. And once this is finished, I'll show you the end results. Now that our training and evaluation for the SSD model have finished, let's take a look at our training and evaluation and see how they went. And for that, as you remember, we have everything saved in the experiment 2 folder here on our bucket. And if we go to the training process, we have 2 checkpoints, and we also have the train and evaluation folder. So the train folder contains events for training part and evaluation, or eval for the evaluation part. And let's maybe open a Cloud Shell in here. And we're going to run TensorBoard and see how the training went, and then also look at the evaluation part. So for that, let me clear this, and I'm going to run the train part here. But as you remember, this is in experiment 2, so I changed that, and I'm going to run it on port 8080. It's going to ask me to authorize, and I'm going to click authorize here, and now I have my TensorBoard running here. So I'm going to preview it on port 8080. And this is the result of the training of the SSD model. And as you can see, the training was smoother compared to the Faster RCNN model. And here we see that the loss functions are all going down, which is a good indication. And in fact, here we see it going down smoothly. And by looking at this graph, the first thing that I can say is that if I leave the training for a little longer, then maybe it can still go down. So when the loss function, or when the loss values keep going down, this means that the model will keep improving. So for me, I stopped it at step 1500, but I do encourage you to run it, to run the training for a longer period of time. So I believe this could improve the results even further, although I haven't seen the results yet, but I just know from this graph of the total loss that basically the model is still capable of learning. So that's how I interpret this result. When you see that the loss function is going down, and it's basically still wants to go down because it's not completely flat here, like we had in the Faster RCNN graphs, where we saw that for the last 500 to to 600 steps, it basically stayed at the same level. But here, I see that it still wants to go down. So if I had left it for a longer period of time, then maybe the model would have learned even more. But apart from this, we can say that the training went well. We don't see a lot of fluctuations. We don't see that the loss is maybe diverging, so maybe going up. We see that overall is going down, so that's a good training, I could say. And now that we have seen how the training went, let's go back. Let's clear this, and now let's run the evaluation. Again, I am inside experiment 2, and experiment 2 is for the SSD model. Let's run this. Let's go back here, refresh. And as we can see, these are the mean average precisions for large, medium, and small objects. Overall, from what we have seen in Faster RCNN, in fact, Faster RCNN had better results in terms of mean average precision, although it wasn't that different. It wasn't that big, the difference. But still, we see that the SSD model has these values for mean average precision. And again, step 0 corresponds to checkpoint 1, and step 1K corresponds to checkpoint 2. And these are saved in here. And we don't see any checkpoint 3 in here because the checkpoints are being saved after every 1K steps. And since we stopped our training at 1,500, then the step at or the checkpoint at that step was not saved. Of course, we can change this in our configuration file. We can choose the frequency of saving the checkpoints. But for our purposes here, we just want to run the training and see the results. So I would say this is okay. Let's go to the images and see how the model performed on the images. And here, I don't see what, I see that the problem, or I see that in this case, the model was not able to detect any images. The same thing for this image in here. Let's go down here. Here it was able to detect these two with low probability, so it's not even sure. And these 3 people were not detected. Let's see here. Okay, one was detected. This one was not. Okay, here it was detected, but even the probability is low. So what we can say, again, in fact, I have said this before, even looking at these images. When we looked at the training graphs, we saw that our model was still learning. It was still able to learn more, but I had set the finishing line at 1,500 steps. But if I had kept it for a longer period of time, then probably the model would have been much better than this. But still, I think it's a good thing for learning experience. Now you see what happens when your model is not trained correctly, or is not trained fully, let's say, because in here it is trained correctly. The loss function is going down. It's just that it's not trained fully. So it could have learned a lot more, but it didn't. Again, in this case here, we see that it only detected these 3 people. It missed so many of them. But still, I would say that that's the lesson we get from this experiment here. So now the hypothesis is it's either that the model did not learn enough and we could have left it learn more by setting longer period for training, or that the SSD model is not good enough for detecting these objects in this specific scenario. And that's for you to investigate. So what I would suggest for you is to run the training for a longer period of time and see if things improve. If they do, then the hypothesis of that, or the hypothesis that says that our model can learn more, is correct. And if you leave it for a longer period of time and it still cannot detect these objects here, then that would mean that our model was not, or our SSD model is not capable enough to make predictions on such objects and in such scenario. So that's for you to investigate, and I would very much encourage you to do that. And I would be happy to help you if you face any problems while doing that. Hello. So in this video, I'll be showing you how we will use YOLO v3 algorithm in order to train an object detection model to do the same thing that we did before, which is detecting masks on people's faces inside images. So for this specific part of the course, we will actually need a different code base so that we can train our YOLO algorithm, because in the object detection API, so if we go back to TensorFlow 2 object detection API, just to look it up here, they don't have the YOLO model as part of their graph or as part of their model zoo. So if we go to TF2 zoo here, let's look here. So as you can see, we have all of these models, but there is no YOLO model, no matter what the version is, whether it's YOLO version 1, 2, or until 4 and 5. So because of that, we actually need a different setup to train our YOLO algorithm. And for that, I have actually put together the code inside a repository on my GitHub account. So as you can see here, this is my GitHub account. And what I have done here is basically take a part of a code from the original repository, which is here. So this repository here is a big one that has many TensorFlow 2 examples. But for me, I only took this one, so YOLO v3, so only this code here and also the code for computing the mean average precision. I didn't want to fork the whole repository because it has so many things that we don't need in our specific task of training a YOLO v3 object detection model. So for that, I have only took the part of the code that's necessary for us, and that's why I added the disclaimer here. And I mentioned here that I took the code from the original repository and I made some minor modifications, because if you go here, there are some issues here that other developers have mentioned, and some of them are more pressing than others. And I noticed that the main contributor to the repository, so the owner, is not answering those issues. So I didn't want to basically just show you the original repository and then you're gonna face some of those problems yourself. I wanted to put together a simple guide so that you can just focus on the task, which is train YOLO v3 object detection model. So this is the setup that we will be using. If you go to my repository, so github.com/sniper0110/YOLO v3, you're going to get to this page. And this is the setup that we will be using. This is the code that we're going to use in order to train and evaluate our model. So the only thing that you need to do is to basically click here and download a zip, so that and then you put that zipped folder on your machine. And for me, it's already in here. So this is the code that's inside this repository here. The only thing that's different is are the weights here. So as you can see, I have some YOLO v3 pre-trained weights. So these represent the same thing as in the TensorFlow object detection API. If you remember, we had to download the pre-trained models from the model zoo. So in the case of YOLO v3, it will be these files here that represent our pre-trained model. And in order to get this, you only need to download the pre-trained models using this command here. So wget, and then you go to, or you just type this command on your terminal, and then you're gonna get the weights, and they will be put inside your repository here. Just make sure that you are inside the folder here, so that so what I mean by that is, when you go here, when you are inside your terminal, just make sure that you go to the place where the code is, so here, and this is where you should run this command here. So it should be something like this, and then you run it. I don't want to run it because I already have my pre-trained model on my local machine, so I don't need to do this. But that's what you'll need to do. And in the next videos, I'll show you the rest of the things that you need to configure. Another thing that you need to set up correctly in order to train your YOLO v3 deep learning model is to install the right requirements. So the requirements are basically all the Python packages that you will need during the training and evaluation. And for that, there's already a requirements.txt file inside this folder called docs. So this requirements.txt file has these different requirements here. And as you can see, TensorFlow is not mentioned here, but we already have TensorFlow installed on our machine. So if you remember, the first thing we need to do is, again, to activate. Okay, let me just clear this first. Then we need to activate our Conda environment. So it's TF2 GPU. So now, as you can see, it's activated because we see this thing here. So let me clear it. And we already have TensorFlow installed here. And probably you already have many of these already installed as well. So maybe NumPy, maybe Pillow as well. The rest, if you don't have them, you just basically, when you run this pip install command here, so pip3 install, you can use pip3 or pip, it doesn't matter here, because we only have Python 3 installed in our virtual environment. So if you run this, then all of the necessary requirements will be installed in our local, or in our virtual environment, sorry. So that's basically the only setup that you will need to do for this. And I think I made some changes. I can't honestly completely remember whether I made some changes regarding the requirements.txt. Because in the original repository, I believe he had maybe the specific versions for each package, but I removed that because that could pose a problem for you, some dependencies problem. So if you just leave it like that, so if you just use my requirements.txt file, then you should be fine. And now let's look at our data set and the necessary changes that we need to do in order to train our YOLO deep learning model. So as you remember, in our annotations file, the CSV file, we had our data organized like this. So each time we have the name of the image, and then we have the width and the height of the image, then the name of the class, so it's either mask or no mask, and then we have xmin, ymin, xmax, ymax, representing the 2 points of the upper left and bottom right of the bounding box. So this is how the data is organized, and as you can see, for each new object in the image, we go to a second line and a third line, and each object is basically represented in one line here. So if the image has 5 objects, then we will have 5 different lines where each time we have the same image name, and then we have the width and height, the class, and the coordinates of the bounding box. So this is how the data is organized here. But for training our YOLO algorithm with the current code base that we are using, we actually need to transform our data in order to look like this. So the difference now is that first we actually need to have the full path to the image. And in fact, the first thing that's even different is that now we have a TXT file instead of CSV. So we don't have the first line that represents the names of our columns, so file name, width, height, so on and so forth. We start immediately by putting the data in place. So each time what we have is the full path to the image, and after that we have the coordinates of the bounding box, which stays basically the same, so x min, y min, x max, y max. But then we actually need to add the label here. So 0 basically in our case represents mask, and 1 would represent no mask. And another difference is that now in one line, or basically at the first time we write the full path to the image, we add all the different objects in that image, one after the other, separated by a space. So here, as you can see, we have the image, then we have a space here, and then we write the first object in that image, and then we have a space here, the second object, third and fourth and fifth. So now, as you can see, we don't represent each object in a separate line, but rather each image or all the objects in one image are represented in one line. So the same thing goes for all the other images. So as you can see, there are a few differences here compared to what we had before. Now we have the full path, we have our labels, and as you can see also the labels are starting from 0. So for mask, we're gonna choose 0. For the no mask, we're gonna choose 1. In the case of TensorFlow Object Detection API, we actually don't use the label 0 for one of our classes because the label 0 is used for background. So here there are all of these differences, but it's not that different from what we had before. But in order to train our YOLO v3 deep learning model, we actually need to transform the data that we have from this form here to this form here. So let's look more into how to prepare our dataset in the next videos. One problem that we have in our annotations.csv file that we had before, or that we got before, is that some of the image names actually contain a space. So here maybe I can't see it, but when I was doing it in code, I realized that some of them actually contain the space. So that poses a problem for us because the way that the current code that we will use for YOLO is made is that it's gonna try to separate between the different parts like here by looking at the spaces. So it's going to use the space as a delimiter in order to distinguish between the image path, the coordinates of each object, or the coordinates of the bounding box for each object. So if there is a space in the image name, then that would create a problem for us, because when the program is going to try to separate between the file name, the coordinates of the bounding box, so on and so forth, it's gonna face a problem, because if it separates, for example, the image here, let's suppose we have a space in here, then what's gonna happen is that it's gonna think that this part here is the file name, and this part here is somehow the first coordinate, so xmin of the bounding box. So let me just confirm. Yeah, so it's xmin of the first bounding box. So that would be a problem if the code tries to find the different parameters based on the space. So for that, what I have done, in fact, is that I created a specific script that reads the annotations from this file and saves them in a new file, and also it changes the names of the images. If they contain a space, it removes them. So this, we will look at it a little bit later, but first I'll show you something in the next video about the source of the data that we used before, and whether we can get our annotations from that source as well. So if we go back to the source of where we got the data set in the first place, so as you remember, we got it from this website, public.roboflow.com, and this is the full URL to the data set. So here what we did was basically click on row, and here we got some of the possible representations of the annotations. So for the object detection API, we downloaded the TensorFlow object detection CSV here. So as you remember, you click here, you click continue, and then you get this path here, and then you can just click on your zip file and it will be downloaded to the local machine. So let me cancel this because we already did this. But as you can see here, we actually have the possible representations here, YOLO v3 keras txt. So if we download this, let's say we do the same thing as before, and let's download this, and let me just let it finish downloading, and I'm gonna go to show in folder, so in my downloads folder. So here, in fact, I already have it here and it's unzipped. So if we go inside, and we're gonna have the same thing as before, 3 folders containing the different images for train, test, and evaluation. And here, if we look at the annotations file, so now we have a txt annotations file. So let me just maybe change its name to YOLO v3 annotations. So if I open this, so as you can see here, we basically have a part of the dataset already created for us. So we have the name of the image, and then we have the coordinates of the bounding box here. So the first thing that we notice, the first thing that's different from the dataset that we need for training, is that we only have the image name and we don't have the full path to the image name. So this could be a problem that's easily solved. We can just maybe change or add the full path here, or just we can choose where to run our training script from, and or we can change that in the code so that we don't need the full path anymore. We just need the names. But again, this doesn't solve the problem of where we have spaces in our image names. So here there are many images. I can't remember all of them, but I remember that one had the parentheses and something else maybe. Let's look at them. Yeah, okay, let's take this one for example. As you can see here, this is the name of the image, but there is a space in here. So this space is contained in the image name. So what happens, or what's gonna happen, is that when the script is gonna try to read the annotations and the image for this specific data point here, is gonna look at this and it's gonna try to split the line based on the space. So it's gonna try to split this space or this line here starting from here, and this is gonna pose a problem because then our code is gonna think that this is the file name, this is the image name, and then this is the first coordinate of the first bounding box of the of an object in the image. So as you can see, we still can't use this data set, although it's almost prepared for us. So if you think of an easy way to change this and to solve this problem, either in the code or going through the txt file here, then of course you can do that. But for me, I chose the other path where I just go to my annotations.csv file here, and then I transform this data from this form to this form. And since I am transforming the data, I have control over how I save it. So basically what I did was remove all the spaces in my image names, and that made things a lot easier, and it made them consistent with the way the code is going to read the dataset that we provided with. So I just wanted to show you this and to show you that there is this option here. It's just that it doesn't solve the problem of having spaces in the image names. And with that, let's go to the next video and let's see what we can do more. So in order to transform our data from this form here or this format here, so where we have the format that we use for Faster RCNN and SSD, in order to transform this into this format here, that is the necessary format to train YOLO v3 with the current code base, we actually need a specific set of transformations that we can do using a script that I have put together, and you can find this script on the repository that I have shared with you. So if we go back here, let's look here. So this script here, prepared data. So this script here basically does the transformation for us. So what I have done here is just I take that CSV file. So I take the, sorry, not this, I take the CSV file that contains the annotations like the one shown in here. And then what I do is first I just parse the CSV file. So I read it and I go through all the data, and I construct a data structure, a dictionary basically, that has as a key the name of the image and and then as values I have a list full of detections such as shown here. As you can see here, I read the file name and I use it as a key in order to add all the detections inside that inside the values corresponding to that key. So what we have here is maybe let me just write it here. So what we have is basically something like this. It would look like this, and here we will have the image name, and then we will have a list that contains a set of detections. So detection 1, so that would be let's just call it detection 1. Then another list, detection 2, so on and so forth. And each detection will be something like this. So detection 1 would be equal to this one here, something like this. So at the end, what we will have is this dictionary here, and I have created another function that basically takes the data that we get from parsing the CSV file and also takes the path to the images, so wherever our images are stored, and also it takes a path here that we define, and what this last path represents is basically where all the generated annotations will be saved. So where this file here will be saved, and also the new images that don't contain any spaces. So what we do here is just go through the data that's inside our data variable here, and just what we do is we take the image or the path to the image and the image name, and what we do is replace the spaces with nothing so that we remove those spaces, and then we construct a path to where we want to save that new image. So basically the path will be just the output path, so the one we define here, and then we concatenate with it the name without any spaces. And I tried to use the names for the variables so that they can be easily understood. So that's what we're doing here. We're creating this path to the output images, and then we're just copying that image that we have from the original source. So at this point, it's an image that has a space in its name, and then here it's copied to a new directory where its name does not contain any space. And then I just write the detections in the same line. So what I do here is of course, I have created this file here. I open it here, and I open it as an A+, which means append to the file. And of course, I had defined I have defined a text or a text file that's called annotations.txt. And what I will do is use my file that I created here in order to fill it with all the paths to the output image. And then I add the detections here, as you can see, xmin, ymin, xmax, ymax. So at the end, what we get is something that looks like this. So we have the full path, then we have the detections right next to it. And then when we finish the detections in one image, we jump we go to the next line. So that's why I have this line here, which means basically go to the next line. So whenever I finish all the detections in one image, I go to the next line and I start again with a new image. And I do this for all the images in my data. So now let's transform our data as I have mentioned before. And for that, as you remember, we have 3 different folders, one for training, one for test, and one for validation. But what we're gonna do is, okay, let me just maybe remove this from here. So what we're gonna do is combine these two, so train and valid. We're gonna use both of these folders. So basically all the images with their corresponding annotations in these 2 folders, we're gonna use them for training. And then the test folder, we're gonna use these images and their corresponding annotations for testing. But first, we need to go through each folder here and transform our data. So the first thing is we're gonna make sure that all the image names don't contain any new or any spaces, sorry. And apart from that, we're gonna change the annotations from a CSV to a text file that contains the path to the full path to the image with its corresponding objects in one line. So for that, we will just run our script, and the script is called preparedata.py. So for that, I'm just gonna use a terminal here. I have activated my Conda environment here, And what I'm gonna do is just run Python prepare data. It should be prepare data.py, and then I'm gonna give it the paths or the parameters that are shown here. So we have three parameters. The first one is path to images. So we're gonna do this for each of the folders here. So let me just maybe create this so that I can see the names of the parameters. So the first one I'm gonna use is the train folder. So all the images are inside the train folder. And then I'm gonna pass the path to CSV annotations. And this would be the CSV annotations inside this folder here. So it should be this one. So I'm gonna just drag and drop it. And finally, we need a path to save output. So this folder will contain a set of images with their names not having any spaces, and also is gonna have a text file that contains all the annotations, but they will be in a format that is consistent with our code that we're gonna use here. So for that, we can just choose wherever we want to save this. Maybe for me, I'm just gonna create a folder here. I'm gonna call it YOLO data, or maybe YOLO v3 data. And I'm gonna use this folder here. And maybe, in fact, let's create a folder inside of it called train. So that folder does not exist, but it should be created once we run the script here. And with this, let's run the script and see what we get. So the first thing we see is that we have a folder called train that was created here. And then it says it's done saving the annotations. So if we go to this new folder, we're gonna see the same images, except that now any image that had a space inside its name, that space is removed. So apart from this, we have a new file called annotations. And this file here, if we open it, we gonna see that it has the annotations in the format that we need. So the full path to the image, and then we have the bounding boxes and their corresponding class. So 0 is for mask and 1 is for no mask. And each image will have all of its objects in the same line. So now for the train folder that's finished, let me just close this. Let me go back here and open these ones here. And I'm gonna do the same thing for the other folders here. So I'm gonna run the Python prepare data.py, and I'm gonna give it the path to images. So path, I just forgot the dash path to images. Now I'm gonna give it the valid folder here and the path to CSV annotations. This should be the path to the CSV file that's in here. So this one, I'm just gonna drag and drop it. And finally, the path to save output. And for this, I'm gonna use the same folder. And here, I'm gonna call it valid just for now, because then I will mix this data here with the training data. So I'm gonna call it valid. And let's run this script here. So now we have our new folder that's created here. And what we can do here is just move all of these images to this folder here, so that we're gonna use all of them in training. So let me just get everything except the annotations file. So I'm gonna move them to the train folder. So I'm gonna move them here. And then I need to move the annotations here. So all of these annotations, Control A, and then I'm gonna do Control C. I'm gonna remove this, and I'm gonna go back to the training folder and open the annotations file that's in here. So let's look for it. It's here. So I'm gonna add these annotations at the end in here. So let me get to a new line here and just paste the rest in here. And I'm gonna save this. So now what we have is this folder that contains a set of images with their corresponding annotations. And I'm just gonna change the name here to call it mask annotations. And I'm gonna go here and just remove this folder completely. So now this data here will be used for training, and we're gonna do the same for the testing data. So let's just open this here again, and let me do again Python prepare data.py, path to images. I'm gonna use the testing folder, and then path to CSV annotations. This will be this file here, and finally path to save output. And this I'm gonna do the same thing. So here, and this should be in a new folder called test. So let me just run this. Since we don't have a lot of images, they will be saved quickly. So if we go here, we see we have a new folder with these new images and also the corresponding annotations here. So let me change this to mask annotations. In fact, maybe we can call this test mask annotations, and this should be train mask annotations. So I'm gonna do train mask annotations just so that we distinguish between the two. And these ones will later be moved to the folder. Let me look for it. So in our code base, so where we have all of our scripts, if we go to data, then dataset, we should move our annotations file to this folder here. For me, I have already done this before, so I already have them here. You see train mask annotations and test mask annotations. So these files will be the ones that are used later. So the script will read from them. When it's going to read from them, it's going to see that we have the full path to the images and then their corresponding bounding boxes, and that should be enough for the training. So with this, I believe we have everything, at least from a dataset standpoint, we have everything ready. So let's see what we can do in the next video. Another thing that we need to add in order to create all the necessary configurations for the training is to define something that looks like a label map. So in TensorFlow Object Detection API, we have a label map. And in this code base, what we need to do is, if you go to the folder data, then you go to classes. Here you actually need to create a file that's, you can give it to whatever name that you like. The convention here is just to call it, to add .names at the end. So you can, it doesn't matter if you want to call it something else, but inside this file here, what you need to set up is just the names of your classes, each line needs to have one name. So mask will be the first one and no mask will be the second one, since we only have two classes. So for you, whether you're on Ubuntu or Windows, the way you need to do this is just to create a text file and add these lines to it. If you're using your own data set and you have several classes, then you just add class 1, then the next line, class 2, class 3, so on and so forth. So this is also something that's necessary when doing the training. So it's a simple step, and that would be it for this specific step. And the last thing that we need to set up is basically setting up all the configurations in the config file. So again, this looks very similar to what we did in the, or what you would do in the TensorFlow Object Detection API. So here in our code base, if you go to data, or not data, sorry. If you go to core, and then there is a Python file called config.py. So if you open that, what you're gonna see here is basically a bunch of parameters that you need to set up. And these parameters will be used during the training and evaluation, as you can see. So this part here is for the training options. This is for the testing options. When I say testing or evaluation, it's the same thing. So here, the parameters that you need to set up is, the first thing is the path to your classes file. So the file where we defined our classes, where we said mask or no mask. So this file here, wherever you have put it, you can you need to point at it here. And for us, since we are putting everything in our data folder here, we can just point at it. So from here, we just say data. In our case, it's in data, then in classes, and this is where our names are defined. So if you put it somewhere else, just change the path to that specific directory. And another thing that you should change is the main things that you need to change is the path to your annotations file. So as you remember, in a previous lecture, I showed you how to change our data set in order to fit the current setup that we are using. And for that, we got a file that looks like this for the training, and also another file that looks like this for testing. So those files, you can put them anywhere you want. You just need to point at them. But for us, we're keeping the same methodology, and we're putting them inside data. So data, then data set. And here we have our file. So train mask annotations. As you can see, it's here. It's the same file that that I showed you here. And apart from this, let me go back to the config file. So this would be the path to your annotations. And again, we're not pointing to the images paths here, because they are in fact the paths to the images are mentioned inside this file here. So if I go back to this file here, you'll see that we have the full path to each image. So that's why we don't need to point to where the images are. So everything necessary for everything related to the dataset is inside this text file here. So apart from this, this would be the main parameters that you need to change. But of course, we're going to go through some other parameters that would be important for you when trying to improve your model and while doing your experiments. So the first parameter that's very important in your experimentation would be the batch size. So here I'm only using a batch size of 2 because on my local machine I don't have a good GPU, so going beyond this might get me an out of memory error, so I'm only using 2. If you're using a better GPU, then you should definitely change this to a higher value. And another important parameter would be the number of train epochs. So if you remember, or if you have used TensorFlow Object Detection API, you realize that in our configuration files in the TensorFlow API, we didn't actually, or we don't set the numbers of epochs. We actually set the number of steps. So what the difference here is that for epochs, what this means is that how many times do you go through all of your data? So if, let's say in your training data, so let's say train data, you have something like 200 images. So if you have 200 images and your batch size, let's say, is 2, what this means is that now you actually get 200 divided by 2, so 100 steps to finish one epoch. So what this means is that you actually need 100 steps in order to go through all your dataset once. And going through all your dataset once is equivalent to one epoch. So here, when you are defining the number of epochs, you're basically defining the number of times you go through your dataset. You go through the whole dataset. So this translates to whatever number of images you have in your training set, and this is of course computed automatically. You don't need to set it anywhere here. So whatever number of images you have, if you divide it by the batch size, you're gonna get the number of steps needed for one epoch. And when you set this value here, this means how many times you want to go through your data set. So here I am setting 100. You can change this to whatever value you like. Usually you should use at least 30 or 25 epochs if you just want to test things. But if you realize that your training or your loss function is still going down, then maybe adding more epochs could improve your results even more. So this is another important parameter that you can change. There are other parameters here, but for now I wouldn't recommend changing them. But let's just go through to some of them and let's explore them. So here the input size is the input of your neural network. I recommend that you leave it to 416. You don't need to change this, but you have the ability to change this since you have a set of convolutional layers in the beginning, so changing this will not matter that much. But if you increase it a lot, then I believe your results would decrease. This is based on what I have seen on the article from the YOLO team. Another parameter that you can set is the data augmentation. So here, if you set it to true, that means you want to use some data augmentation in your training. So I definitely recommend to keep this set to true. And there are some other parameters like the learning rate. So here, why do we have two different parameters? There's the learning rate init and learning rate end. So this is the initial learning rate and this is the end learning rate. And basically there is a function, there is a cosine function that changes. And also we have a certain parameter where basically what this function does is it goes down from this level to this level while the training is moving forward. So the more training you do, the lower your learning rate becomes. And this is one of the things that you see in many deep learning papers. So some of them keep the learning rate fixed, but a lot of them actually make it change in some sort of way so that the learning rate decreases while the training is moving forward. So let's see other parameters as well. So here we have a path to a text file that contains the baseline anchors. So these are the anchor boxes. This represents the same thing in the Faster RCNN terminology. So you have baseline, so you have anchor boxes that we will use during the training. So this is inside data anchors, baseline anchors. And here, as you can see, we have a set of different anchors here, and they represent many different anchor boxes. And of course, this represents the same terminology as in the Faster RCNN case. So when you have more anchor boxes, then what you will have is maybe a training that would take a little longer, but of course you're going to take so many different cases into consideration since you take many different anchor boxes at the beginning. So apart from this, let's look at the other parameters. Here, I wouldn't suggest changing any of these parameters. You don't need to do that. Each one represents a different thing. For example, the IOU loss threshold, this is just the intersection over union. So when it's the same thing in the Faster RCNN or SSD cases where we need to set up a certain threshold when we compute that ratio. So 0.5 is good, so you don't need to change it. You don't need to change the strides. I believe these are the same as in the original YOLO paper, so you can just keep them like that. And if you go down, okay, let me just see, okay, up, we have mentioned almost everything. And in the test options, you need to do something very similar. So here, you need to point where your annotation data is. So again, or where you annotated the data is, but this path here should point to the data that you want to use for testing. So not the ones for training. And the same thing, we actually have that data in our data set, and it's called test mask annotations. And again, it's the same thing. We have the path to the image, to the images, and then we have the coordinates of the bounding boxes inside that image. So these images here and this data here is not contained in the training data. So when you finish training your model, you should test it on these sets or this set of images, and this will give you an idea of whether your model is generalizing well or not. So let me close this. And here as well, you have the batch size. You can choose whatever you like. I have chosen one here. Since I only have a few images, so and I'm only doing evaluation here. It doesn't take long whether I use one or two, so I just kept it one. The input size, we're keeping it the same, 416. The data augmentation is set to false because we don't really want to use data augmentation during testing phase. We want to test the model on data that looks like the real life data. So let's not use data augmentation here. This path here, detected image path, this is the path where when we do the final, when we do the testing, so when we run the testing script, it's gonna do some testing on all of the images that are mentioned in our annotations file here, and then it's gonna save them with the annotation inside this folder here. So what this means is that we're gonna get a set of images that have bounding boxes on them inside this folder here. So just think of it as the path where your detections or your final detections will be. Other parameters are the score threshold and the IOU threshold. I suggest you keep these, or at least this one, you can keep it like this, 0.5. It's a convention used by researchers. But for this score threshold, what this threshold represents is the confidence score. So what this means is that when you are making predictions, you want your model to keep any predictions that have a confidence score higher or equal to 0.3. So sometimes, for example, in the industry where I used to work, when I want to keep only the most confident scores, I would increase this to a higher value, something like 0.8 or even 0.9. So for now, we're just going to keep it to 0.3. We just want to see as many detections as possible. But of course, if you are in the industry, you should probably increase this a little bit more because you don't want to make detections on some objects where the model is not confident enough. So these are the parameters in our config file, the main parameters. And as you can see, they are very similar to the parameters that are known in the TensorFlow object detection API. And it's good that we have something very similar. This keeps things into perspective, and we basically keep the same level of understanding. The one that you use for TensorFlow object detection API, you can use it here as well. So with this, let's go to the next video and see what we can do then. So now that we have everything ready to start the training, if you have set up everything in your config file, the only thing that's left to do is to run the training script, and that would be train.py. And again, just make sure that you are inside the folder that contains all of these scripts. So you need to run this train.py file from within this folder. And here we can run the script, and it should show us that the different steps are running while the training is moving forward. So just to mention a point here that I forgot, in fact, to do. So here, when I transformed my data, as you remember, I moved all of the data from the valid folder. So this folder here, I moved all the data to the train folder, but I did not change that in the corresponding annotations file. So basically now what we need to do is change the, okay, let me just see. So in the train mask annotations, if I look for valid, you can see that all of these images here are shown to be inside the valid folder, but in fact we have moved them to the train folder. So we actually need to change these values to train. So let's just do this quickly here. Sorry about this, just that I forgot to do this before. So I just finished changing all the names valid to train, and there weren't that many, so it didn't take more than maybe a minute or two. So let me just save this, and let me just maybe look at the go back to my terminal here and run the script again. So let me just clear this, and I'm gonna run my script again. And hopefully now there shouldn't be any problem since all the paths are correct. So let's wait and see what we get. So now the training has started. So if you see these steps here, this means that the training has started. And this is the value of the total loss. So you can just follow this one here to see whether the model is converging or not. So if you see that the loss function is going down, then this is an indication that the model is being trained correctly. So of course we have chosen 100 epochs, so this could take some time, especially that we are running it on, I am running it on my local machine, and I don't have a very good GPU, but if you do, this could take maybe less time than me. But for now, let's just let it train and see what we get at the end. So after a while, basically for me, it was 6,700 steps. It took maybe around 2.5 hours to finish all of these steps. Now my training is finished, and again, the model will be saved in the directory where you have all the code. So this or these 3 files are the ones that have been generated from the training. And also during the training, we were saving the events files, which are the files that contain the progress of the loss function throughout the training. So in order to find those events file, you need to go to data and then to log. And this file here is the file that saved all the history of the training. And we will use this file to visualize that progress using TensorBoard. So for that, what we can do is run a TensorBoard. Let me just maybe create a new terminal window here. My PC is a little slow now. Usually this happens when I use a lot of memory during the training and then it stops. So let's just wait for this to open. And now that we have this open, we can run TensorBoard, but after we activate our environment. So let's use conda activate tf2 GPU, and then we can just run TensorBoard. So again, TensorBoard is a tool that basically helps us visualize the progress of the training using those events files. So for this, we need to give it an argument logdir, which should point to where the event files are. So since they are in the log directory here, we're going to just drag and drop this, and let's press enter. So now we see that our TensorBoard here has given us this URL that it tells us that things or the plots are shown in this URL here. So I'm just clicking on control, then clicking on this URL, and it should open in the browser. So these are the plots for our loss functions during the training. The main one that we should look at is the total loss. So the first thing that we can notice is the oscillations. We have so many oscillations. This is mainly due to the very low batch size. So of course, because I don't have a good machine, then I can't go beyond 2 images per batch. But if you have a better machine, and if you train on the cloud, then you can increase, or you should increase, the batch size, and you would have something much smoother. Maybe it would look something like this. So this would be, if you have a graph like this without much smoothing, then you can say that you have a good training. But for us, we can't really say that. We have so many oscillations here, and this usually translates to a model that's not very good. But still, these are the limitations. And if you are working in the industry, you should definitely try to improve your machine with adding better GPUs, or you can just move to the cloud, because the final model that you can get with a larger batch size can be significantly better than the model that's trained on a machine with an average, let's say, GPU. So this is the main thing that we notice, but also something else that you should notice is that overall the loss function, especially when we talk about the total loss, is moving down. So usually in this phase, I like to smooth things just to get a better intuition about the overall progress of the loss function. So here we can clearly see that the loss values keep going down, which is a good indication that the model is training well. So we don't see a divergence. We don't see that the loss function is going up. We don't see it, for example, staying in one level. We see that over time, it's actually going down. So this is good. It also means that the way I see this, I see that there could be a possibility where the loss could go even lower than this. So for this, what this means is that I could have, for example, left the training for a longer period of time. So as you remember, for our number of epochs, I have chosen 100. I can probably increase it to 150 or even more because I see that the graph tends to keep going down. So if we plot some line like this, we see that it's still going down. So if the loss values keep going down, this means that your model is still capable of learning more. But for me, I'm just gonna leave it at this phase here because, again, because of the fluctuations here, as you can see, this means that I am not getting the best model possible. This means that also the way that we are moving or the way we are basically getting down in the gradients at the gradients level is not really good because we're making steps in different directions. This is what it means for me when I analyze this. It means that when we are trying to go down to find the global minimum, we're actually moving in different steps, in steps in different ways. We're not getting steps that are more forwarded towards the downhill of the gradients. So to me, this is not the best possible model or the best possible training. Just by increasing the batch size, I am sure that I can get a much better training than this. It would probably look something like this or even like this. So an example like this means that the training was much better. So again, we are training on the local machine here. So my local machine is not that good, but still when I see this, at least I know that everything is working correctly. And if I want to improve things, I know which things I should focus on. So this would be it for analyzing the development of the training. And as I mentioned, you have so many parameters that you can work on in order to improve your training, including or starting with the batch size. So once the training is done, what we're gonna get is the model weights, so the checkpoints that will be saved in our directory where we ran the training script. So this is the training script, and it's saving the checkpoints here. So this, and this, these are the three files that were generated by the training script. And now what we can do is run the testing or evaluation on our test data. So as you remember, we have a test data here, and this is the test mask annotations, which is a text file that contains the paths to the images and their corresponding objects in one file. So we're going to use this data here in order to run our evaluation. And for that, what we need to do is to basically go to our path here, or to our directory here where we have all of our code. So if I do ls here, you can see we have the training code, and we also have the checkpoints that were saved. We have the test.py file. And in order to run the evaluation or the testing, you don't need to set up everything. If you have already set up these parameters in your configuration files, so if you have pointed to where the test annotations will be, and also to the path where the output images will be, then you don't need to set up anything else. So for that, let me just clear this. And to run the testing or the evaluation, we need to run the script test.py. And in fact, before I do this, as you remember, we have installed everything inside our virtual environment, so we actually need to activate it, because if we run the script here, some Python packages will not be recognized. So for this, let me just use conda activate, and then my environment is called tf2 GPU. So now I have my conda environment activated. Let me clear this, and let's now run the script test.py. So with this script, it should go through all the images. It should make predictions using our model or our trained model. And as you can see, it's doing the detections here. And it should save all of our detections inside this folder here. So it's data eval detection. So if I go to data, and then I go to eval detection. So here, as you can see, we have a new set of images. If I click this one here, as you can see, we now have our images with these detections on them. As you can see, the images are shown in a color that looks a little bit weird. They're different from our images in the original data set, but this is mainly due to OpenCV and how we're saving images in OpenCV. This is not something to worry about, just how OpenCV reads images then saves them. So here, the main thing that we need to focus on are the detections. So we can see that our model was basically almost able to detect that this person is wearing a mask. Also, this person here, we have two detections here. We see that it was able to detect this person here, and we have some false predictions in here. So I didn't expect the model to be very good. I know this because the set of parameters that we used, they didn't allow our model to become as good as it can be. For example, the batch size we only use 2, and that's a low value for the batch size. That's why our loss function did not go down very smoothly. So let's look at other images as well. In this case, we see that the detections are more or less good. So all of these people are wearing masks, and we can see that it was able to detect all of them correctly. Here we see that this person has 2 detections on his face. This could be improved by playing a little bit on the score, on the IOU threshold here. So if we increase it a little bit, we can remove this kind of double detections. But for now, I think this looks good. And let's go to the next one. Here as well, we see that it was able to detect that these people are wearing masks. Here, we see that it was only able to detect that this person is wearing a mask. It couldn't detect the other people. So this is a case where YOLO has failed. Here, we see that it was able to detect these people are wearing masks. And also, in fact, this is a good detection here where we can see only a partial part of the face, but it still recognizes that this person is not wearing a mask.
The same thing goes here. This person is not wearing a mask. This is good. This is a mist detection. So this person here, I believe this lady here looks, her face is more clear than this lady here. So the model should have been able to detect this, but it couldn't. So this is a failure from the part of the model. Here we see it was able to detect, again, with the problem of double detection. Here as well. Here it was able to detect a lot of faces, so this is very good, I would say. So as you can see, the model is not perfect, but still it's good enough. So if we just play on the parameters part, we can improve this dramatically. And if we run this training on the cloud and we increase the batch size and we train for a longer period of time, then we can get probably a model that's much different than this model here. So for this part here, as you can see, when testing on our test dataset, we see that the model is behaving more or less as it should. Of course, it's not perfect, but we know that there is a lot of room for improvement by working on the different parameters and also by training on a better machine. So with this, I will end this video, and let's go to the next video and see what we can do more. So when we ran our testing script, of course, it gave us those images where we had the detections. So images that basically had all of the testing images with bounding boxes on them, but it also did something else. So when we ran the script, it actually saved some text files in the folder called ground truth and also some text files in the folder called predicted. So what these text files represent is, let's take a look at them. So here we have, for one of the images, we have this detection here. So the object was masked, and this is these are the coordinates of the bounding box. Sorry, this is the ground truth. So this is the ground truth for all the images in the testing dataset. So here, each one of these images, we basically saved the coordinates of the bounding box in a text file. And then when we did the prediction, we saved the predicted bounding boxes on or inside this folder here. So here the ground truth that was extracted from basically the annotations file that we had. And this is the predicted, which contains the values after we run the testing on our test dataset. And these folders here, we now are going to use them in order to compute the mean average precision. So the mean average precision is a value that tells us how good our model is. And for that, let's take a look at the scripts that we have here. So if I do ls here, there is a folder called mean average precision. So if I do, for example, ls mean average precision, I can see what's inside of it. And here we have some Python files and also a folder called results and a folder called temp files. So this Python script here called main.py is used to compute that mean average precision and also some other metrics, but the main thing that we want is the mean average precision. So let me clear this and let's run it from here. So Python mean average precision main.py. Again, I am inside my virtual environment here. So just make sure that you run this script from within this folder YOLO v3, and you don't need to cd to mean average precision to MAP folder, because this could pose some problems when you're running the script. But if you run it from here, there shouldn't be any problems. So here, let's run it
and let's see what we get. So as you can see, we get this image here that shows us the mean average precision. It shows us the average precision for objects with the class mask, and also the average precision for the objects with the class no mask. And as you can see here, the average precision for this class is very low. And of course, this plot here is for the testing data and not the training data. So here, for this class here, we see that the average precision is very low, and this is due to so many factors. One of them is that we don't really have that many images or that many objects in images where people were not wearing masks. So if the model misses a few, then that's gonna be very costly in terms of average precision here. And this can be improved by, for example, adding more images during the training for people who are not wearing masks. So you can just collect a set of images of people who are not wearing masks, and I believe this could improve the model's performance much better since it starts to see more the people who are not wearing masks, so the model can learn more what that looks like. Because in our data set, we don't have many people who are not wearing masks, so we can't, the model is not learning enough features to be able to distinguish the people who are not wearing masks easily. So this is just another very important parameter that you need to consider when you are developing your model. And the mean average precision is just the average between these two here. That's why we get something like 34%. It's basically half of this value here because this is very small value. And this value here is an important value that you need to work on so that you can evaluate whether your model is becoming better or worse. And these values here basically give you some specific indications on on where your model is making more mistakes or not. So if I see this, then I probably wouldn't worry that much about the part of the model that's detecting whether people are wearing masks or not. But I would definitely worry about the part where people are not wearing masks, because we see that the model is missing a lot of people here. So with this, that should be it for this video, and see you in the next video. So when we ran our main.py script here, we got the mean average precision as it's shown here, and it was also shown on that output image. But we also got some other results, and in order to see those results, you need to go to the folder results. It should be created in your local folder. And then inside of it, we can see the predicted objects info. So this image here tells us how our model behaved in terms of specific number of objects that were correctly detected and also that were falsely detected. So for the masked object, we see that we have 44 different false predictions and we have 69 true predictions. So this can show that our model maybe is making a lot of false predictions, and it's also doing many good true predictions, but we have a lot of false predictions. So maybe one of the things you can focus on is how to decrease this number here. So for example, just by playing with the config file here, so if, for example, you increase the score threshold, if you increase the IOU threshold here, then probably this number will go down. But the main problem that we see in this plot here is for the second class, no mask, where we have a lot of false predictions and very, very few true predictions. So this means that the model is not really doing good on this class here. And again, if I go back to the same thing that I said before, in order to improve this, for me, one of the straightforward ways would be to add more images that include people's faces and people who are not wearing masks. And if I increase the number of these objects in my data set, this can probably improve the results a lot. So I just wanted to show you this plot here as well. And as you can see, now you have two different plots that you can use for evaluating your model and understanding how it's behaving. So you have this plot here that gives you specific numbers of false predictions and true predictions. And also you have the other plot, which gives you the values of mean, average, precision. So with this, we have finished the part of analyzing the results, and let's see what we can do next. In this video, we will be talking about how to transform our model, so our checkpoints, in order to get a model that's ready for deploying in production. So when we did the training, what we were saving are actually these files here. So these three files, they represent the checkpoints. And usually these files are used to do the training. So if you stop here, maybe if you want to start the training again later, then you should use these files here. But in terms of production code, usually we don't use these files. We actually transform our checkpoints into what is called saved model format. So it's actually, if we look at it, saved model format TensorFlow. So as you can see, it's actually written like this. So using saved model format, and this is the format that's used for TensorFlow 2 models in production. So as you can see, it's one word called saved model. And in order to do this, what we actually need to do is basically just load our checkpoints and then save them using the function save. And that function will save our model as a set of folders and files that are used for production. So here, this script that I have quickly put together, what I do here is that first I basically grab the input size, the number of classes, and the names of classes. In fact, I don't think I need this one here. Sorry, I just added this. I don't really need it. I just need the number of classes. So what I did was getting the input size and the number of classes from the configuration file. So the configuration file is the same file that we used before. So I'm just looking at the part here, taking the input size, and also the we're getting the number of classes using the computation of how many classes we have. As you remember, in our file or in our data here, if we go to classes, mask or no mask, so let's open this. So as you see here, we have two lines, so that means we have two classes, and that's how we're getting the number of classes here. And then we're just constructing the model. We're building it the same way that's built in the code base. So we're just getting the inputs, creating the model using the class YOLO v3 that exists in the code base. And then we're just basically constructing the model here. And at this point here, we're loading the weights. So here we're actually loading the, let's go back and look at them here. So we're now actually loading these files here. So these three files, we're loading them. And then the only thing we're doing is saving that model using the function save. So when you load everything to the model, then you do .save. This means that we want to save our model in the saved model format. And for that, you just need to give a path to where you want to save that. So for me, I chose saved model, then YOLO v3 model. You can call it whatever you like. So for me, what this is gonna do is create a folder called saved model, then create another folder inside of it called YOLO v3 model. And inside of this folder, we will have all the necessary folders and files for our model that we will use in production. So let me just save this. So in order to do this, to basically to do the transformation here, we just need to run this script. So if I go to my terminal here and I am inside the folder here, and also I have my virtual environment activated here. So the only thing I need to do is run Python, then checkpoint or ckpt to save model.py, and I will just run this here. So this script is very simple and it's gonna do what I have mentioned. It's just gonna load the checkpoints and then save them in the saved model format. And again, we're doing this because the saved model format is the convention used by TensorFlow when you try to use your model in production. You should avoid using checkpoints in production. Usually we use checkpoints just to save a certain state of the training, so that if we want to start from that state again at a later time, we can do that much more effectively. But for deploying your model in production, the way to do this is to save your model in the saved model format. So now our model should be inside a folder called saved model, and then inside of it we should have YOLO v3 model, and these are the files and folders that are necessary to basically to represent our model, but this representation is optimized for production. So this is these are the files that we will use when we want to run inference on new images in production, whether that be on the cloud or on edge, or however you want to deploy your model. So now that our model has been saved in the correct format that's used in production, let's see what we can do next. So now that we have our model in the right format for production, what we're gonna do now is to use this model in order to make predictions on new images. So for that, I have put together this simple script. So basically, the script will take as an argument the path to the image. It's also going to take the confidence score and the IOU, so intersection over union, as parameters. So again, this the confidence score parameter controls the detections that we want to show based on their confidence or based on their predicted probability. So whenever we predict a new object in the image, we get a value corresponding to it that tells us how confident the model is that this object belongs to this class. So it could be mask or no mask. So here we can control the value is between 0 and 1. And also the IOU is the intersection over union. So basically this parameter here controls the number of detections that appear in the same place. So sometimes the same object can have multiple bounding boxes around it. So when we control this parameter here, we can choose to have 1, 2, or more detections in one object. So I'm gonna keep it to 0.5 because this is what we use for at the training phase, at the testing phase, and also it's a convention used. But still, this shouldn't stop you from changing this and seeing the differences. If you're in production and you see that by changing this value here, you can improve the results, then please go ahead and do it. Don't let the convention stop you. But so what we're doing here is basically loading the model that we saved. So as you can see here, this is where we are loading the model from the saved model YOLO v3 model folder. Then we're reading our image. We're converting the image from BGR to RGB because since we're using OpenCV here, so of course, if you don't have OpenCV, you can just install it by pip install OpenCV Python. So for me, it should be already installed, but for you, it's gonna install it again. So with this, okay, requirement already satisfied. So when OpenCV loads an image, it actually reads the channels backwards. So the red channel is the last channel instead of the first. So all our images, when we did the training, were actually in the correct order. So they were RGB images. But since OpenCV package reads the channels backwards, we actually need to transform them after reading the image. So here we're changing them to RGB from BGR. Here we're just getting the size of the image. We're gonna need it later. Here we're running some pre-processing. So we're changing the size of the image here to correspond to the size that we used during the training. So for us, it's 416, and it's the same in the tests here. So I'm using this. And apart from this, here we're adding a new axis to the image because when the model reads a certain image, usually, or it's actually in this format here, so it reads it as an array where you have one, then width, height, then 3 channels. So this one here, this first dimension here, basically represents one image or 2 or 3, because when you do the training, you can run multiple images through the model at the same time. So we can control this. If you have, for example, 5 images, then this will change to 5. This means that the first dimension controls the number of images. Then then the rest of the dimensions basically represent the dimensions of your true image. So the width, the height, and the number of channels. So here we're just constructing this tensor, you can call it, so that it fits the way the model accepts input data. And then we're just running that input data through the model by using the function predict. And here we're taking those bounding boxes and we're putting them, so all of this part here, we're just getting those bounding boxes and we're drawing them on our image, and we're saving those detections in a new image called image with detections. And here I am actually converting the image back again to BGR, because if I don't do it like this, then when we look at the image, we actually going to see the channels backwards again. So here I'm turning it back again to BGR, and then here we can look at our image. We can see our image when we do show here. We can see our image in the right order of the channels. And here, this is just something that I added just for me, because I have some images with a large resolution and some of them with a low resolution. The ones with the high resolution, when I see them with OpenCV, I only see a partial part of the image. I can't see the whole image, and I can't resize the window. So I'm just verifying here if if the height or the width is bigger than 1500 pixels, then I just basically divide the width and height by 4 so that it fits to my screen and I can see the image here. And if it's smaller than these dimensions, then I just keep the same dimensions. But of course, feel free to remove this part here if you know that all of your images are small, for example. So okay, last here, okay, I resize the image again, using the display shape. So the display shape at the beginning, it's the same size as the original image. And then here after the verification, if this is true, then I divide the dimensions here. So I'm saving the new dimensions to the display shape, and then I use it here. And at the end, I just show the image here in a window called detections. So in order to run the script, it's very easy. You just need to pass these parameters to it. So let me just clear this, and then let's run Python, run inference, and then we can pass the path to image. And you can actually, you have the option to not pass these two values, confidence score and IOU, since we already have a default value. So if you don't pass them here, that means it's gonna take these values here. So for now, let's just pass this this parameter here. So for that, I have a few images that I want to test. So maybe I'm just gonna grab this image here, and let's run the inference on this image. And again, just in terms of terminology, when we say inference, this means that we just want to pass the image forward through the neural network. So there is no going backward like it happens during the training. So here, usually if you see it taken a little bit of time, it's mostly this time is mostly taken by the part where we're loading the model. So the part where we do the inference or where we do the prediction is lower than the time that takes to load the model into the memory. And here, as you can see, we have some nice predictions here. All of these people are wearing masks and we're detecting them correctly. The color red here points to the class mask. So everything is correct here. This one person here has been missed. So the model could not detect this. But overall, I say that it's good. And of course, you can just change the confidence score and you can see things changing. So for example, if I run this with confidence score, let's say instead of 0.7, let's do 0.3. This should show us more detections here. Let's see if we get more detections on our image. So again, it takes some time to just load the model. But in production, you should also take into consideration this time. So for example, if you have a running application, either on the cloud or on premise, then maybe you can remove this time of loading the model by loading the model at the beginning of running your application. So here, as you can see, we get more detections here, and we actually get this person here with a low probability, so 0.69. We get this other detection here with a lower probability. And of course, you can play with these parameters so that you can get the best confidence score for your specific task. So for example, here, if I choose, let's say, if I choose, for example, 0.65 as my confidence score, then this should give us some clean detections. But again, this is just for one image. But if you test on multiple images, this is gonna change, and the confidence score, you might not get all the results that you like. But still, as you can see, you have at the training time, you have things you can work on to improve your model, and also at the testing time. So here, as you can see, with this value for confidence score, we get this detected person here. We detect all the people with the correct classes, so that's a good thing. So if you have lots of images like this one and you test your model on them, if you find that 0.65 is a good confidence score for you, then use that. If that doesn't work for you, then change it and try to find the best one for you. And again, this is what we can play with at the test time or at the inference time, because now our model is trained. But if you see that your model is not doing well at test time, and even when changing the parameters, it still doesn't do well, then maybe the best thing you can do is to go back to the training phase and improve your model there. So I'm just clicking on my keyboard to exit this window, and maybe let's run the inference on another image. So run inference to image, and here this is an image of me with my mask, and in fact this is one of the images with the high resolution. I took this with my phone, so if I keep it as it is in its original resolution, then I won't be able to see all of the image here. So in this case, we're actually going to go through this condition here. So we're gonna resize our image in order to be able to see it. So here, I don't want to add any confidence score for this one. So let's just run the inference like this, and let's see what we get here. Okay, it's taking some time to read the model again, and it should show us the image with the bounding box around my face telling me whether I am wearing a mask or not. So yeah, as you can see, the model has been successful at predicting or at finding whether I'm wearing a mask or not. And as you can see, we can't clearly see what's the writing here. So this is actually showing mask and the confidence score. We see that the bounding box is in red, so this corresponds to the class mask. So that's why I am sure that it made the correct detection here. But we notice maybe a few things, like the bounding box is not tight enough. So this is something that you can't really work on during test time. So if you want your bounding boxes to be more, let's say, more squeezed around the objects, then this is something you need to work on at the training phase by working on the different anchor boxes, for example, training for longer time, and things like that. So let's just exit this here, and maybe let's do one last testing. So Python run inference, and I'm gonna do image, or what's the path to image. So it should be path to image, and here I'm gonna choose another image. My brother is wearing a mask in this image, so we're gonna use this image for inference. So let's wait a little bit while the model is being loaded into memory. But as you can see, we take a lot of time just loading the model. So this is when I was working on these types of problems in the industry, we always choose a specific time to load the model. So when our application is starting, we load our model then, so that it doesn't take time later. So here, as you can see, this is the picture of my brother, and we can see that the model has successfully predicted that my brother is wearing a mask. So as you can see, these images have never been through the model during training. So the model has never seen these images, but still it was capable of making good predictions. So this is a good indication. This is something that that basically encourages us to continue in the direction of, for example, continuing to try to improve the model so that we put this in production, for example. So with this final example, I think this is it for the part of making predictions, training and evaluating and making predictions with YOLO. And see you in the next video to see what we can do next. So in order to train our YOLO v3 deep learning model on Google AI platform, we actually need to go through a set of steps. So basically, these steps can be summarized in the following. So the first thing we need to do is to containerize our code using Docker. So when I say containerize here, it means that I want to basically pack all of my code and its dependencies in the same, let's say, compact form. So this tool here called Docker allows us to do exactly that. So what's going to help us do is create what's called a Docker image. This Docker image is basically, you can think of it as your code and its dependencies all put together in one, let's call it a compartment, a software compartment. And that software compartment, you can put it anywhere and it could run. You don't need to set up things for each time you want to deploy your code on a different machine. So that's what Docker allows us to do. And when we finish creating our Docker image using the tool Docker, we then need to push our Docker image to Google Container Registry. So you can think of Google Container Registry as you can think of it as GitHub, where we basically have our repositories. So you make changes, you put your repositories on GitHub, you make changes, you push those changes to GitHub. So in the case of GCR here, what we do is basically push Docker images. So what we create in this step, we can push it to Google Container Registry, and from there we can access it anywhere on Google Cloud Platform, including AI Platform Service. So once we finish this step here, once our Docker image is on Google Container Registry, we can then run what's called a training job and an evaluation job using Google AI Platform. So what AI Platform is going to do at this step is basically run our code on a remote machine on Google Cloud servers. So we can run multiple jobs, and by job we mean basically some process. So here we can run, for example, 2 different processes at the same time, one for training and one for evaluation, and that will take our data, and our data actually should be on a remote bucket. So on Google Storage, you can create what's called a bucket, and you can think of it as a drive on your local machine. So we put our data there, and then we can run the training from Google AI Platform. And last, we need to save the trained model. So for this, we need to save it somewhere where we can access it later. So usually what we do is save that model to a Google bucket. Again, a Google bucket, you can think of it just as a drive on your local machine, except that it's actually on Google Cloud Platform. So all of these are basically they represent a summary of what you need to do in order to run your training on Google AI Platform. But this phase here, I will not cover it in this course because I actually have already covered this process. So this training on Google AI Platform, I covered it in depth in one of my other courses. So this course of mine on Udemy is called Train and Deploy Deep Learning Models. And as you can see, there are already more than 2,000 students enrolled in it. And in this course, if we go to the course content, you can see that I have these 2 sections where I explain in depth what you need to do in order to run your training on Google Cloud Platform. So here we start by basically building a Docker image using Docker files. So this is the first step that I showed you. And then we can use that Docker image either locally or on the cloud. So at this section here, what we do is we start by pushing our image to Google Container Registry, and then we put our data on a Google storage. So this step maybe it's somewhere here, putting our data on Google storage. And then we can run multiple trainings. So here, as you can see, this lecture here, I talk about launching a training job on AI platform. Here, we run another training job. There should be also some other lecture here that where we basically put or where we run the evaluation job. So as you can see in this course here, I go in depth about all of these parts, and not just that, it also gives you some guidelines about how to, for example, build an image recognition system, and also how to deploy it at the end using Google Cloud Run and Flask. So that would be a bonus. But again, for training our YOLO V3 algorithm on Google AI platform, I will not cover it in the course, in the current course, but as you can see, if you go to my course on Udemy here, my other course called Train and Deploy Deep Learning Models, then you can learn how to do exactly that. So we're going to take the code that we started with. So you're going to take all of this code. You're going to use Docker in order to containerize your code. You're going to push it. You're going to create a Docker image, push it to Google Container Registry, and then you're going to run the training on Google AI platform. So with this would be the end of the main sections of the course. So see you later. Bye.